Introductory terminology and concepts. Differential equations. An ordinary differential equation is an equation involving an unknown function of one independent variable and one or more of its derivatives. In most general terms, such an equation describes a relationship among an independent variable x, a dependent variable y, which we think of as the unknown function, as well as one or more derivatives of y with respect to x. That's basically what the equation shown here says. Do not worry about its unfamiliar abstract form. Specific examples include y double prime equals y, where y is the unknown function or dependent variable, and the independent variable isn't specified. It could be any letter other than y, but we will typically use either x or t for the independent variable. Another example is y triple prime minus y times y prime equals cosine t. Here again, y is the dependent variable, and t is understood to be the independent variable because it's the variable in the cosine t term. A third example is du dt plus t times u equals minus u cubed. Here u is the dependent variable or the unknown function, and t is the independent variable. Notice that the independent variable is made explicit by the notation used for the derivative here. Now we should say something about the use of the word ordinary to describe the type of differential equations we're dealing with. By ordinary, we mean that the unknown function depends on only one variable, so all of the derivatives involved in the equation are ordinary derivatives as opposed to partial derivatives. A differential equation involving an unknown function of more than one variable and one or more partial derivatives of the unknown function is called a partial differential equation. Since we will only deal with ordinary differential equations, when we refer to a differential equation, we always mean an ordinary differential equation. The order of a differential equation is the order of the highest order derivative in the equation. In the first example above, the equation is second order because the highest order derivative is the second derivative. In the second example, the equation is third order, and the third example is a first order equation, since the first derivative of u is the only derivative that appears in the equation. A solution of such an equation is a function that satisfies the equation for all values of the independent variable in some interval. For example, one solution of the equation y prime plus y equals 0 is y equals e to the minus t for all t in the interval from minus infinity to infinity. Let's check that this is true. If we set y equals e to the minus t, then y prime equals e to the minus t times minus 1, and so y prime plus y equals minus e to the minus t plus e to the minus t, which equals 0 for all t. One solution of y double prime plus y equals 0 is y equals sine x for all x in the interval from minus infinity to infinity. And we check this as follows. We set y equals sine x, and since y prime would then be cosine x, y double prime would be minus sine x, and so y double prime plus y equals minus sine x plus sine x, which equals 0 for all x. The function y of x equals 1 minus x to the minus 1 power satisfies y prime equals y squared everywhere except at x equals 1. We verify this by setting y equal to 1 minus x to the minus 1 power, which tells us that y prime minus y squared is equal to minus 1 minus x to the minus 2 power times minus 1, which is y prime, minus 1 minus x to the minus 2 power. This is now 1 minus x to the minus 2 power minus the same thing, and so we get 0 for all x where y is defined, that is, for all x other than 1. Now, since the domain of any solution must be an interval, we have two distinct solutions from the same formula. We have y equals 1 over 1 minus x on the open interval from minus infinity to 1, and y equals 1 over 1 minus x on the open interval from 1 to infinity. A differential equation typically has infinitely many solutions that can be described using n parameters, where n is the order of the equation, that is, as an n-parameter family of functions. We call such an n-parameter family a general solution of the differential equation. Let's illustrate this with a few simple differential equations. For instance, consider the equation y prime plus y equals 0. It turns out that the general solution of that equation looks like y equals c times e to the minus t. The arbitrary constant c here is our parameter, and notice there's only one parameter due to the fact the differential equation is first order. For the second order equation y double prime plus y equals 0, it turns out that the general solution is the two-parameter family given by a times cosine x plus b times sine x, where a and b are the two parameters. For the first order equation y prime equals y squared, the one-parameter family of functions 1 over c minus t, where c is the parameter, is the general solution. Notice that this is a bit different from the previous two examples, since the parameter c does not appear as a coefficient of some simple solution. The parameters in a general solution are akin to the constants of integration that one encounters in calculus. In fact, any anti-differentiation problem is actually a very simple differential equation. For instance, the solution of y prime equals e to the minus t is just the indefinite integral of e to the minus t, which is minus e to the minus t plus an arbitrary constant c. Here we can think of this either as a one-parameter family of solutions of the differential equation or as the indefinite integral of the function e to the minus t. The differential equation y double prime equals 0 can be solved by simply anti-differentiating twice. Anti-differentiating once gives us y prime equals a constant c1, and a second anti-differentiation gives us c1x plus a second constant c2. So we've obtained a two-parameter family of solutions of the second-order differential equation, and we can think of the two constants as the constants of integration that arise from two anti-differentiation steps. In principle, it is possible to work backwards from a given n-parameter general solution to a corresponding nth-order differential equation. For example, consider the one-parameter family y equals the inverse tangent of x minus c. We compute the derivative y prime, remembering that the derivative of inverse tangent x is 1 over x squared, and we get 1 over 1 plus the square of x minus c, and the chain rule tells us to multiply by the derivative of x minus c, but that's just 1. Also, since y is the inverse tangent of x minus c, we can take the tangent of both sides and write x minus c equals tangent y. So we substitute tangent y for x minus c in the formula for the derivative, and we obtain y prime equals 1 over 1 plus tangent squared y. And we recall the trig identity 1 plus tangent squared y equals secant squared y, and so we have y prime equals 1 over secant squared y, or y prime equals cosine squared y. This is the differential equation associated with this one-parameter family of solutions. Notice that the method here essentially consists of computing the derivative and then eliminating the parameter c. Here's another example. Consider the two-parameter family y equals t times c1 plus c2 natural log of t. We begin by computing y prime and y double prime. Using the product rule, we have the derivative of t, which is 1, times c1 plus c2 log t, plus t times the derivative of the other factor, which is simply c2 times 1 over t, and so we have y prime equal to c1 plus c2 log t plus c2. So y double prime turns out to be simply c2 times 1 over t, or t to the minus 1. Now let's notice that if we multiply y prime by t, we get something very close to y itself. In fact, subtracting t times y prime from y leaves simply minus c2 times t. This tells us that c2 is equal to minus the fraction y minus t times y prime all divided by t. Now if we substitute that into y double prime, we find that y double prime equals minus the fraction y minus t times y prime divided by t squared. This is essentially what we're looking for. We'll tidy things up a little bit and write that equation as t squared y double prime minus t times y prime plus y equals 0. This is the differential equation with general solution t times c1 plus c2 log t. Initial value problems. A first-order initial value problem consists of a first-order differential equation along with a given desired value of the solution at some point in its domain. In general, such a problem looks like y prime equals f of x and y, with y of x naught equal to y naught. For example, given that a general solution of y prime equals y squared is y equals 1 over c minus t, solve the initial value problem y prime equals y squared with y of 1 equal to 2 and state the interval on which the solution is defined. Since we're given the general solution here, the problem amounts only to determining a particular value of the constant c. We want y of 1 to equal 2, so we substitute 1 into the general solution, obtaining 1 over c minus 1, and it turns out that that equals 2 if c is equal to 3/2. So now we have y equals 1 over 3/2 minus t, and if we multiply the top and bottom of that fraction by 2, that turns into 2 divided by 3 minus 2t. Now, since the denominator of that fraction is equal to 0 at t equals 3/2, and because our initial condition is given at t equal to 1, the interval on which the solution is defined is the largest interval that contains 1 but does not contain 3/2, and that is the interval consisting of all t less than 3/2. A second-order initial value problem consists of a second-order differential equation along with given desired values of the solution and its first derivative at some point in its domain. So in general, we have a second-order differential equation, y double prime equals some function of x, y, and y prime, and initial conditions of the form y of x naught equals y naught, and y prime of x naught equals some number m naught. We use the letter m here because we can think of that value as the given slope of the solution at x naught. Example: given that a general solution of y double prime plus 4y equals 0 is y equals c1 cosine 2t plus c2 sine of 2t, solve the initial value problem y double prime plus 4y equals 0, y of 0 equals 2, and y prime of 0 equals minus 1. Because of the initial condition on the derivative of y, we need to compute y prime here. If y equals c1 cosine 2t plus c2 sine of 2t, then y prime is equal to c1 times minus sine 2t times 2, or minus 2c1 sine 2t, plus c2 times cosine 2t times 2, or 2c2 cosine 2t. Now let's see what the initial condition y of 0 equals 2 tells us about the constants c1 and c2. Substituting t equal to 0 into the expression for y, we obtain c1 times 1 plus c2 times 0, and we want that to equal 2. Now that tells us right away that c1 is equal to 2. Next we substitute t equal to 0 into y prime, and we find that the condition y prime of 0 equals minus 1 tells us that minus 2c1 times 0 plus 2c2 times 1 equals minus 1, and that tells us right away that c2 is equal to minus 1/2. So we now have our solution, y equals 2 times cosine 2t minus 1/2 of sine of 2t. Linear differential equations. A differential equation is linear if it is linear in the dependent variable and its derivatives. A linear first-order equation can always be written in the form of P1 times y prime plus P0 times y equals f, where P1 is not 0. Here, P0 and P1, as well as f, are allowed to be functions of the independent variable, even nonlinear functions. A linear second-order equation can be put in the form of P2 y double prime plus P1 y prime plus P0 times y equals f, where P2 is not 0. And again, P0, P1, P2, and f are allowed to be nonlinear functions of the independent variable. In general, a linear nth-order equation can be put in the form of P sub n times the nth derivative of y plus terms down to P1 times the first derivative of y plus P0 times y equals f, where P sub n is not equal to 0. Notice that the left side of each of these equations has a form that's analogous to a polynomial, except instead of powers of the variable, we have derivatives, with y itself, the 0th derivative of y, playing the role of the 0 power. And the p's play the role of the coefficients. However, notice here that the p's needn't be constants. When the function f on the right-hand side of any of these equations is equal to 0, that equation is said to be homogeneous. So a linear equation is homogeneous if every non-zero term involves either y or one of its derivatives. Now we note that usually we write linear equations in a form in which the leading coefficient is 1, and we also try to avoid subscripted coefficients when possible. So we might write a first-order linear equation as y prime plus py equals f, and a second-order linear equation as y double prime plus py prime plus qy equals f, and so on. We can always obtain such a form for an equation by dividing by the leading coefficient. Now let's look at a few sample equations and describe them in terms of their order, whether they're linear or nonlinear, and if they're linear, whether they're homogeneous or non-homogeneous. The equation y prime plus e to the minus x times y equals sine x is a first-order equation, and it is linear, and because of the sine x term on the right-hand side, it is a non-homogeneous linear equation. The equation t times y double prime plus y prime plus t squared y equals 0 is a second-order equation. It is linear, and since every term on the left-hand side involves y and the right-hand side is 0, it is a homogeneous linear equation. The equation t times y double prime plus y squared equals 0 is again a second-order equation, but because of the y squared term, it is a nonlinear differential equation. X double prime equal to x times x prime is a second-order equation, but because of the x times x prime term, it's nonlinear. Y prime times y equals sine x is a first-order equation. The y prime times y term on the left makes the equation nonlinear. X double prime equal to 3x minus e to the minus t times x prime is a second-order differential equation where t is the independent variable and x is the dependent variable. It is linear, and it is also homogeneous. Note that the equation could be rearranged so that it looks like y double prime plus e to the minus t x prime minus 3x equals 0. And finally, the equation u prime equals cosine u is clearly first order, but because of the dependent variable u appearing inside the cosine function, it's a nonlinear differential equation. The importance of being linear. Given one or more solutions of a linear homogeneous differential equation, any linear combination of them is also a solution. And by linear combination, we mean a sum of constant multiples. For instance, let's consider the differential equation y double prime equals 0. Two simple solutions of this equation are x and 1. And because the equation is linear and homogeneous, any constant a times x plus any constant b times 1 is also a solution. For the equation y double prime plus y equals 0, it's easy to see that cosine t and sine t are solutions, and so, because the equation is linear and homogeneous, any constant a times cosine t plus any constant b times sine t is also a solution. For the first order equation y prime minus y equals 0, it's easy to see that e to the x is a solution, and so, because the equation is linear and homogeneous, any constant times e to the x is a solution as well. For the equation y double prime minus y equals 0, both e to the t and e to the minus t are solutions, and again the equation is linear and homogeneous, and so c1 times e to the t plus c2 e to the minus t is also a solution for any constant c1 and c2. Now, without either linearity or homogeneity, this doesn't work. For instance, the differential equation y double prime equals 2, which is linear but not homogeneous, has a simple solution x squared, but if we simply multiply x squared by 2, or any other constant other than 1, we have something that doesn't satisfy the equation anymore. Y prime equals y squared is a nonlinear equation, and one solution is 1 over 1 minus t. Multiplying that solution by any constant other than 1 or 0 produces a function that no longer satisfies the differential equation. Another important property of linear differential equations is that given any two solutions, their difference is a solution of the corresponding homogeneous reduced equation. This is the homogeneous differential equation in which all the terms involving the unknown are the same as the original equation. For example, the non-homogeneous linear equation y prime equals 2t has solutions t squared plus 2 and t squared, which we can check quite easily. Notice that the difference between those two solutions is simply 2, and 2 satisfies the homogeneous differential equation y prime equals 0. The non-homogeneous linear equation y double prime equals 2 has solutions t squared plus t as well as t squared plus 1, which again are easy to check. The difference between those solutions is t minus 1, and t minus 1 satisfies the homogeneous differential equation y double prime equals 0. The non-homogeneous linear equation y double prime plus y equals 1 has solutions cosine x plus 1 and sine x plus 1. The difference there is cosine x minus sine x, and that function satisfies y double prime plus y equals 0. So what's happening here in general? Let's suppose that u and v are solutions of the first order non-homogeneous equation y prime plus py equals f. That means that u prime plus pu is equal to f, and v prime plus pv equals f. And if we subtract the second of those equations from the first, we have u prime minus v prime, which is the same as the derivative of u minus v, plus pu minus pv, which is p times u minus v, equal to f minus f, which is 0. Therefore, u minus v satisfies the homogeneous reduced equation y prime plus py equals 0. This property of linear differential equations turns out to be useful in solving them. The method is called superposition. For example, consider the equation y prime plus y equals t. It's not difficult to see that one particular solution is the linear function z of t equals t minus 1. Now, let's let y of t be any other solution. Then if we plug the difference y minus t minus 1 into the left side of the differential equation, we have the derivative of y minus t minus 1 plus y minus t minus 1. And since y and t minus 1 both satisfy the original differential equation, that ends up being t minus t, which is 0. Now, since the general solution of of the reduced equation y prime plus y equals 0 is y equal to an arbitrary constant c times e to the minus t, we know that the difference y minus t minus 1 has to be some constant c times e to the minus t. Now, by adding t minus 1 to both sides, we conclude that y of t is equal to c times e to the minus t plus t minus 1, and therefore that describes the general solution of the non-homogeneous equation. Y of t equals t minus 1 plus an arbitrary constant c times e to the minus t. The bottom line here is that the general solution of a non-homogeneous linear differential equation always has the following form: y equals any particular solution plus the general solution of the reduced equation. This general solution of the reduced equation is often called a complementary solution, and with that terminology, y equals particular plus complementary. Now let's finish up here with a very basic example. The simplest kind of illustration is just an anti-differentiation problem of the type 1 encounters in Calculus 1. Consider the equation y double prime equals 6x. Anti-differentiating once gives us y prime equals 3x squared plus a constant of integration c1, and a second anti-differentiation gives us y equals x cubed plus c1 times x plus a second arbitrary constant c2. Here, x cubed is the particular solution. In fact, it's the only term here that individually satisfies the differential equation, and c1x plus c2 is our complementary solution. Notice that that is the general solution of the reduced equation y double prime equals 0. Solving linear first-order differential equations. The simplest linear first-order equation is y prime equals ky, where k is constant. It is a linear equation because its terms depend on y and y prime in a linear way, and it is first order because the first derivative of y is the highest order derivative involved. We begin with a couple of basic observations. First, the equation has the trivial solution y of t equals 0 for all t. Secondly, if y is a solution and c is a constant, then c times y is also a solution, and in particular, minus y is also a solution. Now let's see why this is true. We substitute c times y into the differential equation and obtain the derivative of c times y equals k times c times y. Since the derivative of c times y is just c times the derivative of y, that equation is equivalent to c times y prime equals k times c times y. And if c isn't 0, we can divide both sides by c, and we find that the equation is equivalent to y prime equals ky. So if y is a solution of the differential equation, then so is c times y. So let's find the positive solutions. For every positive solution, there will be a corresponding negative solution because of the previous observation. The equation is separable because we can rewrite, using t as the independent variable, dy dt equals ky in the form dy divided by y equals k times dt, where we've simply divided both sides of the equation by y and multiplied by dt. This form allows anti-differentiation of each side separately, resulting in natural log of y equals k times t plus c, where c is an arbitrary constant or parameter. Now we raise e to each side of that equation and obtain y equals e to the kt plus c, which is the same thing as e to the c times e to the kt by a basic property of exponents. Now since c is an arbitrary constant, e to the c is an arbitrary positive constant, and that tells us we can write our solution as y equal to an arbitrary constant c times e to the kt, where we simply have renamed e to the little c as capital C. Moreover, we get all of the negative solutions as well as the zero solution by simply allowing this capital C to be negative or zero as well as positive. Now let's also notice that the capital C here happens to be the value of this solution at time t equals 0. So we can express the solution as y of 0 times e to the kt. So what we have found is that y satisfies the differential equation y prime equals ky if and only if y of t equals y of 0 times e to the kt. Now we can also express that solution in terms of the value of y at any other point t0 as y of t0 times e to the k times t minus t0. Notice that the value here at t equal t0 is in fact y of t0. We will often encounter the same kind of equation written in a different form, y prime plus ky equals 0. Notice that the constant k is not the same as the constant k in the previous equation. In fact, they're negatives of each other. This equation is equivalent to y prime equals minus ky, and so we can write down the solution by simply taking the solution from the previous equation and replacing k with minus k. So we have y of t equals y of 0 times e to the minus kt, or y of t0 times e to the minus k times t minus t0. Now let's look at a somewhat more general case, y prime plus py equals 0, where p is a given function of the independent variable. The equation is still separable. Subtract py from both sides, then divide by y and multiply by dt, and we have dy over y equals minus p of t dt. Now, anti-differentiating both sides gives us natural log of y equals minus the indefinite integral of p of t. And we put the arbitrary constant of integration c here for emphasis, and we can think of the integral of p of t dt here as some particular antiderivative. Now we do more or less the same thing we did in the previous situation where p was constant. We raise e to both sides of the equation here and factor off e to the capital C, and then simply rename e to the capital C. So we have y equals an arbitrary constant c times e to the minus integral of p of t dt, where that integral could be any particular antiderivative of p. For example, let's find a general solution of y prime plus 2t times y equals 0. We separate the differential equation and get dy over y equals minus 2t dt. We integrate both sides under the assumption that y is positive and obtain natural log of y equals minus t squared plus c, which is the same thing as y equals e to the c times e to the minus t squared. Now we replace e to the c with a capital C that is allowed to be positive, negative, or 0, and we have our solution, y equals capital C times e to the minus t squared. Another example. Find a general solution of y prime plus y times sine x equals 0. Now we separate the equation as before. We get dy divided by y equals minus sine x times dx. Then we integrate both sides, getting natural log of y equals cosine x plus c. Then raise e to both sides of that equation and get y equals capital C times e to the cosine x. One more example. Find a general solution of y prime plus 3 divided by 5 minus 2t times y equals 0. Again, we begin by separating the equation. We subtract the second term from both sides, divide by y, multiply by dt, to get dy over y equals minus 3 dt divided by 5 minus 2t. Next, we integrate both sides, and on the left-hand side, we get natural log of y, assuming y is positive, and on the right side, we can bring a factor of minus 3 outside the integral, And then we'll make a substitution. U equals the denominator, 5 minus 2t, which gives us du equals minus 2 dt, or dt equals du divided by minus 2. Now we'll bring a minus 1/2 outside the integral and integrate du over u to get natural log of u. So we have 3/2 natural log of u plus c. Since 3/2 times log u is the same as log of u to the 3/2 power, we can write this equation as the natural log of y equals the natural log of the 3/2 power of 5 minus 2t plus c. Now, when we raise e to each side of this equation, we get y on the left side and a constant times 5 minus 2t to the 3/2 power. Now, after working a few examples in detail, going through the steps of separating the equation and then integrating both sides, let's notice that the final form is very easy to remember. The solution of y prime plus py equals 0 will always be c times e raised to any antiderivative of minus p. The non-homogeneous case. We're now going to consider the equation y prime plus py equals q, where p and q are functions of the independent variable, possibly constants. A crucial observation is that the difference between any two solutions will satisfy the corresponding homogeneous or reduced equation y prime plus py equals 0, whose general solution we've just learned is y equals c times e raised to any antiderivative of minus p. So suppose we can find some particular solution, call it z, then if y is any other solution, we know that y minus z will equal c times e raised to any antiderivative of minus p for some value of the constant c. So we can add z to both sides and conclude that every solution y has the form c times e raised to any antiderivative of minus p plus the particular solution z. This superposition method is a very convenient way to solve the equation, provided we can find a particular solution z without too much effort, such as when p and q are constant functions. For example, find a general solution of y prime plus 3y equals 2. Since p and q are constants here, it's natural to look for a constant solution. For any constant y prime will be 0, and 3y will equal 2, and so that constant would have to be 2/3. So we take z equal 2/3 as our particular solution. Next, we observe that the general solution of the reduced equation y prime plus 3y equals 0 is y of x equals c times e to the minus 3x. Therefore, we conclude that the general solution of the original equation is y of x equals c times e to the minus 3x plus 2/3. Using an integrating factor. Returning to the general case, y prime plus py equals q, where p and q are functions of the independent variable, one might think of the product rule and surmise that if the left-hand side were multiplied by an appropriate function, it might be recognizable as the derivative of a certain product. That is, in fact, true, and an appropriate function is e to the integral of p, where the symbol integral p represents any antiderivative of p. We call this function an integrating factor for the differential equation. Multiplying both sides by the integrating factor gives e to the integral of p times y prime plus p times e to the integral of p times y equals q times e to the integral of p, and notice that the second term on the left-hand side is the same as the derivative of the integrating factor times y. So the left-hand side is now the derivative of the product e to the integral of p times y. And so the differential equation has now become just an anti-differentiation problem. The derivative of the integrating factor times y equals q times the integrating factor. So next we simply integrate both sides and then divide by the integrating factor. Here's the procedure in steps. Step 1 is to anti-differentiate p. Here we typically take the constant of integration to be 0 for simplicity. Next we raise e to that power and simplify. This gives us our integrating factor. Next we multiply the equation by the integrating factor and check that the left-hand side is the same as the derivative of the product of the integrating factor and y. The last step is to integrate and divide by the integrating factor. Showing the constant c for emphasis, this proceeds generically as follows. Anti-differentiating gives us the integrating factor times y equal to an antiderivative of q times the integrating factor plus an arbitrary constant c. And next we divide by the integrating factor, that is, multiply by e to the minus integral of p, and we get y equal to e to the minus integral of p times an antiderivative of q times the integrating factor plus the constant c divided by the integrating factor, or c times e to the minus integral of p. Example. Find a general solution of y prime plus 3y equals 2 times e to the minus x. The first thing we'll do is identify p. P is equal to 3, and a simple antiderivative of that is 3 times x. So our integrating factor, e to the integral of p, is e to the 3x. Now we multiply by the integrating factor, and we get e to the 3x times y prime plus 3 times e to the 3x times y equals 2 times e to the minus x times e to the 3x. Since 3 times e to the 3x is an antiderivative of e to the 3x, the left-hand side is the derivative of the product e to the 3x times y because of the product rule. And we simplify the right-hand side and get 2 times e to the 2x. Next we integrate and solve for y. An antiderivative of the left-hand side is e to the 3x times y, and we integrate 2e to the 2x, getting e to the 2x, plus an arbitrary constant c. Finally, we multiply through by e to the minus 3x and get y equal to e to the minus x plus c times e to the minus 3x. Another example. Find a general solution of y prime plus 3y divided by 5 minus 2t equals 1. The function p here is 3 divided by 5 minus 2t, so we need to anti-differentiate that function. We can pull 3 outside the integral sign, and if we substitute u equal to 5 minus 2t, we find that dt will be minus du over 2, so we'll go ahead and pull minus 1/2 outside the integral and integrate du over u, and we get minus 3/2 times the natural log of u, or the natural log of 5 minus 2t. Since we're going to raise e to that power, let's go ahead and write it as the natural log of the minus 3/2 power of 5 minus 2t. So now our integrating factor is e to that power, which becomes simply the minus 3/2 power of 5 minus 2t. Next we multiply through by this integrating factor. Notice that the second term becomes 3 times the minus 5/2 power of 5 minus 2t, which is in fact the derivative of the integrating factor. So the left-hand side is precisely what we would get if we used the product rule on the product 5 minus 2t to the minus 3/2 power times y. So our differential equation is now the derivative of the product of the integrating factor and y equal to the right-hand side, which is the original right-hand side 1 times the integrating factor. So now we integrate and solve for y. Of course, the left-hand side simply becomes the integrating factor times y, and we integrate 5 minus 2t to the minus 3/2 power by adding 1 to the power, obtaining the minus 1/2 power, and by dividing by the new exponent, which gives us a factor of minus 2 on the outside. But because of the minus 2t inside that power, we also need to divide by minus 2. And of course, we don't want to forget to add the constant of integration. Finally, we multiply through by 5 minus 2t to the positive 3/2 power and obtain y equal to 5 minus 2t all to the first power plus the constant c times the 3/2 power of 5 minus 2t. This is our general solution. One more example. Find a general solution of y prime plus y times tangent x equals sine x. The coefficient of y on the left-hand side is tangent x. That's our function p that we need to antidifferentiate. We hopefully recall from calculus that an antiderivative of tangent x is the natural log of the absolute value of secant x. Now for this purpose, we may as well assume that we're on an interval where secant x is positive, so we can drop the absolute values and obtain our integrating factor by raising e to the natural log of secant x, which gives us secant x. Next, we multiply by this integrating factor, and the differential equation becomes y prime times secant x plus y times secant x tangent x equals tangent x. Now, since the derivative of secant x is secant x tangent x, the left-hand side here is, in fact, the derivative of y times the integrating factor. So our differential equation has become the derivative of y times secant x equals tangent x. So next we'll integrate and solve for y. The left-hand side becomes y times secant x, and the right-hand side becomes the indefinite integral of tangent x, which again is the natural log of the absolute value of secant x plus c. Now here we want to retain the absolute values around secant x so that our solution makes sense even when secant x is negative. Our final step now is to divide by secant x, or multiply through by cosine x, and we get the natural log of the absolute value of secant x plus c all times cosine x. We'll end here with a summary of what we've learned. The homogeneous equation y prime plus py equals 0 is separable. Its general solution turns out to be y equals c times e to any antiderivative of minus p. If p is constant, then this becomes y of t equals c times e to the minus pt, a simple exponential solution. The non-homogeneous equation y prime plus py equals q is not separable unless p and q are constants. When p and q are constants, the general solution is y of t equals c times e to the minus pt plus a constant particular solution q divided by p. In all cases, multiplying by the integrating factor, e to any antiderivative of p, yields the equation the derivative of the integrating factor times y equals the integrating factor times q, which can be solved by antidifferentiating both sides. Applications involving linear first-order equations. A mixing problem. A 100-liter tank is initially full of pure water. At time t equals 0, salt water with salt concentration 50 grams per liter begins to flow into the tank at a rate of 3 liters per minute. The solution in the tank is kept well mixed and flows out of the tank at the same rate. Find the amount of salt in the tank after t minutes. So let's begin by letting A of t equal the amount of salt in the tank in grams at time t. The key to the problem is the observation that the rate of change in the amount, or its derivative, is equal to the salt mass flow rate in minus the salt mass flow rate out. The data in the problem involves concentrations in grams per liter and the volume flow rate 3 liters per minute. But we can obtain mass flow rate by multiplying concentration times volume flow rate. So we obtain units of grams per minute when we multiply grams per liter times liters per minute. So the mass flow rate in is equal to 50 grams per liter times 3 liters per minute, and the mass flow rate out is equal to the concentration of salt in the tank, which is the amount A of t divided by 100 times the volume flow rate 3 liters per minute. So we have A prime of t equal to 50 times 3 minus A of t divided by 100 times 3. Now we rearrange that differential equation and write it as A prime plus 0.03 times A equals 150. The initial value of the amount is A of 0 equals 0, since initially the tank is full of pure water. This is our initial value problem. Since the coefficient of A here, as well as the right-hand side, is constant, it's easy to solve this equation by superposition. We'll first write down the general solution of the corresponding reduced homogeneous equation, which is A prime plus 0.03A equals 0, and that general solution is C times e to the minus 0.03t. Then we add to that a constant particular solution, which is 150 divided by 0.03, or 5,000. Next, we use the initial condition to determine the constant c. Since a of 0 is 0, we have 0 equal to c times 1 plus 5,000, which tells us that c is minus 5,000, which tells us that our solution a of t, after factoring out 5,000, is 5,000 times 1 minus e to the minus 0.03t. So we see that as t goes to infinity, the amount of salt in the tank approaches 5,000 grams, which if we divide by the volume of the tank, 100 liters, gives us the 50 grams per liter concentration of the fluid that's flowing into the tank. So after a long time, the salt solution in the tank becomes virtually identical to the salt solution that's flowing into it, as we should expect. Now let's look at a mixing problem involving a non-constant volume. A 100-liter tank initially contains 40 liters of pure water. At time t equals 0, salt water, with salt concentration 50 grams per liter, begins to flow into the tank at a rate of 3 liters per minute. The solution in the tank is kept well mixed and flows out of the tank at a rate of 2 liters per minute. Find the amount of salt in the tank at the instant when the tank becomes full. So notice that this is very similar to the previous problem, except that the volume flow rate out is less than the volume flow rate in, and so the volume of fluid in the tank increases with time. In fact, since the volume flow rate in is 3 liters per minute and the outflow rate is 2 liters per minute, the difference, 1 liter per minute, is the rate of increase of the volume. And since the volume is initially 40 liters, the volume thereafter is 40 plus 1 times t, a formula which works until the volume is 100 when the tank begins to overflow, and that happens when t is 60. So we have V equals 40 plus t for all t between 0 and 60. So now let's write down A prime equal to the mass flow rate in minus the mass flow rate out. Just as in the previous problem, the mass flow rate in is 50 grams per liter times 3 liters per minute, but now the concentration of salt in the tank is equal to A of t divided by the volume, which is 40 plus t, and the volume flow rate out is 2 liters per minute. Now simplifying and rearranging, we have A prime plus 2 divided by 40 plus t times A equals 150, and again, since initially we have pure water in the tank, A of 0 is equal to 0. This is the initial value problem we need to solve, and our goal here is to compute the amount of salt in the tank at time 60, or in other words, we want to find A of 60. Since the coefficient of A in the differential equation is not constant, we'll need to use an integrating factor to find the solution. Now to compute the integrating factor, we'll integrate 2 divided by 40 plus t, which gives us 2 times the natural log of 40 plus t. Now since we're going to raise e to that power, let's go ahead and write that as the natural log of 40 plus t squared. Now e to that power is our integrating factor, 40 plus t quantity squared. Next we multiply each side of the differential equation by the integrating factor, and we obtain 40 plus t quantity squared times A prime plus 2 times 40 plus t to the first power times A equal to 150 times the square of 40 plus t. It's easy to see now that the left-hand side is the derivative of the product of the integrating factor and A, so we'll antidifferentiate each side and obtain the square of 40 plus t times A equals 50 times the cube of 40 plus t plus a constant of integration c. Notice that this antidifferentiation is more straightforward than it otherwise might be because the derivative of 40 plus t, the inside function here, is just 1. So now we divide both sides by the square of 40 plus t, and we get 50 times 40 plus t to the first power plus c divided by the square of 40 plus t. Now let's put this in a nicer form over a common denominator equal to the square of 40 plus t. Let's also factor out 50 and write this as 50 times the cube of 40 plus t plus a constant c, which is actually the previous c divided by 50, all divided by the square of 40 plus t. Next, we use the initial condition to determine the constant c. We want a of 0 to be 0, and so we need only look at the numerator of our fraction and set 40 cubed plus c equal to 0. This gives us c equal to minus 40 cubed, or minus 64,000. So our solution finally is 50 times the cube of 40 plus t minus 64,000, all divided by the square of 40 plus t. And so to determine the amount at the instant when the tank begins to overflow, we evaluate a of 60, and we have 50 times 100 cubed minus 64,000, all divided by 100 squared, which after a bit of calculation becomes 4,680 grams of salt. Continuous approximation of an annuity. Suppose that you have a $200,000 investment for which it's reasonable to assume a 9% annual rate of return. Estimate the maximum fixed amount you can continuously withdraw per year for 10 years. So the idea here is that we'd like to end up with $0 in the account after 10 years. With capital A standing for the amount after t years, we have that the rate of change in the amount, or the derivative of A, is equal to the rate of increase due to interest minus the rate of withdrawal. Since the interest rate is 9% per year, interest contributes 0.09 times the amount to the rate of change in the amount. The rate of withdrawal is the unknown in our problem, so let's call that W. So our differential equation is A prime equals 0.09A minus W, and we have an initial value A of 0 equals 200 if we assume that the amount is in thousands of dollars. And the problem at hand is to find W so that A of 10 is equal to 0. The differential equation here is simple enough to solve by superposition. We'll write down the general solution of the corresponding reduced homogeneous equation, A prime equals 0.09A, which is a constant c times e to the 0.09t, and then add a particular constant solution, which would be W divided by 0.09, which is roughly the same as 11.1 times W. Now let's use the initial condition, A of 0 equals 200, to find the constant c. Evaluating our solution at time 0 gives us c plus 11.1 W, and we want that to be 200, and that tells us that c is equal to 200 minus 11.1 W. So now we have the solution in terms of W. A of t equals 200 minus 11.1 W, all times e to the 0.09t, plus 11.1 W. Next, we'll determine W by setting A of 10 equal to 0. Substituting t equals 10 into our solution gives us 200 minus 11.1 W times e to the 0.9 plus 11.1 W, and we want that to equal 0. A little calculation reveals that the left-hand side here is roughly the same as 492 minus 16.2 W, and that equals 0 if W is equal to roughly 30.4. So finally, since we're working in thousands of dollars, the answer to our problem is that we can withdraw continuously about $30,400 per year. So note that we start with $200,000, but end up withdrawing over $300,000 over 10 years. Motion of a falling body with air resistance. A basketball with mass 0.6 kilograms is dropped from a height of 20 meters and hits the ground 3.1 seconds later. Find the velocity with which it hits the ground. The setup of the differential equation in this problem is based on Newton's second law. Mass times acceleration equals force. we'll write mass times acceleration as 0.6 kilograms times the derivative of the velocity with respect to t. The downward force of gravity is equal to minus the mass, 0.6 kilograms, times the acceleration due to gravity, for which we'll use 9.8 meters per second squared. We take air resistance into account as a force that always acts in the direction opposite the velocity and is proportional to the velocity. So we write this force as minus k times the velocity v, where k is a positive constant. Now if we divide through by 0.6 and then rearrange, we have the equation v prime plus 1.67 times k times v equals minus 9.8. And since the ball is dropped at time 0, the initial velocity v of 0 is 0. Here again, the general solution of the differential equation is easy to write down by superposition. The general solution of the homogeneous reduced equation is c times e to the minus 1.67 kt, and to that we add a particular constant solution, which is minus 9.8 divided by 1.67 k. Next we use the initial condition v of 0 equals 0 and find that c is equal to 9.8 divided by 1.67 k, which is roughly the same thing as 5.87 divided by k. Now with that expression for c, the two terms in the velocity have a common factor of 5.87 over k. In fact, we'll factor out minus 5.87 divided by k and write the velocity as minus 5.87 over k times 1 minus e to the minus 1.67 kt. So now we have the velocity in terms of the constant k, which we'll now find based on the fact that the ball hits the ground after 3.1 seconds. In other words, the height is equal to 0 at time 3.1 seconds. So we need to obtain the height function, and we can do that by integrating the velocity. So letting h of t stand for the height at time t, we integrate to find that h of t is equal to minus 5.87 divided by k times t plus 0.6 divided by k times e to the minus 1.67 kt. The 0.6 here comes from 1 over 1.67 and is actually the given mass of the basketball. And finally, we add a constant of integration, c. Next, we'll find that constant of integration using the initial condition h of 0 equals 20, since the ball was dropped from a height of 20 meters. Substituting t equals 0 into the height function gives us minus 5.87 divided by k times 0 plus 0.6 divided by k plus the constant c. That equals 20 if c is equal to 20 plus 3.52 over k squared. Now since we have that constant in terms of k, we have our height function also in terms of k. So now we'll substitute t equals 3.1 into this expression for the height and set the result equal to 0. This will give us an equation in which the only unknown is k. It's a transcendental equation which we have no hope of solving by hand, so we try to solve it numerically. If we plot the graph of h of 3.1 versus k using a graphing calculator, we'll see a graph that looks something like this between 0 and 1. Using the built-in solver in the calculator, or using Newton's method for instance, we find that h of 3.1 is equal to 0 if k is 0.65, rounded to 2 decimal places. So now we go back to our velocity function and substitute in the value of k that we've found, which gives us v of t equal to, roughly, minus 9 times 1 minus e to the minus 1.1 t. And so finally we can calculate v at the time the ball hits the ground. V of 3.1 is roughly minus 8.7 meters per second, which turns out to be roughly minus 31 kilometers per hour. Separable differential equations and applications. Separable equations. A first-order differential equation is said to be separable if it can be written in the form of g of y times dy equals f of x dx. In other words, it can be arranged so that the left-hand side is a differential involving the variable y and independent of x, and the right-hand side is a differential involving x and independent of y. For an equation of this form, we can anti-differentiate each side independently. Now, implicit here is that there's an arbitrary constant of integration on each side of the equation. Those constants can be combined into a single arbitrary constant, and we can write that constant on the right-hand side for emphasis and think of the two integrals there as particular antiderivatives. If we want the solution for which y is equal to some value y0 when x is equal to x0, we can use definite integration as follows. We can integrate the left-hand side from y0 to an arbitrary y, and simultaneously integrate the right-hand side from x0 to an arbitrary x. This could be justified using a more detailed argument, but just notice that you have corresponding values of x and y in the lower limits of integration, as well as corresponding values in the upper limits of integration. Now, since we're using x and y as limits of integration, we should introduce different dummy variables of integration on each side. So let's write the integrand on the left as g of z dz, and the one on the right as f of z dz. Now let's look at a couple of examples. First, let's find a general solution of y prime equals 1 plus y squared all times cosine x. Here y prime could be written as dy over dx, and so we'll multiply both sides of the equation by dx and divide by 1 plus y squared, and we obtain dy over 1 plus y squared equals cosine x dx. Next, we anti-differentiate each side. For the left side, we recall that the derivative of inverse tangent y is 1 over 1 plus y squared, and so the antiderivative we want here is inverse tangent of y. And of course, the right-hand side gives us sine x, and we add an arbitrary constant to the right-hand side. Next, we'll solve for y by taking the tangent of both sides of the equation, and we end up with the solution y equals tangent of sine x plus c. Another example. Solve the initial value problem y prime equals y squared divided by 1 plus t with y of 0 equal to 1. Since t is the independent variable here, we think of y prime as dy over dt, then we multiply both sides by dt and divide both sides by y squared. This gives us dy over y squared equals dt over 1 plus t. Now, since we're given an initial value at t equal to 0, we're going to integrate the right-hand side of the equation from 0 to t, and we'll integrate the left-hand side over the corresponding interval from y equals its value at t equals 0, which is 1, up to an arbitrary y. Now, an antiderivative of 1 over z squared is minus 1 over z, and we'll evaluate that from 1 to y. And on the right-hand side, an antiderivative of 1 over 1 plus z is the natural log of 1 plus z, and we evaluate that from 0 to t. This gives us minus 1 over y minus 1 on the left side, and on the right-hand side, the natural log of 1 plus t minus the natural log of 1, which is 0. Next, we subtract 1 from both sides, multiply both sides by minus 1, and then take the reciprocal of both sides, and we end up with y equal to 1 over 1 minus the natural log of 1 plus t as our solution. Orthogonal trajectories. Two families of curves that intersect everywhere at right angles are called orthogonal trajectories. For example, the family of straight lines through the origin and the family of circles centered at the origin comprise two families of orthogonal trajectories. Such pictures can be far more complicated, as indicated here. If one family satisfies the differential equation dy dx equals f of x and y, then the other family must satisfy dy dx equals minus 1 divided by f of x and y, since tangent lines will be perpendicular if their slopes are negative reciprocals. Now, the connection here between orthogonal trajectories and separable differential equations is the fact that if one of these equations is separable, then so is the other. Now let's look at an example. The family of curves y equals c times cosine x satisfies y prime equal to minus c sine x, which is the same thing as minus y times tangent x, since cosine x times tangent x is equal to sine x. Now, by taking the negative reciprocal, we find that the corresponding orthogonal family satisfies y prime equal to cotangent x divided by y. Now let's solve that differential equation. It's separable. We multiply through by y and by dx, and we have y dy equals cotangent x dx. Now we'll antidifferentiate each side. The left side easily gives us 1/2 y squared, and for the right side we need to recall that cotangent x is the derivative of the natural log of the absolute value of sine x. So we have 1/2 y squared equals the natural log of the absolute value of sine x plus an arbitrary constant c. Now let's multiply through by 2 and write 2 times log of absolute value of sine x as the log of sine squared x, and subtract that from both sides and write the equation as y squared minus log of sine squared x equals c. This kind of implicit form of the solution, where the left side is a function of two variables and the right-hand side is constant, is often a good form in which to leave the solution because it allows one to think of the solution curves as the level curves on a surface. However, in this case, we may as well go ahead and solve for y, writing y equal to plus and minus the square root of the natural log of sine squared x plus c. This describes the family of orthogonal trajectories corresponding to the family c times cosine x. Here's a graph of the family given by c times cosine x. And now we'll add to the picture the family of orthogonal trajectories, which satisfy the equation y squared equals natural log of sine squared x plus c. Another example. Find the family of orthogonal trajectories corresponding to the family of hyperbolas x squared minus y squared equals c. In this case, implicit differentiation will produce the differential equation satisfied by these hyperbolas. Differentiating each side of the equation with respect to x gives us 2x minus 2 times y times the derivative of y with respect to x equals 0. And we solve for y prime and get y prime equal to x divided by y. So now we take the negative reciprocal of that expression and conclude that the orthogonal family satisfies y prime equals minus y divided by x. Let's take that equation and multiply through by dx and divide through by y to get the separated form of the equation dy over y equals minus dx over x. Now, antidifferentiating each side gives us the equation natural log of the absolute value of y equals minus the natural log of the absolute value of x plus c. Now let's add natural log of absolute value of x to both sides and rewrite the left side, which is log of absolute value of y plus log of absolute value of x, as log of the absolute value of x times y, a quantity that will be equal to a constant c precisely when the product xy is equal to a constant c. This is the equation of the corresponding family of orthogonal trajectories. Here's a picture of the original family of hyperbolas. Note that the lines y equals plus and minus x are asymptotes for all of these hyperbolas. The corresponding family of orthogonal trajectories is also a family of hyperbolas. Note that that family contains the familiar graphs of y equals plus and minus 1 over x, and that the entire family is identical to the original family of hyperbolas rotated through 45 degrees. The logistic equation is a fundamental equation used in the study of population dynamics. It is typically written in the form dy dt equal to k times y times 1 minus y divided by a constant m. Here the constants k and m are both positive, and m has the important interpretation of being a positive equilibrium solution of the equation. Indeed, notice that the equation has two constant solutions, y equals 0 and y equals m. Notice that when y is between 0 and m, the derivative dy dt will be positive, and so y is increasing. If y is greater than m, then the derivative is negative, and so y is decreasing. Also, the equation is separable, so we should be able to find the solutions. But before we try to solve the equation, let's make a change of variables that will end up making our job a little bit easier. Let's let u equal y divided by m. Then y is equal to m times u, and y prime is equal to m times u prime. So we put m times u prime in place of y prime on the left side of the equation, and replace y with m times u and y over m with u, and we have the new differential equation m times u prime equals k times m times u times 1 minus u. And dividing both sides by m gives us u prime equals ku times 1 minus u. Notice that this equation is exactly the same as the original equation in the case where m is equal to 1. Now let's separate variables. We divide by u times 1 minus u and multiply by dt, and we have du divided by u times 1 minus u equals k times dt. Now, in order to integrate the left-hand side, we need to do a partial fraction decomposition. That's fairly straightforward to do, and the result is that 1 over u times 1 minus u is equal to 1 over u plus 1 over 1 minus u. So the left side of the equation has become du over u plus du over 1 minus u. Next we antidifferentiate, and we get log of u minus the log of 1 minus u equals k times t plus an arbitrary constant c. Now, by omitting absolute values here inside the logarithms, we're essentially assuming for the moment that u is between 0 and 1. We'll see in a moment that that doesn't really make any difference. Now, the left-hand side is the same as the natural log of u divided by 1 minus u, and so if we raise e to each side of the equation, we have u over 1 minus u equals an arbitrary constant c times e to the kt. Now, if u and 1 minus u happen to have opposite signs, then the constant c here will simply be negative. Also, by evaluating both sides of this equation at t equals 0, we can tell that the constant c must equal the value of u at time 0 divided by 1 minus the value of u at 0. In other words, c is equal to u naught divided by 1 minus u naught, where u naught is u of 0. So now we have the equation 1 minus u over u equals 1 minus u naught over u naught times e to the minus kt. Now let's solve for u. First, notice that the left-hand side is the same as 1 over u minus 1. So we'll add 1 to both sides, and then take the reciprocal of both sides. And the result will be u equals 1 over 1 plus 1 minus u naught over u naught times e to the minus kt. And multiplying top and bottom of that fraction by u naught gives us u naught divided by u naught plus 1 minus u naught times e to the minus kt. So this is u. Now we go back to y, replacing u with y over m, and u naught with y naught over m, gives us y over m equal to y naught over m divided by y naught over m plus 1 minus y naught over m times e to the minus kt. And now we multiply top and bottom of that fraction by m, and we get y naught divided by y naught plus m minus y naught times e to the minus kt. And now finally multiplying both sides of the equation by m gives us y equal to y naught times m over the same denominator, y naught plus m minus y naught times e to the minus kt. Now notice that we can check the initial value here by plugging in t equals 0. When we do that, the right side of the equation here is y naught times m divided by y naught plus m minus y naught times 1, but that's just y naught times m over m, which is y naught. Also, the limit as t goes to infinity of this function will be y naught times m divided by y naught plus m minus y naught times the limit of e to the minus kt as t goes to infinity, which is 0. And so, unless y naught is 0, that limit is y naught over m divided by y naught, which is m. But notice that if y naught is negative, then the denominator will actually become 0 at some finite time t, And so negative solutions actually don't approach m as t goes to infinity, but all positive solutions do approach m as t goes to infinity. Here's a picture showing graphs of several non-negative solutions. Notice the constant solution y equals 0 and the constant solution y equals m. Torricelli's law. Suppose that we have a tank that contains some kind of fluid, and the fluid drains through a hole at the bottom of the tank. The rate at which the fluid flows through the hole is the rate of change in the volume of fluid in the tank, and that's dV dt. Let's also let y of t represent the depth of the fluid at time t, that is, the distance from the surface down to the hole. Now, Torricelli's law states that the derivative of the volume with respect to time is equal to minus a positive constant rho times the square root of y. In other words, the rate at which fluid flows through the hole at the bottom is proportional to the square root of the depth. The constant rho here can be expressed as a times b times the square root of 2g, where g is the gravitational constant, a is the cross-sectional area of the hole, and b is the so-called Borda constant, which has to do with characteristics of the hole as well as the viscosity of the fluid. Now the differential equation we have here, dV dt equals minus rho square root of y, is not exactly satisfactory because we have the derivative of the volume in terms of a different variable y, but because of the chain rule, we know that dV dt is equal to dV dy times dy dt. And we know from calculus that the derivative of the volume with respect to y is equal to the cross-sectional area at depth y. In other words, one could compute the volume by integrating the cross-sectional area from 0 to y. So combining these two facts tells us that dV dt is equal to the cross-sectional area A of y times dy dt. And so Torricelli's law becomes A of y times dy dt equals minus rho times the square root of y. This is a separable differential equation for the unknown y, and its separated form is A of y divided by the square root of y times dy equals minus rho dt. Now let's look at an example. A conical tank with height 2 meters and radius 1 meter is initially full of water and thereafter drains through a hole at its vertex. Assume that rho is equal to 0.5 with t in minutes. Find the depth of the water t minutes later, and find the time it takes for the tank to drain completely. The first thing we need to do is to get an expression for the cross-sectional area A of y, and since that cross-section is circular, we need to know its radius in terms of y. Now looking at the right half of the vertical central cross-section, we see that we have a couple of similar triangles, and by the principle of similar triangles, we know that r divided by y is the same as 1 divided by 2. So r is equal to y over 2, which then tells us that the cross-sectional area A of y is pi times the square of y over 2, or pi y squared over 4. Now the left side of our differential equation, A of y dy dt, is pi over 4 y squared dy dt, and that equals the right-hand side, which is minus 0.5 times the square root of y. Now, when we multiply both sides by 4 over pi, as well as dt, and divide both sides by the square root of y, we have on the left y to the 3/2 power dy, and on the right minus 2 over pi dt. And next we antidifferentiate each side, and on the left we have 2/5 times y to the 5/2 power, and on the right minus 2 over pi times t plus c. Multiplying through by 5/2 gives us y to the 5/2 power equals minus 5 over pi times t plus c. And now we use the initial condition that says that the tank is initially full. That's y of 0 equals 2, and that tells us that 2 to the 5/2 equals 0 plus c, or c equals 2 to the 5/2, which is 4 times the square root of 2. Now we use that value of c, and raise each side of our equation to the 2/5 power, and we have y equals the 2/5 power of 4 root 2 minus 5 over pi times t. Now it's easy to see that y becomes 0, that is, the tank becomes empty, at time t equal to 4 root 2 pi divided by 5, which is about 3.55 minutes. And so we should also make a statement about the domain of our solution. It is valid only for t between 0 and 4/5 square root of 2 times pi. Now here's the graph of that solution. What's interesting here is that the slope of the tangent line to the graph approaches negative infinity as t approaches the time when the tank becomes empty. This is a result of the fact that the exponent in the solution, 2/5, is between 0 and 1. So as the depth approaches 0, it decreases at a faster and faster rate. We can illustrate this by plotting the graph from left to right at a constant speed. We can describe what's happening as a kind of whoosh as the tank becomes empty. Direction fields and numerical approximation. Direction fields. A first-order differential equation, y prime equals f of x and y, tells us the following. Given any point x, y, where f of x, y is defined, a solution whose graph passes through x, y does so with slope f of x and y. In other words, the function f of x and y specifies a unique slope at each point x, y where it is defined. We can indicate the slope at each point in a chosen grid with a short arrow. The result is a picture of what we call the direction field or slope field of the differential equation. On the right here is a simple illustration. Notice how the grid of arrows allows you to draw a rough approximation to a solution curve through any given point. Shorter arrows on a finer grid make it easier to draw a more accurate curve. Some graphing calculators have the ability to plot slope fields or direction fields. If you have a TI-89 or a Voyage calculator, in it these are designated as slope fields. The term direction field is used in those calculators for a similar idea related to pairs of differential equations. The equation y prime equals cosine t minus sine y has this direction field for t between minus 1 and 8 and y between minus 4 and 4. Let's now plot the solution curve that satisfies the initial value y of 0 equals 2. Here's another solution curve for the solution satisfying y of 0 equals 2.5. And here's the solution satisfying y of 0 equals negative 1. Here's the solution with y of 0 equals negative 3. And here are a couple more solution curves to fill out the picture. Notice that all of these solution curves seem to be getting close to each other as t increases. In fact, here's another picture for the same equation where t goes from minus 1 to 12. Here we can clearly see that solutions with a variety of initial values all tend to approach the same curve as t increases. It's instructive to think a little bit about how we might sketch a direction field by hand in a reasonably efficient way. It is useful to sketch several isoclines first. Isoclines are curves along which slopes of solution curves are constant. That is, f of x and y equals a constant m. These are actually level curves of the two-variable function f. Along any single isocline f of x and y equals m, the arrows of our direction field will be parallel with slope m. For example, when f is independent of x, as in y prime equals y squared times 2 minus y, horizontal lines are isoclines. This is because the right-hand side of the differential equation is constant if and only if y is constant. For this equation, the slope along any horizontal line is m equal to y squared times 2 minus y. So for any given horizontal line, we can use that formula to compute the slope m. So on the line y equals 2, the slope of the direction field is always 0. So all the arrows there are horizontal. The same is true for the line y equals 0. Along the line y equals 1, m is equal to 1 squared times 2 minus 1, or 1, and so all the arrows along that line have slope 1. On the line y equals 4/3, m turns out to be roughly 1.2, so the arrows along that line are slightly steeper than the arrows on the line y equals 1. On the line y equals 5/3, m turns out to be approximately 0.9, and so we draw arrows that are slightly less steep than those on the line y equals 1. On the line y equals 2/3, m is approximately 0.6, and on the line y equals 1/3, m is roughly 0.2. Now let's just go ahead and fill out the rest of the direction field and use it to sketch a few solution curves. Of course, the easiest ones to sketch are the constant solutions y equals 0 and y equals 2. And here's the graph of a fairly typical solution whose values lie between 0 and 2. Now let's look at an example where the right-hand side of the differential equation involves both the independent and dependent variables. Let's look at y prime equals 1 minus x squared minus y squared. The isoclines in this case are the graphs of the equation 1 minus x squared minus y squared equals m for various values of m, which is equivalent to x squared plus y squared equals 1 minus m, where m must be less than or equal to 1, because the left-hand side of the equation can't be negative. Now this tells us that in our direction field, arrows on the circle centered at the origin, with radius r equal to the square root of 1 minus m, have slope m. By solving that radius for m, we can turn that around and say that arrows on the circle with radius r have slope m equal to 1 minus r squared. So now let's draw a few circles centered at the origin and attach a few arrows to each one with the appropriate slope. The innermost circle here has a radius between 0 and 1, and so the slope of arrows along that circle will be some number between 0 and 1. The next circle outward is the unit circle, and along it, the slope m is equal to 1 minus 1, or 0. The next circle has a radius of about 1.4, which is roughly the square root of 2, and so the slope associated with that circle will be roughly 1 minus 2, or negative 1. The radius of the outermost circle here is roughly the square root of 3, and so the slope ends up being roughly 1 minus 3, or negative 2. So now we have a good enough sampling of arrows to suggest what the direction field looks like overall. The most important feature of it is that arrows have positive slope inside the unit circle, zero slope on the unit circle, and negative slope outside the unit circle. So let's draw a few solution curves. First, let's draw the one that goes through the origin. Here are two more solution curves that cross the y-axis inside the unit circle. Here are two that cross the y-axis at the unit circle. Notice that since they're tangent to the unit circle there, they don't go inside of the circle. And finally, here are a couple of solution curves that cross the y-axis outside the unit circle. Euler's method. Suppose that we have an initial value problem, y prime equals f of t and y, with y of t naught equal to y naught. How might we approximate the value of the solution at a later time t1 equal to t naught plus h without solving the differential equation? The most basic way of doing this is to use a simple approximation to the derivative at time t naught that comes from the definition of the derivative. For small values of h, y prime at t naught is going to be approximately equal to y of t naught plus h minus y of t naught, all divided by h. And because of our differential equation, we can think of that as an approximation of f of t naught, y of t naught. Now, since we're given that y of t naught is y naught, let's go ahead and put that into this approximate formula. Let's now solve for y of t naught plus h. We get y of t naught plus h is approximately equal to y naught plus h times f of t naught y naught. This tells us that the value of the solution at time t0 plus h can be approximated by y0 plus h times f of t0 y0, something that can be computed knowing only the solution value at time t0. So this suggests the approximation of y of t1, or y of t0 plus h, by y1 equal to y0 plus h times f of t0 y0. So notice here that the symbol y sub 1 denotes an approximation to the exact value of the solution y of t1. Now here's a picture that illustrates what's happening. We know the solution value at time t0, and we'd like to approximate the solution value at time t1 equal to t0 plus h. We use the right-hand side of the differential equation to compute the slope of the solution at t0, and then take a value from the linear approximation at t0 as an approximation to the solution at time t1. Notice that the approximate point we obtain, t1, y1, is in the direction given by the direction field at t0, y0. Now let t1 equal t0 plus h, t2 equal t0 plus 2h, t3 equal t0 plus 3h, and so forth, and let y1, y2, y3, and so forth be approximations of y of t1, y of t2, y of t3, and so on, obtained from the formula y sub n plus 1 equals y sub n plus h times f of tn yn for n equal to 0, 1, 2, and so forth. This method of approximating values of the solution of the differential equation is known as Euler's method. Notice that when n is 0, this formula is the same as the one above, in which y1 is computed from y0. Then y2 is computed from y1, y3 is computed from y2, and so on. Now let's look at an example. Let's approximate the solution of y prime equal to t minus y squared with y of 0 equal to 3 at t equal to 0.1, 0.2, and so on up to 0.5 using Euler's method. The difference between successive t values here is 0.1, so that's our step size h. And since the function on the right side of the differential equation is f of t and y equal to t minus y squared, Euler's method takes the form y sub n plus 1 equals y sub n plus 0.01 times tn minus yn squared. Now let's display our calculations in a table. Let's keep track of n, t sub n, y sub n, as well as the slope at tn yn, which is tn minus yn squared. N equal to 0, 1, 2, up to 5 will take us from t0, which is 0, to t1, and so forth up to t5, which is 0.5. We're given that y0 is equal to 3, and so the slope at t0, y0 is 0 minus 3 squared, or minus 9. Next, we calculate y1. Using t0 and y0 in the formula gives us 3 plus 0.1 times minus 9, which is 2.1. Now we calculate the current slope for use in the next row. t1 minus y1 squared is 0.1 minus 2.1 squared, which is minus 4.31. Now, y2 is equal to 2.1 plus 0.1 times minus 4.31, and that equals 1.669 rounded to 3 decimal places. The slope at t2, y2 turns out to be minus 2.586, and so y3 is 1.669 plus 0.1 times minus 2.586, and that gives us 1.410. Continuing on this way, we calculate y4 to be 1.242, and then we find y5 is 1.127. Now here's a picture that shows the points that we've computed, along with the direction field for the differential equation in the background. And here's the solution curve that we're trying to approximate. Had we gone on to compute y6 through y10, this is what our approximate curve would have looked like. And here's what we would have had if we had gone on to compute approximations up to y30. Notice that the approximate curve started out badly, but ended up moving back closer to the actual solution. Now, this is certainly not something we can depend on in general, But in this case, it's not that surprising when you consider the fact that the direction field guides all solutions toward a single curve. A numerical method that is much more accurate than Euler's method is known as improved Euler. The idea here is to estimate the derivative by averaging estimates of the derivative at Tn and at Tn plus 1. The difference quotient y of Tn plus 1 minus y of Tn divided by h is an estimate of y prime at Tn, which equals f of Tn, y of Tn. That same difference quotient can be thought of as a backwards difference approximation to y prime of Tn plus 1, which equals f of Tn plus 1, y of Tn plus 1. Now, by averaging these two approximations and solving for Tn plus 1, we arrive at y of Tn plus 1 is approximately equal to y of Tn plus h over 2 times f of Tn y of Tn plus f of Tn plus 1 y of Tn plus 1. The difficulty with this approximate formula is that y of Tn plus 1 appears on both sides, so its use would require us to solve for y of Tn plus 1. But we can avoid that by approximating the y of Tn plus 1 on the right-hand side, and we do that using Euler's method. This leads to the following formula for computing y sub n plus 1 from y sub n. Y sub n plus h over 2 times f of Tn and yn plus f of Tn plus 1 and y sub n plus h times f of Tn yn. The expression in blue here is exactly the Euler's method approximation of y sub n plus 1. Now, a good way to arrange this computation is as follows. First, compute f of Tn and yn and call that number phi1. Next, compute f of Tn plus 1, yn plus h of phi1 and call that number phi2. Then, yn plus 1 is equal to yn plus h over 2 times phi1 plus phi2. Now let's think about what one step of this method does from a graphical point of view. Let's say we're computing y1 from y0. The number phi1 is the slope of the tangent line at t0. Phi2 is an approximation of the slope of the tangent line at t1. Now, when we average those slopes, we get a much better approximation to the slope of the secant line through those 2 points on the curve. So by adding h times the average of those slopes to y sub n, we get a good approximation to the y coordinate at the second point. Example. Approximate the solution of y prime equals t minus y squared with y of 0 equals 3 at t equal to 0.1, 0.2, and so on up to 0.5 using improved Euler. So let's see what the computation will look like for this particular example. The number phi1 will equal t sub n minus y sub n squared. Then phi2 will equal tn plus 1 minus the square of an approximation to y at tn plus 1, given by the regular Euler's method formula yn plus 0.1 times phi1. Then yn plus 1 will equal yn plus 0.1 times the average of phi1 and phi2. Now let's build a table to show the computations. This table is structured a little different from the table we used for the regular Euler's method. For each n, we'll keep track of the time tn, the numbers phi1 and phi2, as well as y sub n. We'll need to take 5 steps to get from time 0 to 0.5, and we'll go ahead and list those t values down the second column here. Now, we start off knowing that y sub 0 is equal to 3. The first computation we need to do is to compute phi1 for the second row. That will be t sub 0 minus y sub 0 squared, which is 0 minus 3 squared, or negative 9. Now, phi2 is t1 minus the square of y sub 0 plus 0.1 phi1, so that's 0.1 minus the square of 3 plus 0.1 times negative 9, which turns out to be minus 4.31. Now we can compute y1. It's y sub 0, or 3, plus h over 2, which is 0.05, times the sum of phi1 and phi2, negative 9 minus 4.31. This gives us y1 equal to 2.335 rounded to 3 decimal places. Next we go to n equal to 2 and t sub n equal to 0.2. Phi1 will be the previous time 0.1 minus the previous y squared, which is 2.335 squared, and that turns out to be minus 5.350. Next we compute Phi2 using the current time t2 or 0.2, from which we subtract the square of y1 plus h times Phi1. That turns out to be minus 3.038. Now finally we compute y2 by taking y1 plus 0.05 times Phi1 plus Phi2, and the result is y2 equals 1.915. Now continuing to the next row, we similarly compute a new Phi1 equal to minus 3.468, and then a new Phi2 equal to minus 2.160, and from those we compute y3 and get 1.634. The next two rows are filled out similarly, resulting in y4 equal to 1.438 and y5 equal to 1.299. Here's a plot showing the approximate points that we've computed. All of those lie quite close to the actual solution curve. In fact, much closer than the corresponding points we computed using regular Euler. Had we gone on to compute y6, y7 up to y10, the picture would look like this. And finally, here's what the picture would look like if we had continued on to compute up to y30. Existence and uniqueness. Existence of solutions. Let's start with a basic definition of what we mean by solution. A function y of x is a solution of the initial value problem y prime equals f of x and y with y of x naught equal to y naught on an interval I if I contains x naught and the following two things are true. First, y prime of x is equal to f of x and y of x at each x in the interval I. In other words, the differential equation is true at each point in I. And second, y of x naught must equal y naught. That is, the graph of y of x goes through the point x naught, y naught. So essentially, a solution of the differential equation is a function defined on an interval containing the initial point x naught, whose graph has slope determined by the differential equation at each point in the interval. Technically, the interval I here may be very small, although usually when we talk about a solution, the interval I is understood to be as wide as possible while still having the property that the differential equation is true at each point in it. Now, two fundamental questions are, A, is there an interval I on which the initial value problem has a solution? And B, can there be more than one solution on that interval I? The first of these questions concerns the existence of a solution. The second question concerns the uniqueness of such a solution. The existence question is about whether the initial value problem has at least one solution, and the uniqueness question is about whether the problem has at most one solution. Now let's illustrate how a solution can fail to be unique. Here's the graph of a solution of the differential equation through the point x naught, y naught. It's possible that there is another solution through x naught, y naught, but notice that the graphs must have the same slope at any common point. In particular, wherever they diverge from each other, they must be tangent to each other. In this particular picture, the two graphs split off from each other at the point x naught, y naught. This means that there is no interval containing x naught on which the differential equation has a unique solution, because no matter how much we shrink the interval down, there will always be two solution curves going through the same point x naught, y naught. On the other hand, a second solution may branch off at some point to the right of x naught, or to the left. In such a case, we may be able to establish that there is a unique solution to the initial value problem on a smaller interval containing x naught. This is just to emphasize the important role played by the interval with regard to these questions of existence and uniqueness. Now, we would like to have a theorem that tells us when we can expect existence and when we can expect uniqueness for a given initial value problem based on properties of the function f. In other words, we want a theorem that answers the following questions. How nice must f be for the answer to question A to be yes? And how nice must f be for the answer to B to be no? Here's an example of non-existence. Consider the initial value problem, x times y prime equals y, with y of 0 equal to 1. By separating variables and integrating, it's easy to show that the general solution is given by y equals a constant times x. Every member of this general solution must have the value 0 when x is 0. So the initial condition y of 0 equals 1 is impossible. Now let's go ahead and state our basic existence theorem and come back to this example to see what goes wrong. If the point x0, y0 is contained in an open region R on which f of x and y is a continuous function, then there is an open interval containing x0 on which the initial value problem y prime equals f of x and y with y of x0 equals y0 has a solution. So what's needed to reach the conclusion of the theorem is only the continuity of the two-variable function f on some open region in the plane containing the initial point. That region might be a rectangle as shown here, or it could be a disk, or the entire first quadrant, for instance, or any such open region. The requirement that the region be open is simply to guarantee that the point x0, y0 is strictly inside the region and not on its edge. So given such a region, we're guaranteed that the initial value problem has a solution on some possibly very small interval containing x0. We can reapply the theorem at any point in the region, and that allows us to conclude that the interval on which the solution exists can be extended at least until the graph of the solution reaches the edge of the region R. Now let's go back to the example at the top of the page. If we rearrange the equation so that it's in the form of y prime equals f of x and y, we have y prime equals y divided by x. So our function f of x and y is y divided by x, which is certainly not continuous at 0, 1, and so it's impossible to find a region R that satisfies the hypotheses of our existence theorem. To prove the preceding existence theorem requires some very technical knowledge from more advanced courses, but it is instructive here to look at the idea behind one proof of the theorem. Here's an example of a particular initial value problem, y prime equals cosine of t minus y, with y of 0 equals 2. And here's a picture of the direction field for the equation for x between minus 2 and 2 and y between 0 and 3.5. Now let's use Euler's method to approximate points along the graph of the solution. Here's what we get if we use a very large step size equal to 2. With a step size of 1, we have this picture. This is an extremely rough approximation that is likely of very little value, but if we cut the step size in half again, using a step size of 1/2, we get this picture, which begins to give us a rough idea of what the actual solution looks like. Now let's continue cutting the step size in half, using step size 1/4, then 1/8, then 1/16, and so on, obtaining better and better approximations to the exact solution over this interval. As the step size approaches 0, these approximate solutions become better and better, and so their limit is in fact the solution of the initial value problem. In general, this type of construction succeeds on a sufficiently small interval, provided that the right-hand side of the differential equation is continuous in a region containing the initial point. Thus we have the existence theorem stated previously. A corollary to our basic existence theorem is that if f of x and y is continuous everywhere in the plane, then the domain of any solution can be expanded until the graph of the solution has no endpoints. Then either the solution will be defined for all x, or its graph will have a vertical asymptote. Here's a picture of the direction field associated with a differential equation for which the right-hand side is continuous everywhere in the plane. The existence theorem tells us that there is a solution through any initial point and defined on some interval. Now if we take the initial point to be each of the endpoints of that arc, the existence theorem tells us that this solution can be extended over a wider interval. We can continue doing this, and in this case obtain a solution that's defined for all values of the independent variable. Here's the direction field for another differential equation for which the right-hand side is continuous everywhere in the plane. The existence theorem tells us that there is a solution through any given initial point, and using the endpoints of that arc as initial points, we can extend this solution to a wider interval, and we can continue doing this and obtain a solution whose graph has no endpoints. Now in this case, the interval on which that solution is defined does have an endpoint because the solution itself has a vertical asymptote. This curve is in fact the solution of the initial value problem y prime equals y squared with y of 0 equals 1. We can solve that equation by separating variables, and we find that the solution is y equals 1 over 1 minus x for x between minus infinity and 1. Uniqueness and non-uniqueness. There are two different uniqueness questions. The local uniqueness question is this: assuming that a differential equation has a solution whose graph passes through the point x0, y0, is there an open interval containing x0 on which no other solution exists? If the answer is yes, we say that the differential equation has a unique local solution through x0, y0. The global uniqueness question is this: is there exactly one solution curve of the differential equation passing through the point x0, y0? If the answer to this is yes, we simply say that the solution of the differential equation through x0, y0 is unique. We point out that it is possible for a differential equation to have multiple solutions passing through x0, y0 while having a unique local solution through that point. Here's a fairly simple example. Consider the equation y prime equals 3x times the cube root of y, with initial value y of 0 equals 0. It's easy to see from the equation itself that one solution is y of x equals 0 for all x, in other words, the trivial solution. On the other hand, if we separate variables and integrate, we obtain solutions y equal to plus or minus x cubed. So right away, there are at least three solutions of this initial value problem. And not only that, those solutions are distinct on any interval containing 0. Therefore, no solution through 0, 0 is unique. We actually have 9 solution curves in this picture, not just 3. Each of those is obtained by taking one of the 3 solution curves to the left of the origin and one of the 3 solution curves to the right of the origin and piecing those together. It turns out that there are lots of other solutions as well, as shown here. Now let's change the initial condition to y of minus 1 equals 1. There is no constant solution of this equation, but separating variables and integrating leads to the solution y equals minus x cubed. It turns out, and the direction field makes this fairly clear, that that solution is in fact locally unique. However, when we expand the interval on which it's defined, we eventually get to the origin, and we've just seen that the differential equation has multiple solutions through the origin. In fact, our solution could be continued past the origin as minus x cubed, or as plus x cubed, or we could even continue it as y equals 0 for all positive x. In fact, there are many other possibilities where we follow the 0 solution up to some positive x before branching off. In conclusion, the solution y equals minus x cubed is unique locally, but not globally. Examples of non-uniqueness. We'll begin with a one-parameter family of functions whose members all intersect at a given point. So consider the one-parameter family y equal to 0 if x is less than or equal to a constant c, and the cube of x minus c divided by 3 if x is greater than c. For instance, this is what the graph looks like when c is 2.
This illustrates the functions in the family corresponding to c greater than or equal to 0. Notice that the initial condition y of 0 equals 0 is true for all c greater than or equal to 0. In other words, all of the curves in the picture intersect at the origin. Now let's find the first-order differential equation associated with this one-parameter family. By differentiating each piece of the function, we find that y prime is equal to 0 if x is less than or equal to c, and the square of x minus c divided by 3 if x is greater than c. Note in particular that y is differentiable at x equals 0 because the two pieces of the function join together smoothly. So now it's easy to see that if we cube y prime, we get the same thing as when we square y. This gives us the differential equation y prime equals y to the 2/3 power. So for any c greater than or equal to 0, y satisfies the initial value problem y prime equals y to the 2/3 power with y of 0 equals 0. This is a rather innocent-looking problem that turns out to have infinitely many solutions. Here's another example. Again, we'll begin with a one-parameter family and derive the differential equation associated with it. Let y equal 0 if x is less than or equal to c, 1 minus cosine of x minus c if x is between c and c plus pi, and 2 if x is greater than c plus pi. Here's the graph of y when c is equal to 0. The dashed curve there is the graph of 1 minus cosine x, which this function equals between 0 and pi. This picture shows several curves corresponding to values of c greater than or equal to 0. These are simple horizontal shifts of the function corresponding to c equals 0. So notice that the initial condition y of 0 equals 0 is true for all c greater than or equal to 0. Now, these are the curves corresponding to c less than or equal to negative pi. All of these satisfy the initial condition y of 0 equals 2. Now let's compute y prime. It's equal to 0 if x is less than or equal to c, sine of x minus c if x is between c and c plus pi, and it's equal to 0 again if x is greater than c plus pi. Now, because y involves cosine and y prime involves sine, let's look at the sum of the squares of y prime and y. The key here is what happens to the middle piece of each of those functions. We get sine squared of x minus c from y prime squared, and we get 1 minus 2 times cosine x minus c plus cosine squared x minus c from y squared. Since sine squared plus cosine squared is equal to 1, that ends up being 2 minus 2 times cosine x minus c. So y prime squared plus y squared is equal to 0 if x is less than or equal to c, 2 minus 2 times cosine x minus c if x is between c and c plus pi, and 2 squared, or 4, if x is greater than c plus pi. All of that is the same thing as 2 times y. Now we solve for y prime and conclude that for any c, y satisfies the differential equation y prime equals the square root of 2y minus y squared, or the square root of y times 2 minus y. Thus, this differential equation has infinitely many solutions, passing through either 0, 0 or 0, 2. Now, what is it that the two preceding examples have in common? We saw in the first example that the initial value problem y prime equals y to the 2/3 with y of 0 equals 0 had infinitely many solutions. And in the second example, we saw that y prime equal to the square root of y times 2 minus y with y of 0 equals 0 or 2 also has infinitely many solutions. What these problems have in common has something to do with the partial derivative with respect to y of the function f on the right-hand side of the differential equations. The partial with respect to y of y to the 2/3 power is 2/3 times y to the minus 1/3 power, or 2 over 3 times the cube root of y, and the partial with respect to y of the square root of y times 2 minus y turns out to be 1 minus y divided by the square root of y times 2 minus y. Notice that the first of these is undefined at y equal to 0. In other words, it's undefined at the initial point in the initial value problem. And in the second example, the partial of f with respect to y is undefined at 0 and at 2, which means it's undefined at the initial point 0, 0, as well as at 0, 2. So in both cases, the right-hand side of the differential equation is not differentiable with respect to y at the initial point, and its partial with respect to y is unbounded on every region containing the initial point. Now it turns out that an initial value problem cannot have multiple solutions through a given initial point unless that is true. This is basically the gist of the following local existence and uniqueness theorem. If x0, y0 is contained in an open region R on which both f of x and y and the partial of f with respect to y are continuous, then there is an interval containing x0 on which the initial value problem y prime equals f of x and y with y of x0 equals y0 has exactly one solution. Here's an important corollary to that theorem. If f of x and y and the partial derivative of f with respect to y are continuous on an open region R, then there is a solution curve of y prime equals f of x and y through every point in R, and no two solution curves ever intersect in R. Note that saying that no two solution curves ever intersect in the region is the same as saying that there's a unique solution through every point in the region. Now let's look at a nice equation to illustrate the importance of this corollary. Y prime equals y to the 4/3 times 2 minus y. Here's the equation's direction field. Now let's see why this is supposed to be a nice equation. Clearly the right-hand side is continuous everywhere, and its partial derivative with respect to y turns out to be 1/3 of 8 times y to the 1/3 minus 7 times y to the 4/3. Or, factoring out y to the 1/3, 1/3 times y to the 1/3 times 8 minus 7y. This function is also continuous everywhere. So the region R in the corollary may be taken to be the entire xy plane. So the equation has a solution through every point in the plane, and no two solution curves ever intersect. Now, since we know this, we can confidently draw a number of solution curves over the direction field. Notice in particular that because of the constant solutions y equals 0 and y equals 2, any solution curve between y equals 0 and y equals 2 must remain between y equals 0 and y equals 2 for all x. Otherwise, we would have intersecting solution curves, which we know doesn't happen because of uniqueness. Now let's look at one final example where we start with a differential equation that has multiple solutions through certain points and try to find all of its solutions. Let's describe all the global solutions of y prime equal to 3/2 times y to the 1/3. Now by global solution we mean a solution defined for all values of the independent variable. Here the right-hand side of the equation is continuous everywhere, but its partial with respect to y ends up being undefined whenever y is 0, or in other words, along the horizontal axis. For a problem such as this, it's always a good idea to look at the direction field of the differential equation to get an idea for what kind of thing is possible. Now let's note that the equation has the trivial solution y of t equal to 0 for all t. Next, let's see what kind of general solution we find by separating variables. The separated equation can be written as 2/3 times dy over y to the 1/3 equals dt. Anti-differentiating the left side gives us y to the plus 2/3 power, and anti-differentiating the right side gives us t, to which we add a constant c. Now, solving for y, we get plus or minus t plus c to the 3/2 power, which only makes sense for t greater than or equal to minus c. Notice that minus c is important here because it's the value of t where y is equal to 0. In other words, it's the value of t where the solution intersects the trivial solution. So let's rewrite the solution with t0 equal to minus c. We have y equals plus or minus t0 to the 3/2 power for all t greater than or equal to t0. For t0 equal to 0, the graphs of these two functions look like this. Now let's add to the picture several other curves obtained with several other values of t0. Now, except for the trivial solution, none of these solutions is global. We can get global solutions as follows. For any given t0, we simply let the solution equal 0 for all t less than t0. And then for t greater than t0, we let the solution equal either plus or minus the 3/2 power of t minus t0. A typical solution obtained in this way has a graph that looks like this. So for any t0, we have two global solutions given by y equal to plus and minus 0 if t is less than t0, and t minus t0 to the 3/2 power if t is greater than or equal to t0. We need to be a little bit careful here about what's happening at t0. A solution must be differentiable there, and it's fairly straightforward to show that that is in fact the case. Now, finally, we'd like to include the trivial solution among this family of solutions. One way to do that is to simply allow t0 to be plus infinity, noting that the first part of this piecewise defined function then reads y equal to 0 for all t less than infinity, and the second part of the function never comes into play. Note that the direction field makes it clear that this family includes all of the global solutions of the differential equation. Linear second-order equations 1. Fundamentals. We begin here a study of linear second-order equations, which we express generically as y double prime plus p times y prime plus qy equals f, where p, q, and f are given continuous functions on an interval I, which are possibly constant functions. When the function f on the right-hand side is 0, the equation is said to be homogeneous. We refer to the functions p and q as coefficients, and the function f is called the forcing function or non-homogeneous term. This type of equation arises in the study of a simple spring mass system. Letting y denote the displacement from equilibrium of a mass m attached to a spring whose other end is fixed, Newton's second law tells us that mass times acceleration, or m times y double prime, is equal to the sum of the horizontal forces on the mass. Assuming Hooke's law is in effect, the force exerted by the spring on the mass is equal to minus a positive constant k times y. The constant k is called the stiffness of the spring. Friction is typically assumed to be proportional to velocity, so we write that force as minus a positive constant r times y prime. There may also be external forces acting on the mass, such as a force due to a magnetic field. Let's let capital F denote all of the external forces. Now, rearranging this equation gives us m times y double prime plus r times y prime plus k times y equals capital F. This is a linear second-order equation that's non-homogeneous if f isn't 0, and each term in it has units of force. If we divide through by m, we have y double prime plus py prime plus qy equals a little f, where p is r divided by m and q is k divided by m. Little f, of course, is 1 over m times big F. In this form, every term in the equation has units of acceleration. The point here is that linear second-order equations often arise from application of Newton's second law. Existence and uniqueness. Initial value problems associated with linear second-order equations have the form y double prime plus py prime plus qy equals f, along with initial conditions of the form y of a equals b and y prime of a equals m, where a is some number in the interval I on which p, q, and f are assumed to be continuous. Note that initial conditions specify both the value and the slope of the solution at a given point in I. The conditions for existence and uniqueness of a solution of such a problem have already been assumed. That is, the continuity of the functions p, q, and f. In fact, we have the following theorem. If p, q, and f are continuous on an interval I, then for any number a and I, and any numbers b and m, there exists a unique function y on the interval I that satisfies the initial value problem. This is actually a special case of a theorem for second-order equations that's similar to our existence and uniqueness theorem for first-order equations. That theorem concerns second-order equations y double prime equals capital F of t, y, and y prime, which in the linear case is simply little f minus q times y minus p times y prime. The theorem basically says that we can expect a unique solution of the differential equation provided that the right-hand side, as well as its partial derivatives with respect to y and y prime, are continuous. In the linear case here, the partial of big F with respect to y is just minus q, and the partial of big F with respect to y prime is minus p, and we assume that those functions are continuous, at least on an interval I, containing the point at which initial values are specified. General solution. A two-parameter family of solutions to y double prime plus py prime plus qy equals f is a general solution if for any a in the interval I and any numbers b and m, it contains a unique member satisfying the initial conditions y of a equals b and y prime of a equals m. In other words, a two-parameter family is a general solution if it contains a function satisfying any initial conditions we care to specify at any number in I. Now here's a very simple but very important theorem. All general solutions are equivalent, since any general solution contains every solution of the differential equation. Now here's the proof of the theorem. Let U be any solution and let A be any number in I. Now consider the initial value problem y double prime plus py prime plus qy equals f with initial conditions y of a equals u of a and y prime of a equals u prime of a. By definition, every general solution contains the solution of this initial value problem, which is u. Therefore, u is a member of any general solution. Now let's focus on the homogeneous case, the equation y double prime plus py prime plus qy equals 0. We begin with a few observations. If y is a solution, so is c times y for any constant c. Note that with c equal to 0, this says that y equals 0 is a solution, something we can also see by inspection. Also, if y1 and y2 are solutions, then so is y1 plus y2. In other words, the sum of any two solutions is also a solution. And as a consequence of the first two observations, if y1 and y2 are solutions, then so is c1 y1 plus c2 y2 for any constants c1 and c2. In other words, if y1 and y2 are solutions, so is any linear combination of y1 and y2. Now let's look at a few simple cases that we can solve by inspection. We put solve in quotes here because we need to know a little bit more to ensure that we're actually getting all of the solutions. The equation y double prime minus y equals 0 has solutions y equals e to the x as well as y equals e to the minus x. Consequently, any linear combination of those functions is a solution, and so y equals c1 e to the x plus c2 e to the minus x gives us what will turn out to be the general solution of that equation. A somewhat more general version of the same equation is y double prime minus k squared y equals 0, where k is constant. Here, two simple solutions are e to the kx and e to the minus kx, And so y equals c1 e to the kx plus c2 e to the minus kx is a solution for any constants c1 and c2. The equation y double prime plus y equals 0 is satisfied by cosine x and sine x. So y equal to c1 cosine x plus c2 sine x is a solution for any c1 and c2. And now a slightly more general version of that equation is y double prime plus k squared y equals 0, where k is constant. Here, two simple solutions are cosine kx and sine kx. And so y equals c1 cosine kx plus c2 sine kx is also a solution for any constants c1 and c2. The big question now is this. Given solutions y1 and y2, under what circumstances will the two-parameter family c1 y1 plus c2 y2 be the general solution of the differential equation? In other words, given solutions y1 and y2, under what circumstances are we guaranteed that, given any a in the interval I and any numbers b and m, we can find c1 and c2 such that c1 y1 plus c2 y2 satisfies the initial conditions y of a equals b and y prime of a equals m? Certainly a necessary condition is that neither y1 nor y2 is a constant multiple of the other, since in that case the two-parameter family c1 y1 plus c2 y2 reduces to a one-parameter family. That is, if y2 equals c times y1, where c is constant, then c1 y1 plus c2 y2 is equal to c1 plus c2c times y1, which is just a constant times y1. And we don't expect to be able to satisfy two initial conditions when we've only got one constant to choose. The condition that neither y1 nor y2 is a constant multiple of the other is called linear independence. Note that this condition excludes the trivial solution, since 0 is a constant multiple of any other function. So our question now becomes, is the linear independence of y1 and y2 a sufficient condition for y equal to c1 y1 plus c2 y2 to be the general solution of the differential equation? It turns out that the answer is yes. The proof of this relies on two facts about linear algebraic equations. Suppose we have two equations in unknowns x and y, ax plus by equals u, and cx plus dy equals v, where a, b, c, d, and u and v are given numbers. That system of equations may be written in matrix vector form as follows. The 2 by 2 matrix with the coefficients a, b, c, and d times a vector containing the unknowns x and y equals a vector containing the right-hand sides of the equations u and v. This problem has a unique solution if and only if AD minus BC is not equal to 0. The quantity AD minus BC is called the determinant of the coefficient matrix. In the event that the determinant is 0, the system of equations may have no solution, or it may have infinitely many solutions. In the homogeneous case, that is, when the right-hand side of each equation is 0, and the matrix vector equation looks like matrix ABCD times the vector of unknowns x and y equals the 0 vector, the system of equations always has the trivial solution x equals y equals 0. That trivial solution will be unique if and only if the determinant is non-zero, and so a non-trivial solution exists if and only if AD minus BC equals 0. In fact, there would be infinitely many non-trivial solutions in that case. We're now ready to prove that if y1 and y2 are linearly independent, then c1 y1 plus c2 y2 is the general solution of our differential equation. So suppose that y1 and y2 are linearly independent solutions. In order to find c1 and c2 so that y equals c1 y1 plus c2 y2 satisfies initial conditions y of a equals b and y prime of a equals m, we need to solve the equations c1 y1 of a plus c2 y2 of a equals b and c1 y1 prime of a plus c2 y2 prime of a equals m for the unknowns c1 and c2. Putting this in matrix form, we have a coefficient matrix with entries y1 of a, y2 of a, and in the second row, y1 prime of a and y2 prime of a. The vector of unknowns contains c1 and c2, and the right-hand side vector has entries b and m. It follows that a unique solution for c1 and c2 exists if and only if the determinant of the coefficient matrix is not 0, that is, y1 of a times y2 prime of a minus y1 prime of a times y2 of a is not 0. Now, if this determinant were 0, there would be a solution of the homogeneous problem consisting of our coefficient matrix times c1, c2 equals 0, 0, with c1 and c2 not both 0. And with that choice of c1 and c2, the function c1 y1 plus c2 y2 would satisfy 0 initial conditions, y of a equals y prime of a equals 0, which, by uniqueness, only the trivial solution can do. This implies that c1 y1 plus c2 y2 is 0 on the entire interval I, which implies that y1 and y2 are not linearly independent. Since we assume that y1 and y2 are linearly independent, we can conclude that y1 of a times y2 prime of a minus y1 prime of a times y2 of a is not 0. Therefore, there are constants c1 and c2 for which c1 y1 plus c2 y2 satisfies y of a equals b and y prime of a equals m. Therefore, that is the general solution of the differential equation. And this is the end of the proof. Now let's state the result as a theorem. Given any pair of linearly independent solutions, y1 and y2, of the equation y double prime plus py prime plus qy equals 0, the general solution consists of all linear combinations of y1 and y2. Y equals c1 y1 plus c2 y2. Here's a simple example. For the equation y double prime plus y equals 0, we know we have solutions cosine t and sine t. Those solutions are linearly independent on the entire real line, and so the general solution of the differential equation is y equals c1 cosine t plus c2 sine t. So not only is that linear combination a solution for any c1 and c2, it represents all the solutions of the differential equation. You may have noticed that the crucial ingredient in the preceding argument is the function y1 times y2 prime minus y1 prime times y2, which is called the Wronskian of y1 and y2 and denoted by capital W. Notice that the dependence upon y1 and y2 is indicated here, but the end result is a function of the independent variable. Now here are a couple of examples. The Wronskian of cosine t and sine t is a function of t equal to cosine t times the derivative of sine t, which is cosine t, minus the derivative of cosine t, which is minus sine t, times sine t. This is cosine squared t plus sine squared t, which is equal to 1 for all t. The Wronskian of e to the minus x and e to the x is a function of x equal to e to the minus x times the derivative of e to the x minus the derivative of e to the minus x, which is minus e to the minus x, times e to the x. This is equal to 1 plus 1, or 2, for all t. We're now going to state a theorem that lists a few of the important properties of the Wronskian of a pair of solutions of a second-order linear homogeneous differential equation. Suppose that y1 and y2 are solutions of y double prime plus p times y prime plus q times y equals 0, and let capital W denote the Wronskian of y1 and y2. Then, W satisfies the first-order differential equation W prime equals minus P times W. Consequently, W is equal to some constant capital C times E raised to the negative of some antiderivative of P. Now, if that constant C is 0, then W is equal to 0 for all x in the interval I on which P and Q are continuous. And if that constant C is not 0, then W is never 0 on the interval I. In particular, W of x is not 0 for all x in the interval I when y1 and y2 are linearly independent, and W of x is equal to 0 for all x in I when y1 and y2 are linearly dependent. Now let's go back to the two basic examples above. The functions cosine t and sine t satisfy y double prime plus y equals 0, and the functions e to the minus x and e to the x satisfy y double prime minus y equals 0. Now in each of those equations, the coefficient p of the y prime term is 0, and consequently part 2 of this theorem says that the Wronskian has to equal a constant times e to the 0, and so W is constant. So the constant Wronskian that we observed in each of those examples would also be observed for any pair of solutions of any second-order linear homogeneous equation in which the y prime term is missing. Here's an example of a second-order linear homogeneous equation in which the coefficients p and q depend on t. Y double prime minus 1 over t times y prime plus 1 over t squared times y equals 0. The coefficients here fail to be continuous on any interval that contains 0. So let's take our interval I to be the open interval from 0 to infinity. By part 1 of the previous theorem, for any pair of solutions of this equation, the Wronskian will satisfy W prime equals 1 over t times W. Solving that separable equation tells us that the Wronskian is equal to a constant times t. Now it turns out that two solutions of the differential equation are given by y1 equal to t and y2 equal to t times log t. Now let's compute their Wronskian. It will be t times the derivative of t log t, which is log t plus t times 1 over t, minus the derivative of t, which is 1, times t log t. All of this simplifies and gives us t, which is indeed a constant times t, and let's note that that function is non-zero on our interval I. Therefore, y1 and y2 are indeed linearly independent on I, and the general solution of the differential equation is y equal to c1t plus c2t log t, or factoring out t, c1 plus c2 log t times t. Here's another example. Y double prime plus 2t divided by 1 plus t squared all times y prime minus 2 divided by 1 plus t squared times y equals 0. Here, the coefficients of y prime and y are continuous for all t, and so we take our interval I to be the entire real number line. By the first part of the previous theorem, the Wronskian of any pair of solutions will satisfy the differential equation W prime equals minus 2t divided by 1 plus t squared times W. Solving that separable differential equation tells us that the Wronskian will end up being a constant times 1 over 1 plus t squared. Now it turns out that two specific solutions of this equation are y1 equal to t and y2 equal to 1 plus t times the inverse tangent of t. Their Wronskian is equal to t times the derivative of 1 plus t times inverse tangent of t, which is inverse tangent t plus t times 1 over 1 plus t squared, minus the derivative of t times 1 plus t times the inverse tangent of t. And all of that simplifies to 1 over 1 plus t squared, which is never 0. Therefore, y1 and y2 are in fact linearly independent on the entire real number line, and so the general solution of the differential equation is c1t plus c2 times 1 plus t times inverse tangent t. Now let's finish up here by stating a theorem that summarizes everything we've seen. Let y1 and y2 be solutions of y double prime plus py prime plus qy equal to 0 on an interval I where p and q are continuous, and let w be the Wronskian of y1 and y2. Then the following are equivalent. That is, if any one statement is true, then so are all the others. 1. y1 and y2 are linearly independent on I. 2. W of x is not 0 for all x in I. 3. W of x is not 0 for some x in I. And 4. The general solution of the differential equation is given by y equal to c1 y1 plus c2 y2. Linear second-order equations 2. Homogeneous equations with constant coefficients. We're going to learn how to solve equations of the form y double prime plus py prime plus qy equals 0 in all cases where p and q are constants. Recall that the general solution consists of all linear combinations y equal to c1 y1 plus c2 y2 of any two linearly independent solutions y1 and y2. The key here is to look for solutions of the form y equal to e to the r times x, where r is a constant. This is a sensible thing to do because differentiating such a function simply produces constant multiples of itself. In fact, if y equals e to the rx, then y prime equals r times e to the rx, and y double prime will equal r squared e to the rx. Substituting these expressions into the left side of the differential equation gives us y double prime plus py prime plus qy equal to r squared e to the rx plus p times r times e to the rx plus q times e to the rx. And note that we can factor out e to the rx, revealing that the other factor is r squared plus p times r plus q. So we conclude that y equals e to the rx is a solution of the differential equation if and only if r is a solution of the quadratic equation r squared plus pr plus q equals 0. This quadratic equation is called the characteristic equation of the differential equation. The left-hand side is sometimes called the characteristic polynomial, and we sometimes call the solutions of the characteristic equation the characteristic roots of the differential equation. Here's an example. Let's find the general solution of y double prime plus 5y prime plus 6y equals 0. We begin by writing down the characteristic equation. It's r squared plus 5r plus 6 equals 0. The left-hand side factors into r plus 2 times r plus 3, and so the solutions of the characteristic equation, that is, the characteristic roots, are negative 2 and negative 3. This tells us that the differential equation has solutions e to the minus 2x and e to the minus 3x. Since these are linearly independent, the general solution of the differential equation consists of all linear combinations of them, y equals c1 e to the minus 2x plus c2 e to the minus 3x. We can check linear independence with the Wronskian. The Wronskian of e to the minus 2x and e to the minus 3x turns out to be e to the minus 2x times minus 3 times e to the minus 3x minus minus 2 times e to the minus 2x times e to the minus 3x, which equals minus e to the minus 5x, and notice that that is never 0. It turns out that two solutions obtained in this way from distinct roots of the characteristic equation will always be linearly independent. In general, the solutions of the characteristic equation r squared plus pr plus q equals 0 are given by the quadratic formula as follows. R1 and R2 equal to 1/2 of minus p plus and minus the square root of p squared minus 4q, which we can rewrite as minus p over 2 plus and minus the square root of p squared over 4 minus q. Now let's observe that there are three cases with regard to the nature of these roots. R1 and R2 are real and distinct when p squared is greater than 4q, that is, when the quantity under the radical is positive. They are real and repeated when p squared equals 4q, that is, when the quantity under the radical is 0, and the roots are complex conjugates when p squared is less than 4q, resulting in a negative number under the radical. Now in the first case, our problem is completely solved, just as in the previous example. We'll state the result as part 1 of a theorem. If the characteristic equation r squared plus pr plus q equals 0 has two distinct real solutions r1 and r2, then the general solution of the differential equation y double prime plus py prime plus qy equals 0 is y equal to c1 e to the r1x plus c2 e to the r2x. So what happens in cases 2 and 3? To help us answer that question, let's state a useful result as a lemma. Every solution of y double prime plus py prime plus qy equals 0 is of the form y equals u of x times e to the minus px over 2, where u satisfies the differential equation u double prime minus p squared over 4 minus q times u equals 0. Now let's notice that there are two important coefficients in this statement, and they are both important elements in the formula for the characteristic roots. These are minus p over 2 and p squared over 4 minus q. Minus p over 2 is going to be the real part of r1 and r2 in the case where the roots happen to be complex, and p squared over 4 minus q is the quantity under the radical whose sign determines which case we're in. Now let's go through the derivation of this result. Let y equal u of x times e to the minus px over 2. When we compute y prime with the product rule, both terms will have e to the minus px over 2 as a factor. The first term will be u prime times e to the minus px over 2, and the second term will be minus p over 2 times u times e to the minus px over 2. Next, we again use the product rule to compute y double prime. The first term will be u double prime minus p u prime over 2 times e to the minus px over 2. And the second term will be the derivative of e to the minus px over 2, which is minus p over 2 times e to the minus px over 2, times u prime minus pu over 2, which ends up giving us minus p times u prime over 2 plus p squared times u over 4 times e to the minus px over 2. This first factor simplifies to u double prime minus pu prime plus p squared times u over 4. Now let's look at y double prime plus py prime plus qy. There will be an e to the minus px over 2 factor throughout, and to form the other factor, we note that y double prime contributes u double prime minus pu prime plus p squared u over 4. P times y prime contributes p times u prime minus pu over 2, and q times y contributes simply q times u. Now notice that the u prime terms in that factor add up to 0, and so the factor becomes u double prime minus p squared over 4 minus q all times u. Now, e to the minus px over 2 can't be 0, and so that first factor must be 0. In other words, y double prime plus py prime plus qy will equal 0 if and only if u double prime minus p squared over 4 minus q times u equals 0. Now let's consider case 2, the double root case. Here, r1 and r2 are both equal to minus p over 2, since p squared over 4 minus q is equal to 0. Now, according to the lemma, u of x times e to the minus px over 2 will be a solution if u of x satisfies u double prime equals 0, which has linearly independent solutions 1 and x. U equals 1 gives us the solution e to the minus px over 2, which we already knew we had, and u equals x gives us a second solution, x times e to the minus px over 2. A straightforward computation of the Wronskian would tell us that, in fact, these are linearly independent solutions on any interval. We can now state part 2 of our theorem. If the characteristic equation r squared plus pr plus q equals 0 has a repeated real solution, r1 equal to r2 equal to minus p over 2, then the general solution of y double prime plus py prime plus qy equals 0 is y equals c1 times e to the minus px over 2 plus c2 times x times e to the minus px over 2, which equals c1 plus c2x times e to the minus px over 2. Now here's an example to illustrate this case. Let's find the general solution of y double prime plus y prime plus 1/4 y equals 0. The characteristic polynomial is r squared plus r plus 1/4, which factors into r plus 1/2 squared, and that has the double root minus 1/2. So we have solutions y1 equals e to the minus x over 2, and y2 equals x times e to the minus x over 2. And so the general solution of the differential equation is y equal to c1 plus c2x times e to the minus x over 2. Now let's look at case 3, where p squared over 4 minus q is less than 0. So the roots of the characteristic equation are complex conjugates, minus p over 2 plus and minus I times the square root of q minus p squared over 4. Note that the quantity under the radical has been negated, producing the factor I outside the radical. Now let's set alpha equal to minus p over 2 and beta equal to the square root of q minus p squared over 4, so that those roots are alpha plus and minus beta I. In other words, alpha is the real part of both roots, and plus and minus beta are the imaginary parts. By the lemma, the product u of x times e to the alpha x will be a solution provided that u of x satisfies u double prime plus beta squared u equals 0. Note that beta squared is equal to q minus p squared over 4. Now we can simply observe that u1 equal to cosine beta x and u2 equal to sine beta x are solutions. Therefore, a pair of solutions to y double prime plus py prime plus qy equals 0 are y1 equal to e to the alpha x times cosine beta x, and y2 equals e to the alpha x times sine beta x. And these solutions are indeed linearly independent on any interval. So we can now go ahead and state the third and final part of our theorem. If the characteristic equation r squared plus pr plus q equals 0 has complex conjugate roots alpha plus and minus I times beta, then the general solution of y double prime plus py prime plus qy equals 0 is given by y equal to e to the alpha x times c1 cosine beta x plus c2 sine beta x. Notice the specific role of the real and imaginary parts of the roots. The real part alpha determines the exponential growth or decay rate. The imaginary part beta determines the frequency or the period of the trigonometric factor. Here's an example. Find the general solution of y double prime plus 4y prime plus 5y equals 0. The characteristic equation is r squared plus 4r plus 5 equals 0. And using the quadratic formula, we find that the characteristic roots are minus 4 plus and minus the square root of 16 minus 20, all divided by 2. The square root of negative 4 is 2 times I, so we have minus 4 plus and minus 2i all divided by 2, or minus 2 plus and minus I. The real part, alpha, is minus 2, and the imaginary parts are plus and minus 1, and so beta equals 1. Therefore, our general solution is y equal to e to the minus 2x times c1 cosine x plus c2 sine x. Here's an example. Solve the initial value problem y double prime plus 2y prime plus 10y equals 0 with initial conditions y of 0 equals 1 and y prime of 0 equals 0. We first need to find the general solution of the differential equation, so let's write down the characteristic equation r squared plus 2r plus 10 equals 0. The quadratic formula tells us that the roots are minus 2 plus and minus the square root of 4 minus 40 all divided by 2, which is minus 2 plus and minus 6i divided by 2, which turns into minus 1 plus and minus 3i. These have real part alpha equal to minus 1, and the imaginary parts are plus and minus beta, where beta is 3. So our general solution is y equal to e to the minus x times c1 times cosine 3x plus c2 times sine 3x. Now we'll use the initial conditions to find c1 and c2. We'll need y prime, so let's go ahead and compute that. Using the product rule, we get y prime equals minus e to the minus x times c1 cosine 3x plus c2 sine 3x plus e to the minus x times minus 3 c1 sine 3x plus 3 c2 cosine 3x. Collecting cosine and sine terms, we have minus e to the minus x times c1 minus 3c2 times cosine 3x plus 3c1 plus c2 times sine 3x. Now, the initial condition y of 0 equals 1 tells us that c1 times 1 plus c2 times 0 is equal to 1. Thus, c1 is equal to 1. The condition y of 0 equals 0 tells us that c1 minus 3c2 times 1 plus 3c1 plus c2 times 0 equals 0, and since c1 is 1, we see that c2 is equal to 1/3. So now we have our solution, y equals e to the minus x times cosine 3x plus 1/3 of sine 3x. Now let's finish with a summary of what we've learned. For the homogeneous differential equation y double prime plus py prime plus qy equals 0, with p and q constants, there is an associated characteristic equation r squared plus pr plus q equals 0, whose roots we denote by r1 and r2. These characteristic roots may be real and distinct, they may be real and equal or repeated, or they may be complex conjugates. Note that the common value alpha in the repeated root case, as well as the real part alpha of both roots in the complex conjugate case, is equal to minus p over 2. When the characteristic roots are real and distinct, the general solution of the differential equation is y equal to c1 e to the r1x plus c2 e to the r2x. In the repeated root case, the general solution has the form of a general linear polynomial c1 plus c2x times e to the alpha x. In the complex conjugate case, the general solution of the differential equation is e to the alpha x times c1 cosine beta x plus c2 sine beta x, where alpha is the real part of both roots and plus and minus beta are the imaginary parts of the roots. Linear second-order equations 3. Non-homogeneous equations. The problem we want to address here is that of finding the general solution of a non-homogeneous equation y double prime plus py prime plus qy equals f. Let's begin by noting that given any two solutions u and v, their difference, y equal to u minus v, satisfies the homogeneous reduced equation y double prime plus py prime plus qy equals 0. Let's let y1 and y2 be linearly independent solutions of the reduced differential equation. If z is a known particular solution of the non-homogeneous equation, and y is any other solution of that equation, then the difference y minus z is a solution of the reduced equation. So we can write that difference as c1y1 plus c2y2 for some constants c1 and c2, which tells us that y is equal to c1y1 plus c2y2 plus z for some c1 and c2. In other words, the general solution of the non-homogeneous differential equation is y equal to c1y1 plus c2y2 plus z, where z is any known particular solution. So notice that this general solution consists of the general solution of the reduced differential equation plus any particular solution of the non-homogeneous differential equation. So our focus here will be on finding a particular solution. A general method for doing this is known as variation of parameters, which is sometimes called variation of constants. We'll state the result as a theorem. Let y1 and y2 be linearly independent solutions of y double prime plus py prime plus qy equals 0, and let w be the Wronskian of y1 and y2, y1 times y2 prime minus y1 prime times y2. If u and v satisfy u prime equal to minus y2 over w times f, and v prime equals y1 divided by w times f, then z equal to u times y1 plus v times y2 is a solution of y double prime plus py prime plus qy equals f. This theorem provides us with a method that consists of 3 steps as follows. First, anti-differentiate minus y2 over w times f to get u. Second, anti-differentiate y1 over w times f to get v. And third, write the particular solution z as u times y1 plus v times y2. Now, before we use the method on a few examples, let's look at a proof of the theorem. Let z equal u times y1 plus v times y2, where u prime equals minus y2 over w times f, and v prime equals y1 over w times f. Then we compute the derivative z prime using the product rule on each term, and we get u prime times y1 plus u times y1 prime plus v prime times y2 plus v times y2 prime. The first term here is equal to minus y2 over w times f times y1, and the third term is equal to y1 over w times f times y2. These add up to 0, and so z prime is u times y1 prime plus v times y2 prime. Next, we compute z double prime, again using the product rule on each term. We get u prime times y1 prime plus u times y1 double prime plus v prime times y2 prime plus v times y2 double prime. By combining the first and third terms here, we get y1 times y2 prime minus y1 prime times y2 divided by w all times f, and the numerator of that fraction is precisely w. And so z double prime is equal to f plus u times y1 double prime plus v times y2 double prime. Now let's look at z double prime plus p times z prime plus q times z. It's equal to f plus u times y1 double prime plus v times y2 double prime plus p times the quantity u times y1 prime plus v times y2 prime plus q times the quantity uy1 plus vy2. Now let's collect the terms that have u as a factor as well as the terms that have v as a factor and rewrite this expression as f plus u times y1 double prime plus py1 prime plus qy1 plus v times y2 double prime plus py2 prime plus qy2. Now, assuming that y1 and y2 are solutions of the reduced homogeneous equation, the second and third terms in this expression are both 0, and therefore z double prime plus pz prime plus qz is equal to f. Example: find the general solution of y double prime plus 3y prime plus 2y equals e to the minus t. We begin by solving the corresponding reduced equation, whose characteristic polynomial is r squared plus 3r plus 2, which factors as r plus 1 times r plus 2, and so the roots of the characteristic equation are minus 1 and minus 2. So we have linearly independent solutions of the reduced equation, y1 equal to e to the minus t and y2 equal e to the minus 2t. We're going to need the Wronskian of those two solutions. That's w equal to e to the minus t times minus 2 e to the minus 2t minus e to the minus t times e to the minus 2t, which all adds up to minus e to the minus 3t. So we're ready to compute u and v. U prime equals minus y2 over w times f. Here y2 is e to the minus 2t, and w is equal to minus e to the minus 3t, and so this becomes e to the t times f. Now f is e to the minus t, and so u prime equals e to the t times e to the minus t, which equals 1. So anti-differentiating gives us u equal to t. Note that we don't need to include a constant of integration here, since we're looking for only a particular solution. Next, we'll find v from the equation v prime equals y1 over w times f. y1 is e to the minus t, and again w is minus e to the minus 3t, and so v prime is minus e to the 2t times f, and again f is e to the minus t, so this is minus e to the 2t times e to the minus t, which equals minus e to the t. So we anti-differentiate and obtain v equal to minus e to the t. So now we have u times y1 plus v times y2 equal to t times e to the minus t minus e to the t times e to the minus 2t, which equals t times e to the minus t minus e to the minus t. Now, as sometimes happens, one of the terms of this solution satisfies the reduced homogeneous equation, and the solution may be simplified by simply removing that term. So we have the particular solution z equal to t times e to the minus t. And finally, we write down the general solution of the non-homogeneous equation by adding that particular solution to the general solution of the reduced homogeneous equation. That's y equal to c1 e to the minus t plus c2 e to the minus 2t plus t times e to the minus t. Here's another example. Find a particular solution of y double prime plus 4y equals 4 times cosine 2t. We begin by finding a pair of solutions of the reduced homogeneous equation. The characteristic equation is r squared plus 4 equals 0, and so we have characteristic roots equal to plus and minus 2i. That tells us that we can take y1 equal to cosine 2t and y2 equal to sine 2t. The Wronskian of those two solutions is cosine 2t times 2 times cosine 2t minus 2 sine 2t times sine 2t, all of which is equal to 2 times cosine squared 2t plus sine squared 2t, and so the Wronskian is equal to 2. Now, we want u to satisfy u prime equal to minus y2 divided by w times f, which here is minus sine 2t divided by 2 times f, and our f is 4 times cosine 2t, and so u prime should equal minus 2 times sine 2t times cosine 2t. Next, we anti-differentiate to obtain u. An antiderivative of sine 2t times cosine 2t turns out to be sine squared 2t divided by 4, and so minus 2 times that is minus 1/2 times sine squared 2t. Next, we want v to satisfy v prime equal to y1 over w times f, which here is cosine 2t over 2 times f, and again f is 4 times cosine of 2t, and so we want v prime equal to 2 times cosine squared 2t. For the purpose of anti-differentiating, we use the half angle formula and rewrite that as 2 times 1/2 of 1 plus cosine of 2 times 2t, or 1 plus cosine 4t. So now, antidifferentiating gives us t plus 1/4 of sine of 4t. Now, using the double angle formula for sine, we can write that as t plus 1/2 of sine of 2t times cosine of 2t. So now we have our particular solution, u times y1 plus v times y2 equal to minus 1/2 of sine squared 2t times cosine of 2t plus t plus 1/2 sine 2t cosine 2t all times sine 2t. Notice that multiplying out the second term would produce a 1/2 sine squared 2t times cosine 2t term, and that plus the first term here equals 0. So we end up with our particular solution z equal to t times sine of 2t. Our next example involves an equation with non-constant coefficients. Given that e to the minus x squared over 2 and x times e to the minus x squared over 2 are solutions of the homogeneous equation y double prime plus 2x times y prime plus 1 plus x squared times y equals 0, find a particular solution of y double prime plus 2xy prime plus 1 plus x squared times y equal to e to the minus x squared over 2 divided by 1 plus x squared. Fortunately here we're given solutions y1 and y2 of the reduced equation, so we begin by computing their Wronskian. The first term is y1 times y2 prime, and y2 prime, using the product rule and then factoring, turns out to be 1 minus x squared times e to the minus x squared over 2. Then we subtract y1 prime times y2, and y1 prime is minus x times e to the minus x squared over 2. Now when we multiply out the first term, we'll have e to the minus x squared minus x squared times e to the minus x squared, and multiplying out the second term gives us plus x squared e to the minus x squared, and so we end up with only e to the minus x squared. So now we want to find the function u, for which u prime is equal to minus y2 divided by w times f, which here is minus e to the minus x squared over 2 divided by e to the minus x squared all times f. And since our non-homogeneous term f is e to the minus x squared over 2 divided by 1 plus x squared, this all becomes minus 1 over 1 plus x squared. Now recalling that 1 over 1 plus x squared is the derivative of inverse tangent x, we have u equal to minus inverse tangent x. Next, we want to find a function v, for which v prime is equal to y1 divided by w times f, which here is x times e to the minus x squared over 2 divided by e to the minus x squared times f, which simplifies to x divided by 1 plus x squared. Since the numerator of this fraction is exactly half of the derivative of the denominator, antidifferentiation gives us v equal to 1/2 of the natural log of the denominator, 1/2 the natural log of 1 plus x squared. Now finally we assemble our particular solution in the form u times y1 plus v times y2, which is minus inverse tangent x times e to the minus x squared over 2, plus 1/2 of the natural log of 1 plus x squared times x times e to the minus x squared over 2. Let's simplify this a bit by factoring out 1/2 of e to the minus x squared over 2. The other factor then is log of 1 plus x squared minus 2 times the inverse tangent of x.
Linear second-order equations 4. Non-homogeneous equations with constant coefficients. We consider here non-homogeneous linear second-order equations of the form y double prime plus py prime plus qy equals f with constant coefficients p and q. Recall that its general solution is of the form y equal to c1y1 plus c2y2 plus z, where z is any particular solution and c1y1 plus c2y2 is the general solution of the reduced homogeneous equation y double prime plus py prime plus qy equals 0. Also recall that if R1 and R2 are the roots of the equation R squared plus PR plus Q equals 0, then the general solution of the reduced equation takes one of the following three forms. Y equal to C1 times e to the R1 times x plus C2 times e to the R2 times x if R1 is not equal to R2 and P squared is greater than 4Q. This is the case when the characteristic equation has distinct real roots. The general solution of the reduced equation may have the form y equal to a linear polynomial c1 plus c2x times e to the minus px over 2 if R1 is equal to R2, and in that case that common value is minus p over 2. This is the case where the characteristic equation has a double real root. In the third case, the general solution has the form e to the alpha x times c1 cosine beta x plus c2 sine beta x, and this happens if R1 and R2 are complex conjugates alpha plus and minus beta, where beta is not 0. Now we're going to consider a handful of different cases for the form of the non-homogeneous term on the right-hand side of our differential equation. The first case we'll consider involves polynomials. Here we'll go ahead and state a general result and then illustrate it with a couple of examples. Let capital P of x be a polynomial, possibly constant, with degree n. Then the equation y double prime plus py prime plus qy equals p of x has a polynomial solution with degree n if the coefficient q is not 0, degree n plus 1 if q equals 0 and p is not 0, and degree n plus 2 if p and q are both 0. Now notice that the second situation here occurs when the differential equation is missing the y term, and the third situation occurs when the differential equation is missing both the y and y prime terms and has the simple form of y double prime equals p of x. Now let's look at an example that illustrates that third case. Find a particular solution of y double prime equals 3x squared. This is really just an anti-differentiation problem. We're looking for a function z whose second derivative is 3x squared. That will happen if z prime is equal to x cubed, which is true if z is equal to x to the fourth divided by 4. So notice that the two anti-differentiations increase the degree by 2. Moreover, there is no polynomial solution of that equation with degree less than 4. Here's an example that illustrates the second case where the y term in the equation is missing. Find a particular solution of y double prime plus y prime equals 3x squared. Now just for the sake of illustration, let's try a quadratic first, since the right-hand side of the equation is quadratic. Let's look for z in the form of ax squared plus bx plus c. That gives us z prime equal to 2ax plus b, which tells us that z double prime is equal to 2a. And so z double prime plus z prime will equal 2a plus 2ax plus b. Now notice that there is no x squared term here, and so it's impossible for this to equal 3x squared. So the equation has no quadratic solution. So let's look for a cubic solution. Let z equal ax cubed plus bx squared plus cx plus d. Then z prime is 3a times x squared plus 2bx plus c, and z double prime is 6ax plus 2b. So z double prime plus z prime is equal to 6ax plus 2b plus 3ax squared plus 2bx plus c. Now collecting like terms, we have 3ax squared plus 6a plus 2b times x plus 2b plus c. Now we want all of that to equal 3x squared for all x. That will only happen if the coefficients of x squared are the same, so we need to have 3a equal to 3, which happens if a is equal to 1. We also need for the coefficients of x to be the same, and that tells us that 6a plus 2b has to equal 0, which is true if b is equal to minus 3a, and since a is 1, b must equal minus 3. The constant terms in the two polynomials must be the same, and so 2b plus c has to equal 0. That's true if c is equal to minus 2b, and since b is minus 3, c must be 6. Now notice that since the equation was missing the y term, z itself was not involved here, and so the constant term d is undetermined. In fact, it could be taken to be any constant, and that's because constants satisfy the reduced homogeneous equation. But as far as finding a particular solution is concerned, we may as well just take d equal to 0, and note that it was unnecessary from the beginning here. So we have our particular solution, z equal to x cubed minus 3x squared plus 6x. Now let's look at a third example. Find a particular solution of y double prime plus 4y prime plus 3y equal to 27x squared. Notice that here the coefficients p and q are both non-zero, and so we expect a solution with the same degree as the right-hand side. So we'll look for a solution z equal to ax squared plus bx plus c, whose first derivative is 2ax plus b, and whose second derivative is 2 times a. So z double prime plus 4z prime plus 3z equals 2a plus 4 times 2ax plus b plus 3 times ax squared plus bx plus c. Now we gather like terms and rewrite that as 3ax squared plus 8a plus 3b times x plus 2a plus 4b plus 3c. Now that polynomial will be the same as the polynomial 27x squared for all x if 3a is equal to 27, 8a plus 3b is equal to 0, and 2a plus 4b plus 3c is equal to 0. So now we have a system of 3 equations and 3 unknowns, a, b, and c, which fortunately is easy to solve. 3a equals 27 tells us that a is equal to 9. The second equation says that b equals minus 8a divided by 3, and since a is 9, b is equal to negative 24. The third equation says that c must equal minus 2a plus 4b all divided by 3, and since a is 9 and b is minus 24, this becomes minus negative 78 divided by 3, which is 26. So we have our particular solution, z equal to 9x squared minus 24x plus 26. So we do in fact find out that with a quadratic polynomial on the right-hand side, we end up with a quadratic particular solution. Case 2. Products of polynomials and exponential functions. We now consider equations of the form y double prime plus py prime plus qy equal to capital P of x times e to the kx, where p of x is a polynomial, which is possibly constant. We start out with an example. Let's find a particular solution of y double prime plus 3y prime plus 2y equal to x plus 2 times e to the minus x. Let's begin by looking for a solution z of the form u of x times e to the minus x, where u is a function to be determined. Now, of course, since the right-hand side is a polynomial times e to the minus x, we can probably expect u of x to end up being a polynomial as well. Let's compute z prime using the product rule. We'll have 2 terms, each of which will have a factor of e to the minus x. The first term is e to the minus x times u prime, and the second term will be minus e to the minus x times u. Now let's compute z double prime, again using the product rule. E to the minus x will be a factor of both terms. The first term is e to the minus x times the derivative of u prime minus u, which is u double prime minus u prime. And the second term is e to the minus x times minus u prime minus u, or minus u prime plus u. Simplifying that gives us e to the minus x times u double prime minus 2u prime plus u. Now, z double prime plus 3z prime plus 2z will be an expression having e to the minus x as a common factor,
The other factor has a contribution from z double prime of u double prime minus 2u prime plus u, and 3z prime contributes 3 times u prime minus u, and 2z gives us 2 times u. Now all of that simplifies to e to the minus x times u double prime plus u prime. So z double prime plus 3z prime plus 2z will equal x plus 2 times e to the minus x if u double prime plus u prime is equal to x plus 2. Since the u term is missing in this equation and the right-hand side is a first-degree polynomial, we expect a solution u of the form ax squared plus bx. For such a u double prime is equal to 2 times a, and u prime equals 2ax plus b. So u double prime plus u prime will equal x plus 2 if 2a is equal to 1, that is, a equals 1/2, and if the constant term 2a plus b is equal to 2, which since a is 1/2 tells us that b equals 1. So we now have u equal to 1/2 x squared plus x, or 1/2 x times x plus 2. Therefore, our particular solution z is 1/2 x times x plus 2 times e to the minus x. Now let's consider the general case y double prime plus py prime plus qy equals a polynomial p of x times e to the kx. And just as in the previous example, we'll look for a solution z in the form of u of x times e to the kx, where u of x is a function that we want to determine. We first compute derivatives. If z is u times e to the kx, then z prime turns out to be, by the product rule, u prime plus ku times e to the kx. Then, using the product rule again, z double prime ends up being u double prime plus 2k times u prime plus k squared times u, all times e to the kx. And so, z double prime plus pz prime plus qz will consist of several terms with e to the kx as a common factor. In the other factor, we have u double prime plus 2ku prime plus k squared u coming from z double prime, and then p times u prime plus ku from pz prime, and then simply q times u from qz. Simplifying that factor gives us u double prime plus 2k plus p times u prime plus k squared plus pk plus q times u, all that times e to the kx. So z equal to u times e to the kx satisfies our differential equation if that factor is equal to p of x. Now notice that in this differential equation, the coefficient of u prime is 2k plus p, and the coefficient of u is k squared plus pk plus q, which just happens to be the value of the characteristic polynomial at k. So let's let chi of r be the characteristic polynomial. Chi of r equals r squared plus pr plus q. And notice that its derivative, chi prime of r, is equal to 2r plus p. So the differential equation here for the function u can be written as u double prime plus chi prime of k times u prime plus chi of k times u equals p of x. Now the kind of solution that we find for u here depends a lot upon whether one or both of these coefficients are 0. Now notice that the coefficient of u here, chi of k, is 0 if k is a root of the characteristic polynomial, and both coefficients are 0 if k is a double root of the characteristic polynomial. Also notice that none of this depends on what type of function capital P of x is here. The same thing is true even if it's not a polynomial. Now let's state what we've learned as a theorem. Let chi of r be the characteristic polynomial r squared plus pr plus q. Then the differential equation y double prime plus py prime plus qy equal to a function phi of x times e to the kx has a solution z equal to u of x times e to the kx,
where u of x satisfies u double prime plus chi prime of k times u prime plus chi of k times u equals phi of x. Now, because of our previous theorem about equations with polynomial non-homogeneous terms, we add that if phi of x is a polynomial, possibly constant, with degree n, then u of x is also a polynomial with degree n if chi of k is not 0, degree n plus 1 if chi of k is 0 and chi prime of k is not 0, and degree n plus 2 if chi of k and chi prime of k are both 0. The second of these situations corresponds to k being a simple root of the characteristic polynomial, which means that e to the kx satisfies the reduced homogeneous equation. In the third case, k is a double root of the characteristic polynomial, which means that e to the kx and x times e to the kx both satisfy the reduced homogeneous equation. Example: find a particular solution of y double prime plus y prime plus 5y equals x plus 1 times e to the minus x. We'll look for a solution z equal to u of x times e to the minus x. First, let's observe that the characteristic polynomial chi of r is r squared plus r plus 5, and its derivative chi prime of r is 2r plus 1. Now our value of k here is minus 1, so we compute chi of minus 1 and get 5. Chi prime of minus 1 is minus 1, and therefore u of x will satisfy u double prime minus u prime plus 5u equals x plus 1. And since the coefficient of u here is not 0, we'll be able to find a linear polynomial solution u equal to ax plus b. We substitute that into the left side of the differential equation. U double prime is 0, minus u prime is minus a, and 5u is 5 times ax plus b. And on the right-hand side, we have x plus 1. We'll simplify the left-hand side. We get 5a times x plus 5b minus a equal to x plus 1, which tells us that 5a must be 1 and 5b minus a must be 1 as well. Solving for a and b gives us a equal to 1/5, and then b equal to 1 plus a divided by 5 ends up being 6 divided by 25. And so we have u equal to 1/5 x plus 6 over 25, and factoring out 1/25, that becomes 1 over 25 times 5x plus 6. Therefore, our particular solution z is 1 over 25 times 5x plus 6 times e to the minus x. Example: find the general solution of y double prime plus 4y prime plus 4y equals 4 times e to the minus 2x. Let's first consider the reduced equation y double prime plus 4y prime plus 4y equals 0. The characteristic polynomial is chi of r equals r squared plus 4r plus 4, which is a perfect square, r plus 2 squared. So minus 2 is a double root. So two linearly independent solutions of the homogeneous equation are y1 equal to e to the minus 2x and y2 equal x times e to the minus 2x. Now let's look for a particular solution z equal to u of x times e to the minus 2x. Since chi prime of r is 2 times r plus 2, we have both chi of minus 2 and chi prime of minus 2 equaling 0. So the differential equation for u is u double prime equals 4. Antidifferentiation gives us u prime equals 4x, and another step of antidifferentiation gives us u equal to 2 times x squared. And so our particular solution is 2x squared times e to the minus 2x. Now we're looking for the general solution of the differential equation. We construct that by writing down the general solution of the homogeneous reduced equation. That's c1 times e to the minus 2x plus c2 times x times e to the minus 2x, and then adding the particular solution we've just found, 2x squared times e to the minus 2x. Now e to the minus 2x is a common factor, and so we can express our general solution as c1 plus c2x plus 2 times x squared all times e to the minus 2x. Case 3. Sinusoidal functions. Let's start with an example. Find a particular solution of y double prime plus 3y prime plus 3y equals 3 times cosine of 3x. Since the non-homogeneous term here, 3 cosine 3x, is a sinusoidal function with period 2 pi over 3, we're going to look for a solution z in the general form of a sinusoidal function with that same period, which we'll write as a times cosine 3x plus b times sine 3x. Even though the right-hand side of the differential equation involves only cosine, it is necessary to include a sine term here for reasons which will become clear momentarily. So let's compute z prime and z double prime. Z prime is minus 3a sine 3x plus 3b cosine 3x. Now differentiating again, we find that z double prime is minus 9a cosine 3x minus 9b sine 3x. Now let's look at z double prime plus 3z prime plus 3z. That will consist of 3 terms having cosine 3x as a factor and 3 more terms having sine 3x as a factor. From z double prime, we get minus 9a times cosine 3x. From 3z prime, we get 3 times 3b times cosine 3x. And from 3z, we get 3a cosine 3x. Also, from z double prime, we get minus 9b times sine 3x. From 3z prime, we get 3 times minus 3a sine 3x. And from 3z, we get 3b sine 3x. The coefficient of cosine 3x simplifies to minus 6a plus 9b, and the coefficient of sine 3x simplifies to minus 9a minus 6b. Now we want all of this to equal 3 times cosine 3x for all x. Now that will happen if the coefficient of cosine 3x, which is minus 6a plus 9b, equals 3, and if the coefficient of sine 3x, which is minus 9a minus 6b, is equal to 0. So we now have 2 simple linear equations for a and b to solve. We'll do this by multiplying the first equation by 2 and the second equation by 3 and adding. This will eliminate the b term. That gives us minus 39a equals 6, and so a is 6 divided by minus 39, or minus 2 over 13. Now the second equation here tells us that b has to equal minus 9a divided by 6, and that turns out to be 3 divided by 13. Now, factoring out 1/13, we can write our particular solution as 1/13 times minus 2 cosine 3x plus 3 sine 3x. Now consider the general case y double prime plus py prime plus qy equals either cosine omega x or sine omega x. We'll begin just as in the previous example. We'll look for a solution z of the form a times cosine omega x plus b times sine omega x. Then z prime is minus a omega sine omega x plus b times omega times cosine omega x. And z double prime is minus a omega squared cosine omega x minus b omega squared sine omega x. Now z double prime plus pz prime plus qz will contain multiples of cosine omega x and multiples of sine omega x. The coefficient of cosine omega x in z double prime is minus a omega squared. In p times z prime, it's b times p omega, and in qz, it's qa. The coefficient of sine omega x in z double prime is minus b omega squared. In pz prime, it's minus a p omega, and in qz, it's qb. The coefficient of cosine omega x can be expressed as q minus omega squared times a plus p omega times b, and the coefficient of sine omega x we'll write as minus p omega a plus q minus omega squared times b. Now, if the right-hand side of the differential equation is cosine omega x, we want the coefficient of cosine omega x here to be 1 and the coefficient of sine omega x to be 0. And if the right-hand side of the differential equation is sine omega x, we want the coefficient of cosine omega x to be 0 and the coefficient of sine omega x to be 1. Now, regardless of the numbers on the right-hand side, these two algebraic equations for a and b can be written in matrix form, where the coefficient matrix has q minus omega squared and p omega in the first row, and minus p omega and q minus omega squared in the second row. Now recall that the determinant of this coefficient matrix is what tells us whether or not the system of equations has a unique solution for a and b. That determinant is q minus omega squared times q minus omega squared minus p omega times minus p omega. So we have q minus omega squared, quantity squared, plus p squared omega squared. Since this equation is the sum of two squares, it can't be 0 unless both terms are 0. Now we're assuming that omega is not 0, so the only way this determinant is 0 is if p is equal to 0 and q is equal to omega squared. That's the only situation in which this differential equation will not have a solution of the form a cosine omega x plus b sine omega x. Now notice that that exceptional case occurs when the differential equation can be written as y double prime plus omega squared y equals either cosine omega x or sine omega x. And that is precisely the case where the non-homogeneous term satisfies the homogeneous reduced differential equation. So let's see what happens in that exceptional case where the differential equation is y double prime plus omega squared y equals either cosine omega x or sine omega x. Here we'll look for a solution of the form z equal to x times a cosine omega x plus b sine omega x. This is a sensible form to try based upon what we've seen happen when the non-homogeneous term of the differential equation was an exponential function that satisfied the reduced equation. Now with this form for z, we have z prime equal to 1 times a cosine omega x plus b sine omega x plus x times minus a omega sine omega x plus b omega cosine omega x. Now z double prime is minus a omega sine omega x plus b omega cosine omega x plus two more terms that we get from the product rule, 1 times minus a omega sine omega x plus b omega cosine omega x plus x times minus a omega squared cosine omega x minus b omega squared sine omega x. Now when we form z double prime plus omega squared z, all of the terms involving x add up to 0, and we have only 2b omega cosine omega x minus 2a omega sine omega x, which we'll rewrite as 2 omega times b cosine omega x minus a sine omega x. This will equal cosine omega x if a is 0 and b is 1 over 2 omega. It will equal sine omega x if a is minus 1 over 2 omega and b is 0. So, when the non-homogeneous term is cosine omega x, our particular solution is 1 over 2 omega times x times sine omega x. And when the non-homogeneous term is sine omega x, the particular solution is minus 1 over 2 omega times x times cosine omega x. Now let's summarize this in a theorem. If p is not 0 or q is not omega squared, then the equation y double prime plus py prime plus qy equals either cosine omega x or sine omega x has a particular solution of the form z equal to a times cosine omega x plus b times sine omega x, where a and b are constants. If p equals 0 and q equals omega squared, then a particular solution is z equal to either 1 over 2 omega times x times sine omega x, or minus 1 over 2 omega times x times cosine omega x. The solution involving sine occurs when the non-homogeneous term is cosine omega x, and the solution involving cosine occurs when the non-homogeneous term is sine omega x. Again, we emphasize that this exceptional second case occurs when the equation has the form y double prime plus omega squared y equal to either cosine omega x or sine omega x, and so the non-homogeneous term on the right-hand side satisfies the homogeneous reduced equation. Case 4. Products of exponential and sinusoidal functions. Fortunately, we can handle this case by piecing together what we've already learned about equations with non-homogeneous terms that are products with exponential factors and equations with sinusoidal non-homogeneous terms. We'll state the result as a theorem. The equation y double prime plus py prime plus qy equal to either e to the kx times cosine omega x or e to the kx times sine omega x has a solution z equal to a function u of x times e to the kx, where u of x satisfies u double prime plus chi prime of k u prime plus chi of k times u equals either cosine omega x or sine omega x, where chi is the characteristic polynomial associated with the differential equation. Note that this is really the same as the theorem that covered case 2, only here it's expressed in terms of trigonometric functions rather than polynomials. Now let's work an example. Let's find the general solution of y double prime plus 2y prime plus 2y equal to e to the minus x times sine x. We'll need the characteristic polynomial, both for finding the general solution of the reduced equation and to help us find a particular solution. That's chi of r equal to r squared plus 2r plus 2, and its roots are given by the quadratic formula as minus 2 plus or minus the square root of 4 minus 8 all divided by 2, which simplifies to minus 1 plus and minus I. So we can take note of the fact now that the general solution of the reduced equation is going to be e to the minus x times c1 cosine x plus c2 sine x, since the real part of the characteristic roots is minus 1 and the imaginary parts are plus and minus 1. Now our theorem tells us that the non-homogeneous equation has a particular solution z equal to u of x times e to the minus x, where u satisfies u double prime plus chi prime of minus 1 times u prime plus chi of minus 1 times u equals sine x. Since chi prime of r is 2r plus 2, chi prime of minus 1 is 0. Chi of minus 1 is minus 1 squared minus 2 plus 2, which equals 1. So the equation that we need to solve to obtain u is u double prime plus u equals sine x. This falls into the so-called exceptional case, since sine x will satisfy the corresponding reduced equation u double prime plus u equals 0. So rather than a sinusoidal particular solution, we'll have a solution that has x as a factor. Since the non-homogeneous term here is sine x, a particular solution is going to be minus 1/2 of x times cosine x. There we're using the formula minus 1 over 2 omega times x times cosine omega x, with omega equal to 1. Next we multiply by e to the minus x to obtain our particular solution. Z equals minus 1/2 times x times e to the minus x times cosine x. Now finally we write our general solution as y equals e to the minus x times c1 cosine x plus c2 sine x minus 1/2 x times e to the minus x cosine x, which we can rearrange and write a little more simply as 1/2 of e to the minus x times c1 minus x times cosine x plus c2 sine x. Note that the c1 and c2 in this expression are actually 2 times the previous c1 and c2, since we've essentially factored 1/2 from the entire expression. There's no harm in doing that, since c1 and c2 are arbitrary constants to begin with. Let's finish up with a summary of what we've learned. The equation y double prime plus py prime plus qy equals capital P of x, where P of x is a polynomial of degree n and little p and q are constants, has a particular solution that's a polynomial with degree n if q is not 0, degree n plus 1 if q is 0 and p is not 0, and degree n plus 2 if p and q are both 0. The equation y double prime plus py prime plus qy equals cosine omega x or sine omega x, with p not equal to 0 or q not equal to omega squared, will have a sinusoidal solution with the same period as the non-homogeneous term, that is, a solution of the form a cosine omega x plus b sine omega x, where a and b are constants. When p is 0 and q is omega squared, this equation becomes y double prime plus omega squared y equal to cosine omega x or sine omega x, and a particular solution is given by 1 over 2 omega times x times sine omega x, or minus 1 over 2 omega times x times cosine omega x. Note that when the non-homogeneous term is cosine omega x, the particular solution involves sine omega x, and when the non-homogeneous term is sine omega x, the particular solution involves minus cosine omega x. When the non-homogeneous term is a function phi of x times e to the kx, the equation has a particular solution of the form u of x times e to the kx, where u satisfies u double prime plus chi prime of k times u prime plus chi of k times u equals phi of x, where chi of r is the characteristic polynomial r squared plus pr plus q. When the function phi is a polynomial or a sinusoidal function, one of the previous three results applies to the equation for u. Mechanical Vibrations Part 1. Unforced Motion. Simple spring mass systems. Consider a basic mechanical system consisting of a linear spring with stiffness K, with one end held fixed and an object with mass m attached to the other end. The stiffness coefficient K represents the force exerted by the spring when it's stretched 1 unit of length. The apparatus is oriented in such a way that we can assume that any motion of the mass is along a straight line. The figure here shows a typical such system. We have a cart attached to a spring with the other end of the spring attached to a wall. We let y denote the position of the mass relative to its equilibrium position, with y positive when the spring is stretched and y negative when the spring is compressed. Assuming there are no forces acting on the mass other than that exerted by the spring, Newton's second law, together with Hooke's law, tells us that mass times acceleration, that is, mass times the second derivative of y with respect to t, will equal minus k times y. In other words, the force exerted by the spring on the mass is proportional to the amount that the spring is stretched, with the proportionality constant being minus k, where k is the stiffness coefficient. Now rearranging and switching to prime notation for simplicity, we have m times y double prime plus k times y equals 0. This is the differential equation satisfied by the position of the mass. The same equation arises if the spring hangs from a support with gravity acting upon it and the mass. The reason is that the force of gravity is always balanced by an equal force from the spring. With S the amount that the spring is stretched when y is equal to 0, that is, when the system is at rest, Newton's second law tells us that mass times acceleration is equal to the downward force of gravity, which is m times g, minus the spring stiffness K times the amount that the spring is stretched, which is y plus S. But K times S is equal to mg because those are the opposing forces that balance each other when the mass is at rest. So again, we end up with m times y double prime plus k times y equals 0. We also get the same equation if the entire system is flipped vertically. Damping. A damping force, think friction, may be assumed proportional to the velocity of the mass. So we can write down Newton's second law as m times y double prime equals minus ky, the spring force, minus a positive constant delta times y prime. Now rearranging, we have my double prime plus delta y prime plus ky equals 0. This is a linear second-order homogeneous differential equation with constant coefficients. Moreover, the coefficients m and k are positive, and the coefficient delta is positive if damping is present and 0 otherwise. We can also include an external force as a non-homogeneous term. Writing down Newton's second law, we have m times y double prime equals minus ky minus delta y prime plus capital F of t, where capital F of t represents the external force. And moving all the y terms to the left side, we have my double prime plus delta y prime plus ky equals f of t. One way that an external force is created is by moving the other end of the spring. If little f of t is its position relative to its position when the system is at rest, then the amount that the spring is stretched is reduced by f of t. And so when we write down Newton's second law, instead of having a force minus ky, we have the force minus k times y minus f of t. So when we rearrange the equation as usual, putting all the y terms on the left, we have the force term k times f of t on the right-hand side. Note that f of t has the same units as the solution y, that is, units of length, and k times f of t would then have units of force, just as k times y does. Unforced motion, or free vibrations. When there's no external force on the system, the initial value problem to solve is my double prime plus delta y prime plus ky equals 0, with initial conditions y of 0 equals some y naught and y prime of 0 equals some initial velocity v naught. There will be 4 different cases to consider, and the first case is the undamped case, in which the damping coefficient delta is equal to 0. The differential equation is my double prime plus ky equals 0, and we'll divide through by m and rewrite the equation as y double prime plus omega squared y equals 0, where omega is the square root of k over m. By inspection, the general solution of this equation is y equals c1 cosine omega t plus c2 sine omega t. We can already make an important observation. Irrespective of initial conditions, this is simple harmonic motion with period 2 pi over omega seconds and frequency omega over 2 pi cycles per second. So no matter how the mass is set in motion, the system always vibrates with the same frequency. We can rewrite the solution y in the form y equals a times sine omega t plus phi naught, where a is positive and the angle phi may be chosen to be between 0 and 2 pi. Here a is the amplitude of the motion, and phi naught is the angle through which the basic sine wave is shifted to the left. The actual leftward shift is phi naught divided by omega seconds. Now this specific form is somewhat arbitrary. We could just as easily write it in terms of cosine, and we could also use as the argument omega t minus phi naught, making phi naught the angle through which the sine wave is shifted to the right. And we might just as well choose the angle phi naught from the interval from minus pi to pi. Nevertheless, for the form a sine omega t plus phi naught, once we've found c1 and c2 from initial conditions, we can find a and phi naught from the formulas a equals the square root of c1 squared plus c2 squared, and sine of phi naught equals c1 divided by a, and cosine of phi naught equals c2 divided by a. All of this is just a consequence of the addition formula for the sine function, which says that sine omega t plus phi naught is equal to sine omega t times cosine of phi naught plus cosine omega t times the sine of phi naught.
We could also find A and phi naught directly from the initial conditions as follows. Y of 0 equals y naught tells us that A times the sine of phi naught equals y naught. Now, since y prime is equal to A times omega times cosine omega t plus phi naught, y prime of 0 equals v naught tells us that A times omega times cosine of phi naught equals v naught. And dividing this by omega gives us A cosine of phi naught equals v naught divided by omega. So we have two equations and the two unknowns A and phi naught. We can find A by squaring each side of both equations and then adding. That will give us A squared times sine squared phi naught plus cosine squared phi naught, which is A squared times 1. And so we have A squared equal to y naught squared plus v naught squared over omega squared. And of course we take the square root to obtain A. Now with A known, phi naught is determined by the equation sine of phi naught equals y naught divided by A, and cosine of phi naught equals v naught divided by A times omega. Now let's look at an example. A 5 kilogram mass hangs from a spring with stiffness 45 newtons per meter, whose top end is fixed. The mass is pulled down 1/10 of a meter and projected upward with velocity minus 3/5 meters per second. Find the equation of motion in the form y equals A times sine omega t plus phi naught. Let's first write down the initial value problem that we want to solve. Since the mass is 5 and the spring stiffness is 45, the differential equation is 5 times y double prime plus 45y equals 0. Remembering that down is the positive direction for this type of problem, we have an initial position y of 0 equals 1/10, and the initial velocity is y prime of 0 equal to minus 3/5. Now dividing the differential equation by 5 gives us y double prime plus 9y equals 0, which makes it clear that the general solution can be written as y equals c1 cosine 3t plus c2 sine 3t. Now rather than finding c1 and c2 from the initial conditions, let's go ahead and write this as y equals A times sine of 3t plus phi naught and determine A and phi naught from the initial conditions. Y of 0 equals 1/10 tells us that A times sine phi naught equals 1/10. Since y prime equals 3A cosine 3t plus phi naught, y prime of 0 equal to minus 3/5 tells us that 3A cosine phi naught equals minus 3/5, and after we divide by 3, we have A cosine phi naught equal to minus 1/5. Now by squaring each side of both equations and adding, we obtain A squared equals 1/10 squared plus the square of minus 1/5, which is 1 over 100 plus 1/25, which ends up being 1/20. And so by taking the square root, we get A equal to 1 over the square root of 20, which is 1 over 2 root 5. And punching that in the calculator tells us that A is approximately 0.224 with units of meters. So now the equations for sine of phi naught and cosine of phi naught become 1 over 2 root 5, sine of phi naught equals 1/10, and 1 over 2 root 5 times cosine phi naught equals minus 1/5. So sine of phi naught is 1 over root 5, and cosine of phi naught is minus 2 over root 5. Now, since sine of phi naught is positive and cosine of phi naught is negative, we know that phi naught is a second quadrant angle. Consequently, we can use the inverse cosine function to compute phi naught, since the range of the inverse cosine function is the interval from 0 to pi. So phi naught equals inverse cosine of minus 2 over root 5, which is approximately 2.68, and converted to degrees, it's 153 degrees. Now dividing phi naught by omega gives us the actual time shift here. 2.68 divided by 3 is about 0.893 seconds. So our solution is 1 over 2 root 5 times sine of 3t plus phi naught, where phi naught is the inverse cosine of minus 2 over root 5. In numerical form, this looks like y equals 0.224 times sine of 3t plus 2.68, which we could also write as 0.224 times sine of 3 times t plus 0.983. Here's the graph of the solution. Notice the amplitude 0.224, and notice that if we were to follow that sine curve backwards in time, it would begin with a value of 0 at minus 0.893. That's the negative of phi naught divided by omega. Damping. With damping, delta is positive, and the characteristic equation is mr squared plus delta r plus k equals 0, and its roots, r1 and r2, are minus delta plus and minus the square root of delta squared minus 4km, all divided by 2m. The crucial quantity here is under the radical. Delta squared minus 4km will determine what type of roots we have. The roots will be complex conjugates if delta squared is less than 4km, real and repeated if delta squared equals 4km, and real and distinct if delta squared is greater than 4km. These three cases are going to be our cases 2, 3, and 4. Now, because each of the coefficients m, delta, and k is positive, these roots will either be negative or, when they're complex conjugates, have negative real part. This is a very important observation because it tells us that the solution of the differential equation will always have a decaying exponential factor. Now let's think about case 2. That's when delta squared is positive and less than 4km. This is the so-called underdamped case, and since delta squared is less than 4km, the quantity under the radical in our formula for the roots is negative, and so we can write the roots as minus delta plus and minus I times the square root of 4km minus delta squared divided by 2m. Notice we've negated the quantity under the radical, making it positive by reversing the terms. So we can express our solution as y equals e to the minus delta over 2m times t times c1 cosine beta t plus c2 sine beta t, where beta is the square root of 4km minus delta squared, all divided by 2m. This may also be written in the form a times e to the minus delta over 2m times t times sine of beta t plus phi naught. Here's the graph of a typical such solution. The mass experiences damped oscillation. Notice that the curve oscillates between the graphs of plus and minus a times e to the minus delta over 2m times t. Those two curves form what is sometimes called an envelope for the oscillation. The constant a here is just the y-intercept of that top curve, and if we follow the solution backwards in time to the first negative 0 where the derivative is positive, we'll arrive at minus phi naught divided by beta. In other words, this is the graph of a times e to the minus delta over 2m times t times sine beta t shifted to the left by phi naught divided by beta. Now case 3. This is where delta squared equals 4km, and this is called the critically damped case. The characteristic equation has repeated real roots, each being equal to minus delta over 2m. So the general solution of the differential equation is y equal to a general linear polynomial c1 plus c2 times t times e to the minus delta t over 2m. In case 4, delta squared is greater than 4km, and this is called the overdamped case. The characteristic roots, r1 and r2, are real and distinct and negative, and the general solution of the differential equation can be written as c1 e to the r1t plus c2 e to the r2t. There's essentially no qualitative difference in these two cases. In each of them, the solution decays exponentially to 0 without oscillation, going through 0 at most once. In fact, for both types of functions, the graph crosses the t-axis exactly once, but depending upon c1 and c2, it may do that at a negative t. Now let's look at an example. A cart with mass 25 kilograms is attached to a spring with stiffness 5 newtons per meter, and the other end of the spring is fixed. The wheels of the cart provide a damping force of minus 30 newtons per unit of velocity. The cart is released, with zero velocity, from a position at which the spring is stretched 2 meters. A. Solve for the resulting motion of the cart, and B. Solve for the motion if an additional mass of 425 kilograms is loaded onto the cart. For part A, our initial value problem consists of the differential equation 25y double prime plus 30y prime plus 5y equals 0, along with initial conditions y of 0 equals 2 and y prime of 0 equals 0. So our characteristic equation is 25r squared plus 30r plus 5 equals 0, which we can divide by 5 and rewrite as 5r squared plus 6r plus 1 equals 0. So the characteristic roots, r1 and r2, are given by the quadratic formula as minus 6 plus and minus the square root of 36 minus 20, all divided by 10. Those are minus 6 plus and minus the square root of 16, or 4, all divided by 10. With the minus sign, we get minus 1, and with the plus sign, we have minus 2/10, or minus 1/5. So the general solution of the differential equation is y equals c1 e to the minus 1t plus c2 e to the minus 1/5 t. Now let's go ahead and compute the derivative. Y prime is minus c1 e to the minus t minus 1/5 c2 e to the minus t over 5. The initial condition y of 0 equals 2 tells us that c1 plus c2 must equal 2, and the initial condition y prime of 0 equals 0 tells us that minus c1 minus 1/5 c2 equals 0. We can eliminate c1 by simply adding the equations together. That gives us 4/5 c2 equals 2, and so c2 equals 5/2. Now we go back to the first equation, c1 plus c2 equals 2. That tells us that c1 equals 2 minus c2, and so c1 is 2 minus 5/2, which is minus 1/2. Now the solution of our initial value problem, after factoring out 1/2, is 1/2 of minus e to the minus t plus 5 times e to the minus t over 5. Here's the graph of that solution. Notice that there's so much damping that the cart simply rolls slowly back toward its equilibrium position without going through it. Now for part B, recall that our mass now becomes the original 25 kilograms plus an additional 425 kilograms for 450 kilograms total. So our initial value problem is the same as before, except the coefficient of y double prime is now 450. So our characteristic equation is 450r squared plus 30r plus 5 equals 0. And again, we'll divide by 5, which gives us 90r squared plus 6r plus 1 equals 0. Now the characteristic roots are minus 6 plus and minus the square root of 36 minus 360, all divided by 180. The number under the radical here is 36 minus 360, which is negative 324. And since 324 is 18 squared, our roots are minus 6 plus and minus 18i divided by 180. Now simplifying a bit gives us minus 1 over 30 plus and minus 1/10 I. So our real part is minus 1 over 30, while the imaginary parts are plus and minus 1/10. Consequently, we can write the general solution of the differential equation as e to the minus t over 30 times c1 cosine of 1/10 t plus c2 times the sine of 1/10 t. Or, alternatively, a times e to the minus t over 30 times sine of 1/10 t plus v naught. We'll go ahead and take the derivative. Using the product rule, y prime will be a times two terms that have e to the minus t over 30 as a factor. The first term, in which we differentiate e to the minus t over 30, will be
minus 1 over 30 times e to the minus t over 30 times sine of t over 10 plus v naught. And the second term will be e to the minus t over 30 times 1/10 of cosine t over 10 plus v naught. Let's factor out 1 over 30, which makes the quantity in parentheses become minus sine of t over 10 plus v naught plus 3 times cosine of t over 10 plus v naught. Now the initial condition y of 0 equals 2 tells us that a times sine of phi naught equals 2, and y prime of 0 equals 0 tells us that 1 over 30 times a times minus sine phi naught plus 3 cosine phi naught equals 0. Now we need to do a little work here before we square and add. We need to eliminate the sine term from the second equation. Let's first multiply the second equation by 30. Then we can simply add the two equations together to eliminate the sine term. The result is 3a cosine of phi naught equals 2, and then dividing by 3 gives us a cosine phi naught equals 2/3. So in the usual way now, a squared will equal 2 squared plus 2/3 squared, which turns out to be 40 over 9, and so a is the square root of 40 divided by 3, or 2 root 10 divided by 3. That number is approximately 2.11. So we can write our solution as y equals 2 root 10 over 3 times e to the minus t over 30 times sine of 1/10 t plus phi naught. And since we know that sine and cosine of phi naught are both positive, phi naught is a first quadrant angle, which can be expressed simply in terms of inverse sine or inverse cosine. So let's write phi naught equals inverse sine of 2 divided by a, which is the inverse sine of 3 over root 10, which is approximately 1.25, or about 72 degrees. Now the actual time shift here is phi naught divided by omega, which is 10 phi naught, which turns out to be about 12.5 seconds. Here's the graph of the solution. Notice the 12.5 second time shift. So what we've seen here is that with a greater mass, the cart has sufficient momentum to push it through its equilibrium position, resulting in oscillatory motion. Mechanical Vibrations Part 2, Forced Vibrations and Frequency Response. We're concerned here with spring mass systems subjected to periodic external forces. Specifically, we want to describe a system's response to a sinusoidal force in terms of the frequency of the force. We can assume that the force is a simple sine function, as in the equation my double prime plus delta y prime plus ky equals k times sine gamma t. We refer to sine gamma t here as the input to the system and gamma as the angular input frequency. The input frequency is gamma over 2 pi. The input has the same units as the solution and may be viewed as the position function of the opposite end of the spring. Any particular solution of the differential equation represents a response to that input. In most cases, there will be a particular solution of the form y equal to a constant g times sine of gamma t plus phi. Here g and phi are the gain and phase angle of the system at angular input frequency gamma. Now, of course, g is just the amplitude of the response. In general, gain is the ratio of the amplitude of the response to the amplitude of the input. In other words, it's an amplification factor. But here, since we're assuming that the input has amplitude 1, the gain is equal to the amplitude of the response. The undamped case. Here delta is 0 and our equation is m times y double prime plus k times y equals k times sine gamma t. We divide by m and rewrite the equation as y double prime plus omega squared y equals omega squared times sine gamma t, where omega is the square root of k over m. Since vibrations of the corresponding unforced system have angular frequency omega, we call omega the system's natural angular frequency. If gamma is not equal to omega, then a particular solution of this equation is y equal to omega squared divided by omega squared minus gamma squared times sine gamma t. This is easy to find using the method of undetermined coefficients. Notice that the coefficient omega squared over omega squared minus gamma squared will be positive if gamma is less than omega and negative if gamma is greater than omega. So the amplitude of this response in general is the absolute value of that coefficient. In fact, this response can be written as y equal to g times sine of gamma t plus phi, where g equal to omega squared divided by the absolute value of omega squared minus gamma squared is the gain of the system at input frequency gamma over 2 pi, and the corresponding phase angle or phase lag is phi equal to 0 if gamma is less than omega and pi if gamma is greater than omega. Note that sine of gamma t plus pi is the same as minus sine gamma t, which makes up for the minus sign we lose when we replace the coefficient of the sine function with its absolute value. Now, since phi is either 0 or pi, depending on whether gamma is less than or greater than omega, we say that the response is either in phase or 180 degrees out of phase with the input. Now, here's a little animation that illustrates the situation when the input frequency is less than the natural frequency of the system. Notice that the motion of the mass is in phase with the motion of the other end of the spring. Also, the amplitude of the motion of the mass seems to be a little bit greater than the amplitude of the motion of the other end of the spring, so the gain would be a little bit bigger than 1. Now let's compare that with an animation where the input frequency is greater than the natural frequency. Here, the motion of the mass is 180 degrees, or completely out of phase, with the motion of the other end of the spring. And again, it appears that the gain is not too far from 1. Now, another important thing to notice about the formula for the gain is that for values of gamma that are large relative to omega, the gain will be small. In fact, the gain approaches 0 as gamma approaches infinity. That's what we see in this animation, where the input frequency is much greater than the natural frequency. Again, the phase angle is 180 degrees, but notice the small amplitude motion of the mass relative to that of the other end of the spring. The solution that satisfies 0 initial conditions, y of 0 equals y prime of 0 equals 0, represents motion that results solely from the external force. That solution is y equal to omega squared divided by omega squared minus gamma squared times sine gamma t minus gamma divided by omega times sine omega t. Note that the sine omega t term here is merely part of the solution of the reduced equation with a coefficient chosen to make the value of the derivative at 0, 0. Now we know that this makes no sense when gamma is equal to omega, so let's suppose that gamma is approximately equal to omega, one consequence of which is that the amplitude of the solution would be large, but there's another interesting phenomenon that occurs. Now let's rewrite the solution by essentially subtracting and then adding sine omega t inside the parentheses. Now let's focus on sine gamma t minus sine omega t. A sum to product formula from trigonometry tells us we can rewrite this as 1/2 of sine of gamma minus omega divided by 2 times t times cosine of gamma plus omega over 2 times t. Also, since the coefficient of the third term in the parentheses, 1 minus gamma over omega, is equal to omega minus gamma all divided by omega, when we multiply through by the coefficient on the outside, we can cancel a factor of omega minus gamma, resulting in omega over omega plus gamma times sine omega t. And let's notice that the closer gamma is to omega, the larger the amplitude of the first term here will be, while the second term will have an amplitude that simply gets closer and closer to 1/2. Consequently, the first term is the dominant one as far as the behavior of the solution is concerned.
In fact, the first term is a solution of the differential equation with a different initial value for y prime. So let's examine the first term. Since we're assuming that gamma is close to omega, the frequency of the cosine factor is much larger than the frequency of the sine factor. So we can view the cosine factor as a high-frequency oscillation that takes place within a low-frequency envelope given by the other factors. Here's a graph that's typical of this type of solution. What we're seeing here is a phenomenon often called beats. Here's an animation in which beats occur in a spring mass system. The upper end of the spring continues to move according to a simple sine function with a frequency close to the natural frequency, and the amplitude of the motion of the mass first increases and then decreases until the mass seems to come to a stop before starting all over again. When vibrations occur in the audible range, one can hear beats when two tones are played simultaneously with frequencies that are close to each other. The sound you're about to hear consists of two simultaneously played tones, one with frequency 220 cycles per second and the other with frequency 222 cycles per second. This results in two audible beats per second. We've seen that beats occur when gamma is close to omega, but what happens if gamma is equal to omega? In that case, a particular solution is given by y equals minus 1/2 times omega t times cosine omega t, which we can rewrite in terms of the sine function as 1/2 omega t times sine of omega t minus pi over 2. So we have oscillations at the natural frequency of the system that are 90 degrees out of phase with the input and have linearly increasing amplitude. This is what's known as resonant response to input at the system's natural frequency. Here's an animation of a spring mass system that's forced at its own natural frequency with a fairly low amplitude input. Notice that the amplitude of the response gradually increases. This would continue until it reached the point at which the spring could not be compressed any further. Now let's consider the damped case. We'll begin with an example in which all system parameters are fixed except the mass m. For the forced system, my double prime plus y prime plus 10y equal to 10 times sine 5t, find a. the gain and phase shift in terms of the mass m, and b. the value of m that maximizes the gain. We'll begin by finding a particular solution, or response, in the form of y equal to c1 cosine 5t plus c2 sine 5t. When we substitute that into the expression my double prime plus y prime plus 10y, we'll have three terms involving cosine 5t and three terms involving sine 5t. My double prime gives us minus 25m times c1 cosine 5t and minus 25m c2 times sine 5t. Y prime gives us minus 5c1 sine 5t and 5c2 cosine 5t. And 10y gives us 10c1 cosine 5t plus 10c2 sine 5t. So the coefficient of cosine 5t is 10 minus 25m times c1 plus 5c2, and the coefficient of sine 5t is minus 5c1 plus 10 minus 25m times c2. And in order for y to be a solution of the differential equation, the coefficient of cosine 5t must be 0, and the coefficient of sine 5t must equal 10. So we have those two equations for C1 and C2. Let's first simplify by dividing through each one of them by 5. That gives us 2 minus 5m times C1 plus C2 equals 0, and minus C1 plus 2 minus 5m times C2 equals 2. We can eliminate C2 by multiplying the first equation by 2 minus 5m and then subtracting the second equation from the first. That gives us 2 minus 5m squared plus 1 times C1 equal to minus 2. Next, we'll eliminate C1 by multiplying the second equation by 2 minus 5m and then adding. That gives us 2 minus 5m squared plus 1 times C2 equal to 2 times 2 minus 5m. So C1 equals minus 2 divided by 2 minus 5m squared plus 1, and C2 is 2 times 2 minus 5m divided by the same denominator. Now we can compute the gain g from the formula square root of C1 squared plus C2 squared. Now C1 squared and C2 squared will have the common denominator 2 minus 5m squared plus 1 quantity squared, and so the square root of that will be the denominator of g, and that's simply 2 minus 5m squared plus 1. And the numerator will be the square root of 2 squared plus 2 squared times 2 minus 5m squared. Now notice that we can factor 4 from the two terms under the radical, and the square root of that will give us a factor of 2, and the other factor in the numerator will then be the square root of the denominator. And so we can simplify to get g equal to 2 divided by the square root of the square of 2 minus 5m plus 1. Now let's write down the sine and the cosine of the phase angle. Sine of phi equals c1 divided by g, and that ends up being minus 1 divided by the square root of the square of 2 minus 5m plus 1. Cosine of phi is c2 divided by g, and that ends up being 2 minus 5m divided by the same denominator. Now notice that sine phi is always negative, and cosine of phi is positive or negative according to whether 2 minus 5m is positive or negative. So in every case, phi is either a third or fourth quadrant angle. And we can describe phi very simply by specifying its tangent. Sine phi over cosine phi is 1 over 5m minus 2, and then simply stipulating that phi is a third or fourth quadrant angle, and we may as well take that to be a negative angle between minus pi and 0. Now part B of our problem is to find the mass m for which the gain is a maximum. Because of the form of g, we really don't even need calculus to find that. To maximize g, we need simply to minimize its denominator, and we can minimize its denominator by just minimizing what's under the radical, 2 minus 5m quantity squared plus 1. Now that simple quadratic is already in the form of the sum of two perfect squares, and so it will be a minimum when the first term is 0, and that happens when m is 2/5. And by substituting m equals 2/5 back into the gain, we find that the maximum gain is 2. So when the mass is 2/5, the system doubles the amplitude of the input. In fact, here's the graph of g versus the mass m for values delta equal to 1, k equals 10, and angular input frequency gamma equal to 5. Let's now look at the general damped case. My double prime plus delta y prime plus ky equal to k times sine of gamma t, where m, delta, k, and gamma are all positive parameters. We'll look for our response in the form of c1 cosine gamma t plus c2 sine gamma t, and the calculations here are going to be very similar to the calculations that we did in the previous example. My double prime plus delta y prime plus ky will consist of 3 terms with cosine gamma t as a factor and 3 terms with sine gamma t as a factor. From my double prime, we get minus m gamma squared c1 times cosine gamma t and minus m gamma squared c2 sine gamma t. Delta y prime contributes minus delta gamma c1 sine gamma t and delta gamma c2 cosine gamma t. And k times y is kc1 cosine gamma t plus kc2 sine gamma t. So the coefficient of cosine gamma t is k minus m gamma squared times c1 plus delta gamma c2, and the coefficient of sine gamma t is k minus m gamma squared times c2 minus delta gamma c1. We want the coefficient of sine gamma t to equal k, and the coefficient of cosine gamma t to equal 0. To eliminate C2, we'll multiply the first equation by delta gamma and the second equation by k minus m gamma squared before subtracting the first equation from the second, and we eliminate C1 by multiplying the first equation by k minus m gamma squared and the second equation by delta gamma, and then adding. So we'll end up with C1 equal to minus K delta gamma divided by the square of K minus M gamma squared plus delta squared gamma squared, and C2 equal to K times K minus M gamma squared divided by the same denominator. Now we'll write down Y. Remember, it's C1 cosine gamma t plus C2 sine gamma t. So there will be a common factor equal to K divided by the square of K minus M gamma squared plus delta squared gamma squared. And since there's a minus sign in front of C1, we'll write K minus M gamma squared times sine gamma t first, and then minus delta gamma cosine gamma t. Now this is equal to G times sine gamma t plus phi, where G is the square root of C1 squared plus C2 squared, which we write by first writing down the square root of the square of the common factor in C1 squared and C2 squared, and then multiplying by the square root of the square of K minus M gamma squared plus delta squared gamma squared. Now the quantity under the radical here is the same as the denominator in the first factor, and so we can rewrite this as K divided by the square root of the square of K minus M gamma squared plus delta squared gamma squared. Now let's write down the sine and cosine of our phase angle. Sine phi is C1 divided by G, which turns out to be minus delta gamma divided by the same denominator as G. Cosine phi, which is C2 divided by G, ends up being K minus M gamma squared divided by that same denominator. Now we notice that sine of phi is always negative, and cosine of phi is positive or negative depending upon whether K minus M gamma squared is positive or negative. So phi will either be a third or fourth quadrant angle. We can describe phi more simply using the tangent function. Tangent of phi will be minus delta gamma divided by K minus M gamma squared, which equals delta gamma divided by M gamma squared minus K, and phi is a third or fourth quadrant angle, which we'll take to be between minus pi and 0. Note that phi equal to minus pi or 0 only occur when sine phi is 0, and we can think of that as corresponding to the undamped case, delta equal to 0. So we now have general formulas that give the gain and phase angle of a given system at input frequency gamma over 2 pi. Now if we think of the system parameters m, delta, and k as fixed, and plot g and phi as functions of the angular input frequency gamma, we obtain what's known as a Bode plot. This is a plot that describes the frequency response of the system. Actually, we'll plot g and minus phi versus gamma, since our phi has negative values, and furthermore, we'll mark the minus phi axis in degrees. The plot you see here is typical. We won't go through the details here, but the maximum gain will occur when gamma is equal to the square root of k over m minus delta squared over 2m squared, provided that the quantity under the radical there is positive. Otherwise, g is strictly decreasing and is always less than 1. A phase angle of 90 degrees will correspond to tangent phi being undefined, which happens when the denominator m gamma squared minus k is 0, which happens when gamma is the square root of k over m. Recall that that is the natural angular frequency of free vibrations of the undamped system with the same values of m and k. Also notice that the input frequency that maximizes the gain is always less than the input frequency that causes a phase angle of 90 degrees. In fact, when the gain is at a maximum, the corresponding phase angle is less than 90 degrees. The Laplace transform, Part 1. Definition. Given a function f of t defined for t greater than or equal to 0, its Laplace transform, capital F of s, is defined as the improper integral from 0 to infinity of e to the minus st times f of t dt, provided that the improper integral converges for all sufficiently large s, which will be the case if the function f has the property that its absolute value is bounded above by an expression m times e to the kt for some constants m and k. This is basically just a condition that guarantees that the function f has a Laplace transform. It says that such functions are bounded on any bounded interval and grow no faster than exponentially as t goes to infinity. Such a function is said to be of exponential order. This is not really something we have to worry much about, since all the functions that we will be working with will have this property. Now let's also point out the way the notation here works. Notice that the symbol for the Laplace transform is the uppercase version of the letter that denotes the function. So the Laplace transform of a function g of t would be capital G of s, the transform of y of t would be capital Y of s, and so on. Also, using the letter s for the argument of the transform is a very common convention. Now let's look at an example of a Laplace transform. Consider the function f of t equal to 1. Its Laplace transform, capital F of s, is the improper integral from 0 to infinity of e to the minus st times 1 dt. We'll antidifferentiate e to the minus st with respect to t, getting minus 1 over s times e to the minus st, and evaluate that between 0 and infinity, where of course evaluating at infinity means taking the limit as t goes to infinity. That limit is 0 provided that s is positive, and the value of e to the minus st at t equal to 0 is of course 1, so we have minus 1 over s times 0 minus 1, which equals 1 over s, and this calculation is valid for all positive s. Another example. Here's the Laplace transform of f of t equal to e to the at. Capital F of s equal to the integral from 0 to infinity of e to the minus st times e to the at dt. To do the antidifferentiation, we'll combine the two factors here and write the integrand as e to the a minus s times t, and so our antiderivative is 1 over a minus s times e to the a minus s times t, which will evaluate from t equals 0 to infinity. The limit of e to the a minus s times t as t goes to infinity will be 0 if a minus s is positive, otherwise the limit won't exist, and of course the value at t equal to 0 will be 1. So we have 1 over a minus s times 0 minus 1, which equals 1 over s minus a. And this is valid if a minus s is positive, or in other words, if s is greater than a. Now let's note that capital F of s is the result of applying a linear operator L to the function f of t. So we'll denote the Laplace transform of f of t using operator notation by writing L of f of t of s. We'll typically read that symbol as simply the Laplace transform of f of t. Now in this notation, the result of the last example may be written Laplace transform of e to the at is a function of s equal to 1 over s minus a. This Laplace transform operator L has the same linearity properties that the integral has. The transform of a constant times f of t is equal to that constant times the transform of f of t, and the transform of the sum of any two functions is equal to the sum of their Laplace transforms. So, for example, having already calculated that the Laplace transform of the constant function f of t equals 1 is 1 over s, we can now conclude that the transform of any constant function f of t equals c is equal to c times 1 over s. Here's another example. Let's say that we want to know the Laplace transform of 3 times e to the minus t minus 2 times e to the minus 4t. Because of our linearity properties, we know that this is the same as 3 times the Laplace transform of e to the minus t minus 2 times the Laplace transform of e to the minus 4t. Now, since we already have a formula that tells us that the transform of e to the at is 1 over s minus a, we have 3 times 1 over s plus 1 minus 2 times 1 over s plus 4. Now we can combine those terms over a common denominator, s plus 1 times s plus 4, And after a little simplifying, we have s plus 10 divided by s squared plus 5s plus 4. The transform of a derivative. Here's where we get to the heart of why the Laplace transform is useful for solving differential equations. The question we want to answer here is, given a function y of t with Laplace transform capital Y of s, what can we say about the transform of y prime of t? In particular, can we express the transform of y prime in terms of the transform of y itself, capital Y of s? It turns out the answer is yes, and it's really all about integration by parts. The transform of y prime is the integral from 0 to infinity of e to the minus st times y prime of t dt. To integrate this by parts, we'll set u equal to e to the minus st and dv equal to y prime of t dt. That makes du equal to minus s times e to the minus st dt, and v is simply equal to y. So, using the formula uv minus the integral of v du, we have e to the minus st times y of t, which will evaluate from t equals 0 to infinity, minus the integral from 0 to infinity of v du, which is minus s times e to the minus st times y of t dt. Now we're assuming that y of t is of exponential order, so as t goes to infinity, e to the minus st times y of t goes to 0, and from that we subtract the value of that product at t equals 0, which is 1 times y of 0. Since the integral that comprises the second term is done with respect to t, s is treated as a constant, and so the factor s can be brought out in front of the integral. And once we do that, the integral is precisely the Laplace transform of y of t. So we found that the Laplace transform of y prime is equal to s times the transform of y minus the value of y at 0. So notice that the Laplace transform changes differentiation into multiplication by s followed by subtraction of the initial value. We can get a similar formula for the transform of the second derivative by basically applying this formula twice. One application of the formula says that the transform of y double prime is equal to s times the transform of y prime minus the value of y prime at 0. There we're just using the basic formula, except with y prime in place of y. Now we use the formula to write down the transform of y prime in the first term. We get s times the quantity s times capital Y of s minus y of 0 minus y prime of 0. Now we multiply out that first term, and we have that the Laplace transform of y double prime is equal to s squared times the transform of y minus s times y of 0 minus y prime of 0. In fact, a general formula for the Laplace transform of the nth derivative of y is as follows. We begin with s to the nth power times the transform of y, and then subtract s to the n minus 1 power times y of 0, s to the n minus 2 power times y prime of 0, and so on down to s to the 0 power times the n minus first derivative of y at 0. Notice that in these extra terms involving y and its derivatives at 0, the powers on the s factors decrease, while the order of the derivative that's evaluated at 0 increases. In fact, those numbers add up to n minus 1 in every term. Now let's look at an example in which we use this result to compute a transform. Let's find the Laplace transform of the function sine omega t. Now, of course, we could do this using the definition of the transform. That would be the integral from 0 to infinity of e to the minus st times sine omega t dt, which wouldn't be too difficult to do by hand. We'd either use parts or look it up in a table. But let's instead find that transform by using the fact that sine omega t is the solution of the differential equation y double prime plus omega squared y equals 0 with initial values y of 0 equals 0 and y prime of 0 equals omega. What we're going to do here is take the Laplace transform of both sides of the differential equation and then solve the resulting algebraic equation for the transform capital Y of S. The Laplace transform of the left side of the differential equation will be the Laplace transform of y double prime, which is s squared times capital Y of S minus s times y of 0 minus y prime of 0, plus omega squared times the transform of y. And of course the transform of the right-hand side is just 0. Now since y of 0 is 0 and y prime of 0 is omega, this equation becomes s squared times capital Y of S minus omega plus omega squared times capital Y of S equals 0. Next, by rearranging and factoring, we have s squared plus omega squared times the transform capital Y equal to omega. And so, capital Y of S equals omega over s squared plus omega squared. This is the transform of sine omega t. Now in a similar way, let's find the Laplace transform of cosine omega t. Cosine omega t is the solution of y double prime plus omega squared y equals 0 with initial conditions y of 0 equals 1 and y prime of 0 equals 0. Just as before, transforming each side of the differential equation gives us s squared capital Y of S minus s times y of 0 minus y prime of 0 plus omega squared capital Y of S equal to 0. Next we substitute 1 for y of 0 and 0 for y prime of 0 and get s squared capital Y of S minus s plus omega squared capital Y of S equals 0. Now we rearrange and factor, getting s squared plus omega squared times capital Y of S equal to s. And so the transform capital Y of S is equal to s divided by s squared plus omega squared. This is the transform of cosine omega t. Notice that the denominator is the same as with sine omega t, but now the numerator is s rather than omega. Now let's look at a summary of what we've seen so far in the form of a short table. Each entry in the second column of our table will be the Laplace transform of the corresponding entry in the first column. We have our linearity properties, which can be stated all at once, as indicated here. Next, the transform of y prime of t equals s times capital Y of S minus y of 0. The transform of y double prime of t is s squared times capital Y of S minus y of 0 times s minus y prime of 0. The transform of the constant function 1 is 1 over s. The transform of e to the at is 1 over s minus a. The transform of sine omega t is omega divided by s squared plus omega squared. And the transform of cosine omega t is s divided by s squared plus omega squared. Now let's look at an example that will illustrate how we can use the Laplace transform to solve a linear second-order initial value problem. We'll find the solution of y double prime plus 9y equals 0 with initial conditions y of 0 equals 1 and y prime of 0 equals negative 2. The first step is to find capital Y of S, the Laplace transform of the solution. We do that by taking the transform of both sides of the differential equation. The transform of y double prime plus 9 times the transform of y will equal 0. The transform of y double prime is s squared capital Y of S minus s times y of 0 minus y prime of 0. That plus 9 times capital Y of S equals 0. Now we substitute 1 for y of 0 and negative 2 for y prime of 0 and get s squared times capital Y of S minus s plus 2 plus 9 capital Y of S equal to 0. Next we rearrange, factor the left-hand side, and end up with capital Y of S equal to s minus 2 divided by s squared plus 9. This is the transform of the solution of the initial value problem, and so the question now is, whose transform is this?
Well, it looks like some combination of the transforms of sine 3t and cosine 3t because of the 9 in the denominator. And in fact, if we break it up into two terms, s over s squared plus 9 minus 2 over s squared plus 9, the first term is already recognizable as the transform of cosine 3t. The second term is much like the transform of sine 3t, except the constant in the numerator is not correct. We need to see a 3 in the numerator because the denominator is s squared plus 3 squared. So we make it that way and then adjust by multiplying by minus 2/3. So now we recognize all of capital Y of s as being the Laplace transform of cosine 3t minus 2/3 times the Laplace transform of sine 3t. And of course, that's the same thing as the transform of cosine 3t minus 2/3 of sine of 3t because of linearity. Therefore, our solution, y of t, is equal to cosine of 3t minus 2/3 of sine of 3t. The procedure used here is typical of how the Laplace transform is used to solve an initial value problem. A shift theorem. We're going to look at the Laplace transform of a function of the form e to the at times f of t, where we assume that f of t has a known transform capital F of s. By definition, the transform of e to the at times f of t is the integral from 0 to infinity of e to the minus st times e to the at f of t dt. The product of those two exponential factors can be written as e to the at minus st, or e to the minus s minus a times t. Now we notice that this improper integral is precisely the transform of f with s replaced with s minus a. In other words, it's capital F of s minus a. So we have our result. The Laplace transform of e to the at times little f of t is equal to capital F of s with s replaced with s minus a. Or in other words, the transform of little f shifted by a, which we normally write as capital F of s minus a. Here's a simple example. The Laplace transform of e to the minus t times cosine of 2t is equal to the Laplace transform of cosine 2t shifted by minus 1, that is, with s replaced with s minus minus 1, or s plus 1. The transform of cosine 2t, we know, is s divided by s squared plus 4, so we replace s with s plus 1 in that expression and obtain s plus 1 divided by s plus 1 squared plus 4. With the shift theorem, we can now add a few more entries to our table of Laplace transforms. Now we already know the transforms of sine omega t and cosine omega t, and our shift theorem says that the transform of e to the at times little f of t is capital F of s minus a. That's the transform of little f of t shifted by a. So to write down the transform of e to the at times sine omega t, we take the transform of sine omega t and replace s with s minus a, obtaining omega divided by the square of s minus a plus omega squared. Similarly, the Laplace transform of e to the at cosine omega t is the transform of cosine omega t shifted by a, and that's s minus a divided by the square of s minus a plus omega squared. Example. Use the Laplace transform to find the solution of y double prime plus 4y prime plus 5y equals 0 with initial conditions y of 0 equals 1 and y prime of 0 equals 0. Our first job is to find capital Y of s, the Laplace transform of the solution. Taking the Laplace transform of each term in the differential equation, we get Laplace transform of y double prime plus 4 times the transform of y prime plus 5 times the transform of y equals 0. The transform of y double prime is, as always, s squared times capital Y of s minus s times y of 0 minus y prime of 0. And the transform of y prime is s times capital Y of s minus y of 0. Our initial conditions tell us that y of 0 is 1
and y prime of 0 is 0. So after adding s plus 4 to both sides of the equation and factoring capital Y of s from the remaining terms on the left side, we have s squared plus 4s plus 5 times capital Y of s equal to s plus 4. And so capital Y of s is s plus 4 divided by s squared plus 4s plus 5. So now the question is, whose transform is capital Y of s? To find out, we'll begin by completing the square in the denominator of the transform. S squared plus 4s are the first two terms that we get if we multiply out the square of s plus 2. But squaring s plus 2 gives us a constant term of 4, and we want the constant term to be 5, so we add 1. So capital Y of s is s plus 4 divided by the square of s plus 2 plus 1. That denominator is the denominator in each of the transforms of e to the minus 2t cosine t and e to the minus 2t sine t. In the transform of e to the minus 2t cosine t, the numerator is s plus 2. So let's break this fraction up into two pieces and write it as s plus 2 divided by the square of s plus 2 plus 1 plus 2 divided by the square of s plus 2 plus 1. So we recognize the first term as the transform of e to the minus 2t cosine t, and the second term is 2 times the transform of e to the minus 2t sine t, because the numerator in that transform would be 1. So we're basically done. This tells us that our solution, y of t, is e to the minus 2t times cosine t plus 2 times e to the minus 2t sine t, which we can factor and write as e to the minus 2t times cosine t plus 2 sine t. Let's wrap this up with a sort of schematic that indicates the plan for solving linear initial value problems by means of the Laplace transform. We begin wanting to solve a linear initial value problem for a function little y of t. We use what we know about the Laplace transform of derivatives to obtain an algebraic equation for capital Y of s, the transform of the solution. We then solve that algebraic equation, which is typically an easy thing to do, and we obtain the transform of the solution, capital Y of s. Then we try to identify the function whose Laplace transform is capital Y of s. This last step is often described as finding the inverse transform of capital Y of s. It is also the only one of the three steps here that is really non-trivial. Part 2 of this series on the Laplace transform will focus on the problem of finding inverse transforms. The Laplace transform, Part 2. Let's recall the plan for solving linear initial value problems by means of the Laplace transform from Part 1. Given a linear initial value problem for little y of t, we take the Laplace transform of both sides of the equation to obtain an algebraic equation for the transform of the solution, capital Y of s. We then solve that algebraic equation for capital Y of s. Next, the problem is to determine what function, little y of t, has capital Y of s as its Laplace transform. This amounts to finding the inverse transform of capital Y of s. There is no straightforward formula for computing an inverse transform. The methods that we use typically involve algebraic manipulation together with table lookup. In other words, we try to write capital Y of s in a form which allows us to identify various pieces with known transforms from a table. Inverse transforms. Given a Laplace transform, capital Y of s, we want to identify a continuous function, little y of t, defined for t greater than or equal to 0, such that the Laplace transform of little y is equal to capital Y of s. The function little y of t is the inverse Laplace transform of capital Y of s. We use typical inverse function type notation using a -1 superscript and write y equals the inverse Laplace transform of capital Y, which is equivalent to capital Y equaling the Laplace transform of little y. For instance, We know that the Laplace transform of sine pi t is pi divided by s squared plus pi squared. Therefore, the inverse transform of pi over s squared plus pi squared is sine pi t. One important tool for finding inverse transforms is completion of squares combined with the shift theorem. Here's an example. Let's find y of t given that capital Y of s is equal to s minus 3 divided by s squared plus 6s plus 13. Now what we're going to do is complete the square in the quadratic in the denominator. The first two terms, s squared plus 6s, are the first two terms of the perfect square s plus 3 squared. The constant term that results from s plus 3 squared is 9, so we write plus 9 to complete the square, and then add 4 so that the constant term still equals 13. So capital Y of s is equal to s minus 3 divided by the square of s plus 3 plus 4. And we recall that that denominator is the denominator of the transform of either cosine 2t or sine 2t shifted by negative 3. Now, since there is an s term in the numerator, we need to have s plus 3 to go with the s plus 3 squared in the denominator. So let's write s plus 3 divided by the square of s plus 3 plus 4, and then subtract 6 divided by s plus 3 squared plus 4. Now that first term is exactly like we want to see it. It's the transform of cosine 2t shifted by negative 3. But because of the 4 in the denominator, the second term needs to have a 2 in the numerator. So let's put a 2 in the numerator and then multiply by minus 3 in front of the fraction. Now we can recognize the entire transform as the transform of cosine 2t minus 3 sine 2t shifted by negative 3. And our shift theorem tells us that that's the transform of e to the minus 3t times cosine 2t minus 3 sine 2t. Therefore, the inverse transform, little y of t, is e to the minus 3t times cosine 2t minus 3 sine 2t. Now let's notice what made this a good technique to use in this case. Completing the square in the denominator ended up giving us a denominator of the form something squared plus a positive constant, precisely because the denominator has no real zeros, and in particular, we could not factor the denominator using real numbers. So the general rule is if the denominator cannot be factored, complete the square. Another important tool for finding inverse transforms is expansion by partial fractions. Here's an example. Let's find little y of t given that capital Y of s is s minus 3 divided by s squared plus 7s plus 10. Let's first factor the denominator into s plus 2 times s plus 5. So the transform can be rewritten as some constant a divided by s plus 2 plus some constant b divided by s plus 5. To find a and b, let's first notice that if we multiply through by the denominator s plus 2 times s plus 5, we have s minus 3 equal to a times s plus 5 plus b times s plus 2. A particularly simple way of finding a is to substitute s equals minus 2 into this equation. With s equal to minus 2, the left side, s minus 3, becomes minus 5. The first term on the right is a times minus 2 plus 5, and the second term on the right is b times 0. So the right-hand side equals 3a, and now minus 5 equals 3a tells us that a is minus 5/3. Similarly, substituting s equals minus 5 will give us a very simple equation for b. When s is minus 5, the left side is minus 8, and the right side is a times 0 plus b times minus 5 plus 2, or minus 3b. So minus 8 equals minus 3b, which tells us that b is 8/3. Now 1/3 is a common factor of each of those constants, so we can write our transform capital Y of s as 1/3 times minus 5 over s plus 2 plus 8 over s plus 5.
Now we can easily recognize that 8 over s plus 5 is 8 times the Laplace transform of e to the minus 5t, and minus 5 over s plus 2 is minus 5 times the transform of e to the minus 2t. So our inverse transform, little y of t, is 1/3 times 8e to the minus 5t minus 5e to the minus 2t. We point out that this example is typical of the case in which the denominator of the transform can be factored into non-repeated linear factors. Example: find the inverse transform of capital Y of s equal to 10s squared divided by s plus 6 times s squared plus 9. Our denominator here is already factored into non-repeated linear and irreducible quadratic factors. So capital Y of s can be expanded in partial fractions as a divided by s plus 6 plus a linear polynomial bs plus c divided by the quadratic factor s squared plus 9. Note that each of these terms represents the most general proper fraction with its respective denominator. Now let's multiply through by s plus 6 times s squared plus 9, and we get 10s squared equal to a times s squared plus 9 plus bs plus c times s plus 6. Since the second term on the right-hand side will be 0 when s is minus 6, we should be able to determine a very easily by substituting s equals minus 6 into the equation. Doing that gives us 360 on the left side, a times 45 plus minus 6b plus c times 0 on the right side, which equals 45a. Now 360 equal to 45a tells us that a is equal to 8. Now let's go ahead and put a equals 8 into the previous equation, and we'll use a different technique to determine b and c. Since we want this equation to be true for all s, it must be the case that coefficients of corresponding powers of s must be the same on each side of the equation. So let's first look at the coefficient of s squared on each side of the equation. On the left-hand side, that's clearly 10, and if we were to multiply out everything on the right-hand side, there would be an 8s squared term as well as a bs squared term. So the coefficient of s squared on the right-hand side is 8 plus b. So 10 must equal 8 plus b, which tells us that b equals 2. Note that if we had not already found a by other means, we would only have an equation here involving a and b. Now let's look at the coefficient of s on both sides of the equation. On the left it's 0, and if we were to multiply out the right-hand side, we would have a cs term as well as a 6bs term. So the coefficient of s on the right is c plus 6b, and since b is 2, that equation tells us that 0 equals c plus 12, so c must be minus 12. Now we've already found a, b, and c, but let's check by making sure that the constant terms are the same on each side of the equation. The constant term on the left is 0. Multiplying out the right-hand side would give us 8 times 9 equals 72, as well as a 6 times c term. Now with c equals minus 12, 72 plus 6c is equal to 0, and so we do have the same constant on both sides. So we found out now that capital Y of s is equal to 8 divided by s plus 6 plus 2s minus 12 divided by s squared plus 9. Now let's factor a 2 from everything, which gives us 2 times 4 over s plus 6 plus s over s squared plus 9 minus 6 over s squared plus 9. But because of the 9 in the denominator here, and what we know about the transform of sine 3t, we'd like to see a 3 in the numerator of that term rather than minus 6, so let's just write minus 2 times 3 over s squared plus 9. We can now recognize, using a table as necessary, the inverse transforms of each of the 3 terms in the parentheses. 4 over s plus 6 is the transform of 4 times e to the minus 6t. S over s squared plus 9 is the transform of cosine 3t. And minus 2 times 3 over s squared plus 9 is the transform of minus 2 sine of 3t.
Another differentiation theorem. Here we'll learn about the derivative of a transform. Let's write down the definition of the Laplace transform and take its derivative with respect to s. We'll accept on faith that the differentiation can be done inside the integral. In other words, we assume that we can interchange the operations of integration and differentiation here. The derivative of the integrand with respect to s is minus t times e to the minus st f of t. Now bringing the minus sign out front of the integral and grouping t with f of t makes it clear that this is the negative of the Laplace transform of t times f of t. This tells us that the Laplace transform of t times f of t is minus capital F prime of s, the negative of the derivative of the transform of little f. This result opens the door to many more transforms than we currently have. In particular, we can write down the transforms of powers of t now. The Laplace transform of the function f of t equals t is minus the derivative of the transform of 1. So the transform of t is minus the derivative of 1 over s, and since that derivative is minus 1 over s squared, we get plus 1 over s squared. Now, knowing the transform of t, we can get the transform of t squared. That's minus the derivative of the transform of t, which we've just learned is 1 over s squared. And since the derivative of 1 over s squared is minus 2 over s cubed, we get plus 2 over s cubed. Similarly, the transform of t cubed will be minus the derivative of the transform of t squared, and that ends up being 3 times 2, or 6, divided by s to the fourth. So notice that as we raise the power on t by 1, we also raise the power on the s in the denominator of the transform by 1. In fact, that power is always 1 more than the power of t. Also, the successive differentiations that are done here, together with the minus sign out front, will cause the numerator to be the factorial of the power on t. In fact, a general formula may be written: the Laplace transform of t to the n is equal to n factorial divided by s to the n plus 1. Here n is any non-negative integer. From the point of view of solving differential equations, we get a much more important result when we combine this with the shift theorem. The Laplace transform of t to the n times e to the at is n factorial divided by s minus a to the n plus first power. For example, let's solve y double prime plus 4y prime plus 4y equals 4 times e to the minus 2t, with initial conditions y of 0 equals 1 and y prime of 0 equals minus 6. We begin by taking the Laplace transform of each side of the differential equation. Using the initial values that were given, the Laplace transform of y double prime is s squared capital Y of s minus 1 times s minus negative 6. And the transform of 4y prime is 4 times s times y of s minus 1. And the transform of 4y is, of course, 4 times capital Y of s. All that will equal the transform of the right-hand side, which will be 4 times 1 over s plus 2. Now, when we collect terms involving capital Y of s and factor, we have on the left side the product s squared plus 4s plus 4 times capital Y of s. The terms on the left that don't involve capital Y of s are minus s plus 6 minus 4, or minus s plus 2. So we'll add s minus 2 to both sides of the equation, giving us a right-hand side equal to 4 over s plus 2 plus s minus 2. Combining everything there over a common denominator of s plus 2 gives us a numerator of 4 plus s minus 2 times s plus 2. Now multiplying out that numerator gives us 4 plus s squared minus 4, or simply s squared. Now we also notice that the factor of capital Y of s on the left, s squared plus 4s plus 4, is the square of s plus 2. So dividing both sides by s plus 2 squared gives us capital Y of s equal to s squared over s plus 2 cubed. Now, because there's only one distinct factor in the denominator, it might not occur to us right away to do a partial fraction decomposition here, but in fact, that is what we need to do. If the numerator were constant, this expression would already be its own partial fraction decomposition. But since it's not constant, we can find a partial fraction expansion equal to a constant a over s plus 2 to the first power plus a constant b over s plus 2 squared plus another constant c over s plus 2 cubed. Notice that even though the second and third terms have denominators that involve higher powers of s, the numerators are still constants because the basic factor here, s plus 2, is linear. So let's find a, b, and c. We'll find a by means of a new trick. Instead of multiplying through by s plus 2 cubed to clear out all fractions, let's just multiply through by s plus 2 to the first power. That gives us s squared over the square of s plus 2 equal to a plus b over s plus 2 plus c over s plus 2 squared. Now, if we let s approach infinity, the left-hand side here will approach 1 because the leading terms in both the numerator and denominator are s squared, and the right-hand side will approach a plus 0 plus 0. And so we found that a is equal to 1. We point out that when dealing with repeated linear factors in the denominator, such as we have here, the constant over the first power of that factor in the partial fraction expansion can always be found in this way. Now let's go ahead and take our original partial fraction expansion and multiply through by s plus 2 cubed. That gives us s squared on the left-hand side, and using the fact that a is equal to 1, we have on the right 1 times s plus 2 squared plus b times s plus 2 to the first power plus c. If we substitute s equal to minus 2, the left-hand side equals 4. The first two terms on the right will be 0, and the third term is c, and so c is 4. At this point, we have only b to find, and a simple way to do that is to simply substitute s equal to any convenient value other than minus 2. Using s equals 0 gives us 0 equal to 4 plus 2b plus c, which is 4, and this equation tells us that b is minus 4. So our partial fraction expansion is 1 over s plus 2 minus 4 over the square of s plus 2 plus 4 over the cube of s plus 2. The first term is the transform of e to the minus 2t, and using the result we just obtained, the second term is the transform of minus 4 times t times e to the minus 2t. That same result tells us that 2 divided by s plus 2 cubed is the transform of t squared e to the minus 2t, and so our third term here is the transform of 2 times t squared e to the minus 2t. Transforms of t times sine omega t and t times cosine omega t. According to our differentiation theorem, the transform of t times sine omega t equals minus the derivative of the transform of sine omega t. That's minus the derivative of omega divided by s squared plus omega squared, which is minus omega times minus 1 over s squared plus omega squared quantity squared times the derivative of the denominator 2s. All that gives us 2 omega s over the square of s squared plus omega squared. Similarly, the transform of t times cosine omega t is minus the derivative of the transform of cosine omega t, and that's minus the derivative of s divided by s squared plus omega squared. Now, using the quotient rule, all of this becomes minus something over the square of s squared plus omega squared. In the numerator, we'll have the derivative of the top, which is 1 times the bottom, s squared plus omega squared, minus the numerator s times the derivative of the bottom, and that's 2s. All of this simplifies to s squared minus omega squared over the square of s squared plus omega squared. Now, the first of these transforms has a numerator that's a constant times s. A term of that form may very well arise as part of a partial fraction expansion. However, the second of these transforms, the transform of t cosine omega t, has s squared in the numerator, which we would never have as part of a partial fraction expansion. So what we're missing here is a known transform of the form of a constant divided by the square of s squared plus omega squared. We can obtain that as follows. Let's take 1 over s squared plus omega squared and subtract s squared minus omega squared over the square of s squared plus omega squared. Combining over a common denominator gives us 2 omega squared, a constant, divided by the square of s squared plus omega squared. And the two terms we began with, we know, are the transforms of 1 over omega times sine omega t and minus t times cosine omega t. So we have 3 new table entries. Transforms of t sine omega t, t cosine omega t, and a third formula that, like the first one, is useful for finding inverse transforms of terms that arise in partial fraction expansions. Example. Find the inverse transform of capital Y of s equal to 4 divided by s plus 1 times the square of s squared plus 1. We need a partial fraction expansion of capital Y of s. The s plus 1 factor in the denominator tells us that we need a single term, a constant a, divided by s plus 1, and the squared factor s squared plus 1 requires us to write 2 terms, one with a denominator of s squared plus 1 to the first power and a linear numerator, bs plus c, and another with a denominator of s squared plus 1 squared, also having a linear numerator, ds plus e. We point out that just as all terms associated with a linear factor will have constant numerators, all terms associated with an irreducible quadratic factor will be linear, no matter what power of the factor appears in the denominator of the term. So, let's find our constants a through e. Let's multiply through by s plus 1 times the square of s squared plus 1. That gives us 4 on the left side, and on the right side, a times the square of s squared plus 1 plus bs plus c times s plus 1 times s squared plus 1 to the first power plus ds plus e times s plus 1. Since the second and third terms on the right have s plus 1 as a factor, we can plug in s equals minus 1 and determine a. We get 4 equal to a times 1 plus 1 squared, or 4, plus 0, which tells us that a is equal to 1. Now let's determine the other constants by equating coefficients. The coefficient of s to the fourth on the left side is 0, and if we were to multiply out the right side, there would be an a times s to the fourth term, as well as a b times s to the fourth term. Those are the only s to the fourth terms, and so the coefficient of s to the fourth on the right side is a plus b. So a plus b equals 0, and since we already know that a is 1, b is minus 1. The coefficient of s cubed on the left is 0, and on the right side we would have a bs cubed term as well as a cs cubed term. So b plus c equals 0, and that tells us, since b is minus 1, that c is 1. Now at this point it might be simpler to find d and e by substituting s equals 0 and then some other value of s, but let's continue equating coefficients for the sake of illustration. The coefficient of s squared on the left is 0, and on the right we would have a 2a s squared term, a bs squared term, a cs squared term, and a ds squared term. So the coefficient of s squared on the right is 2a plus b plus c plus d, and using the previous values for a, b, and c, we find out that d is minus 2. The coefficient of s on the left side is 0, and expanding the right-hand side would give us a bs term, a cs term, a ds term, and an es term. So the coefficient of s on the right is b plus c plus d plus e, and using our known values of b, c, and d, we find out that e must equal 2. Now, just to check, let's look at the constant term. On the left, the constant term is 4, and on the right, the constant term would be a plus c plus e. The values that we've found for a, c, and e do in fact add up to 4, so this checks out. So finally, our partial fraction expansion for capital Y of s is 1 over s plus 1 plus minus s plus 1 over s squared plus 1 plus minus 2s plus 2 over the square of s squared plus 1. Now, to identify this with known transforms, let's break apart the second and third terms. The first term here is the transform of e to the minus t. The second term is the transform of minus cosine t, and the third term is the transform of sine t. For the fourth and fifth terms, we'll need the new entries in our table. The fourth term matches perfectly with minus the transform of t times sine t. And the fifth term matches perfectly with our special entry for a constant numerator over a squared quadratic denominator. With omega equal to 1, we have the inverse transform for that term being sine t minus t cosine t. Now finally, we'll simplify a little bit and write our inverse transform as e to the minus t plus 2 minus t times sine t minus 1 plus t cosine t. The Laplace transform, part 3, piecewise defined functions. Piecewise defined forcing functions. The Laplace transform is especially useful for solving initial value problems in which the non-homogeneous term is piecewise defined and/or piecewise continuous. For instance, consider a forced spring mass system initially at rest, governed by the initial value problem my double prime plus delta y prime plus ky equals k times f of t, with y of 0 equal to y prime of 0 equal to 0, and where the forcing function f of t has the following graph. Let's assume that the spring and mass hang vertically, and let's recall that the function f of t here may be thought of as representing the position of the top end of the spring. This f of t with this particular graph indicates that the top end of the spring first moves downward at a constant rate, then instantaneously changes direction and moves upward at the same constant rate until it arrives at its initial position and stops. Here's an animation that shows a damped system with this forcing function. This is fairly representative of the type of problem that we're going to learn how to solve by means of the Laplace transform. The Heaviside unit step function. We define a function u of t to be 0 if t is negative and 1 if t is greater than or equal to 0. This is known as the Heaviside unit step function, or simply unit step function. We're going to find out that any piecewise defined function can be expressed in terms of this unit step function. Let's begin by noticing that we can shift this unit step function horizontally by an amount c by replacing t with t minus c. So u of t minus c jumps from 0 to 1 at c. Now let's think about what happens when we subtract one shift of the unit step function from another. Let's assume that a is less than b and consider u of t minus a minus u of t minus b. When t is less than a, both terms are 0. When t is between a and b, the first term becomes 1 while the second term is still 0. And when t is greater than b, the value of both unit step functions is 1, and so we have 1 minus 1 equals 0. So u of t minus a minus u of t minus b is equal to 1 if t is greater than or equal to a and less than b, and 0 otherwise. Now, for our purposes, it's not particularly interesting exactly what happens at a and b, whether we get a 0 value or a value of 1. So we just want to think of this difference of shifted unit step functions as a kind of characteristic function of the interval from a to b that gives a value of 1 if t is in the interval and 0 if t is not in the interval. And we don't really care much about what goes on at the endpoints. This turns out to be a very important and useful kind of building block for describing lots of different piecewise defined functions. For example, let's consider the function defined by sine of t times u of t minus 2 pi minus u of t minus 3 pi. The factor u of t minus 2 pi minus u of t minus 3 pi is 1 when t is between 2 pi and 3 pi and 0 otherwise. And so this whole product is equal to sine t when t is between 2 pi and 3 pi and 0 otherwise. So its graph corresponds with the t-axis everywhere except between 2 pi and 3 pi, where we see one arch of the sine function. Example. Express the following piecewise defined function in terms of unit step functions. Little f of t equals 0 if t is less than 0, t if t is greater than or equal to 0 and less than 1, 2 minus t if t is greater than or equal to 1 and less than 2, and 0 if t is greater than or equal to 2. Here's the graph of that function. Notice that it's just like the forcing function in the animation that we previously saw. Notice that we can think of this function as the sum of two functions, one of which is 0 outside of the interval from 0 to 1, and the other is 0 outside the interval from 1 to 2. We'll write the first of those functions as t times u of t minus u of t minus 1. That gives us t when t is greater than or equal to 0 and less than 1, and 0 everywhere else. Then we'll add to that 2 minus t times u of t minus 1 minus u of t minus 2. That term equals 2 minus t when t is between 1 and 2 and 0 elsewhere. So we're done. For t between 0 and 1, the first term here equals t and the second term is 0. When t is between 1 and 2, the first term is 0 and the second term equals 2 minus t, and when t is outside both intervals, both terms are 0. We also happen to get the right values at 0, 1, and 2. Now let's simplify this by grouping together the multiples of the three different shifts of the unit step function. We have t times u of t, and multiplying u of t minus 1, we have minus 1 plus 2 minus t, or 2 minus 2t, and multiplying u of t minus 2, we have minus 2 minus t. Now this is a perfectly good way to leave this, but later we're going to see that a particularly nice form for each of these terms is one in which the function multiplying the unit step function is expressed as a function shifted by the same amount as the unit step function. So in particular, the second term here we like to see expressed in terms of t minus 1, and the third term we like to see expressed in terms of t minus 2. So let's rewrite the second term as minus 2 times t minus 1 times u of t minus 1. And take note of the fact that this entire term is the function minus 2t times u of t shifted by 1. And let's write the third term as plus t minus 2 times u of t minus 2. Now that term is the function t times u of t shifted by 2. The point is that whenever it's practical to do so, it's good form to express the function that multiplies u of t minus c in terms of t minus c as well, so that the entire term can be easily identified as some function shifted by c. Here's another example. Express the following piecewise defined function in terms of unit step functions. F of t equals 1 minus t for t greater than or equal to 0 and less than 1, t minus 2 for t greater than or equal to 1 and less than 2, and 0 otherwise. Now, just as in the last example, this function consists essentially of two non-zero pieces. For t between 0 and 1, values will be given by the formula 1 minus t. So we write 1 minus t times u of t minus u of t minus 1. That gives us 1 minus t when t is between 0 and 1, and 0 everywhere else. Between 1 and 2, values are given by the formula t minus 2. So we write t minus 2 times u of t minus 1 minus u of t minus 2. That gives us t minus 2 when t is between 1 and 2, and 0 everywhere else. So the sum of these two pieces will give us 1 minus t when t is between 0 and 1, t minus 2 when t is between 1 and 2, and 0 elsewhere. Now let's gather together terms according to the different shifts of the unit step function. we have 1 minus t times u of t plus 2t minus 3 times u of t minus 1 minus t minus 2 times u of t minus 2. Now let's rewrite the second term so we can view it as a single function shifted by 1. We do that by rewriting 2t minus 3 as 2 times t minus 1 minus 1. And so that second term is the function 2t minus 1 times u of t shifted by 1. The third term is already the way we'd like to see it. That term is the function minus t times u of t shifted by 2. Transforms. Let's suppose we have a function f of t that's defined for t greater than or equal to 0. We may as well assume that the function is 0 for t less than 0, which amounts to the function being multiplied by the unit step function u of t. Now let's shift that function by c and see if we can compute the Laplace transform of that shifted function. Using the definition of the transform, we have that the transform of f of t minus c times u of t minus c is the integral from 0 to infinity of e to the minus st times f of t minus c times u of t minus c dt. Now u of t minus c is 0 when t is less than c and 1 otherwise, so we can rewrite this integral as the integral from c to infinity of the same integrand with u of t minus c replaced by 1. Now let's make a change of variables so that the lower limit of integration is shifted back to 0. Let tau equal t minus c, in other words t equals tau plus c, which tells us that the differential dt is equal to d tau. But most importantly, the limits of integration are now tau equals 0 to infinity, while the integrand becomes e to the minus s times tau plus c times f of tau d tau. We can factor that exponential expression into the product e to the minus cs times e to the minus s tau, and we can bring e to the minus cs outside the integral because it's independent of tau. Having done that, we can now recognize the integral as the Laplace transform of little f. Of course, we could just replace the dummy variable tau with t here if we wanted to, but that's really not necessary. The bottom line is that the Laplace transform of this shifted function is equal to e to the minus cs times the transform of the unshifted function. So when a function that's 0 for negative t is shifted by c, its Laplace transform is multiplied by e to the minus cs. So we have a second shift theorem. The transform of f of t u of t shifted by c is equal to e to the minus cs times capital F of s. Now let's write this in a couple of equivalent forms. If we set phi of t equal to f of t minus c, then f of t is equal to phi of t plus c. Think of phi as f shifted forward by c, which makes f the same as phi shifted backwards by c. Now, in terms of the function phi, the second shift theorem says that the transform of phi of t times u of t minus c is equal to e to the minus cs times the transform of phi of t plus c. This formula is a bit more straightforward to use when computing a transform as opposed to an inverse transform. Another equivalent form is simply the basic formula written in terms of the inverse transform. The inverse transform of e to the minus cs times capital F of s is equal to little f of t minus c times u of t minus c. In general, this is a very straightforward thing to apply. Whenever a known transform is multiplied by e to the minus cs, we simply shift the inverse transform by c and multiply by u of t minus c. Here are two small examples. Let's find the Laplace transform of e to the minus t times u of t minus 2. We'll use the first of the equivalent forms of the shift theorem. Since that unit step function has a shift of 2, we write e to the minus 2s and multiply by the transform of e to the minus t plus 2. Now e to the minus t plus 2 is the same as e to the minus t times e to the minus 2. We can bring that constant factor e to the minus 2 outside the transform, and since the transform of e to the minus t is 1 over s plus 1, we end up with e to the minus 2s divided by e squared times s plus 1. Now let's find the inverse transform of e to the minus pi s over 2 times s over s squared plus 1. Now we recall that s over s squared plus 1 is the transform of cosine t. The e to the minus pi s over 2 factor tells us to take that inverse transform, cosine t, shift it by pi over 2, and multiply by u of t minus pi over 2. Or equivalently, multiply it by u of t and shift the whole thing by pi over 2. Now cosine t shifted by pi over 2 is exactly the same thing as sine t. So we have sine of t times u of t minus pi over 2. Here's another example. Let's find the Laplace transform of the function z of t equal to t times u of t minus 1 minus u of t minus 2. And here's the graph of z of t. Z of t equals t when t is between 1 and 2, and it's 0 elsewhere. We'll first multiply this out and write z of t as t times u of t minus 1 minus t times u of t minus 2. Now we notice that the first term is the function t plus 1 times u of t shifted by 1. So our shift theorem tells us that the transform of that term is e to the minus s times the transform of t plus 1, which is 1 over s squared plus 1 over s. The second term in little z of t is minus t plus 2 times u of t shifted by 2. So its transform is minus e to the minus 2s times the transform of t plus 2, which is 1 over s squared plus 2 over s. So the transform, capital Z of s, can be written over a common denominator of s squared, with the numerator e to the minus s times 1 plus s minus e to the minus 2s times 1 plus 2s. Now it's interesting to note that this result is the same as what we would have gotten by appealing directly to the definition of the Laplace transform. The integral from 0 to infinity of e to the minus st times z of t dt would become the integral from 1 to 2 of e to the minus st times t dt, an integral which we could have computed by parts. Another example. Find the Laplace transform of x of t equal to t squared times u of t minus u of t minus 2. Again, we'll start by multiplying this out, writing t squared times u of t minus t squared times u of t minus 2. The transform of the first term is simply the transform of t squared. Next, we note that the second term is the function minus t plus 2 squared times u of t shifted by 2. So, by our second shift theorem, its transform is minus e to the minus 2s times the transform of t plus 2 squared. Now, to find that transform, we need to multiply out t plus 2 squared. That's t squared plus 4t plus 4. So now we're ready to write down the transform capital X of s. The transform of t squared is 2 over s cubed. Then we have minus e to the minus 2s times the transform of t squared again, plus the transform of 4t, which is 4 over s squared, plus the transform of 4, which is 4 over s. Now we might want to write this over a common denominator of s cubed, but let's just leave it as it is. Another example. Find the Laplace transform of g of t equal to t times u of t minus 2 times t minus 1 times u of t minus 1 plus t minus 2 times u of t minus 2. This is the same function we've seen a couple of times before. To write down its Laplace transform, we'll first write down the transform of t times u of t, which is just the transform of t, which is 1 over s squared. And then we note that the second term is the function minus 2t times u of t shifted by 1. So its transform is e to the minus s times the transform of minus 2t, which is minus 2 over s squared. The third term is t times u of t shifted by 2. and so its transform is e to the minus 2s times the transform of t, which is again 1 over s squared. Now, writing this over a common denominator of s squared, we have a numerator 1 minus 2 times e to the minus s plus e to the minus 2s. Now, we can notice that that numerator is actually a perfect square. It's the square of 1 minus e to the minus s. Another example. Find the Laplace transform of f of t equal to sine t times u of t minus 2 pi minus u of t minus 3 pi. First, we'll expand the product and write it as sine of t times u of t minus 2 pi minus sine t times u of t minus 3 pi. Now we know that the period of the sine function is 2 pi, so sine of t may be rewritten as sine of t minus 2 pi in order to match the t minus 2 pi in the unit step function multiplying it. Also, if we shift the sine function by 3 pi, that's the same as negating the function. So our second term here is the same as plus sine of t minus 3 pi times u of t minus 3 pi. So both terms here now match up perfectly with the original version of the shift theorem. The transform of the first term is e to the minus 2 pi s times the transform of sine t, which is 1 over s squared plus 1. The transform of the second term is e to the minus 3 pi s times the same transform of sine t, 1 over s squared plus 1. Now finally, let's rewrite this over a common denominator. We have e to the minus 2 pi s plus e to the minus 3 pi s, all divided by s squared plus 1. Now here's an example of finding an inverse transform. Let's find little f of t, given that its Laplace transform, capital F of s, is equal to 2 minus 3s plus 2 times e to the minus s plus s times e to the minus 2s, all divided by s cubed. The first thing we'll do is break the fraction apart and rewrite it as 2 over s cubed minus e to the minus s times 3s plus 2 over s cubed, which is 3 over s squared plus 2 over s cubed, plus e to the minus 2s times 1 over s squared. Now we recognize the first term as the transform of t squared. So our first term in little f of t we'll write as t squared times u of t. Note that the u of t factor here isn't totally necessary, but we write it there since we may as well assume that our function is 0 for all negative t. Now we go to the second term. The factor that multiplies the exponential, 3 over s squared plus 2 over s cubed, can be recognized as the transform of 3 times t plus t squared. Now, taking into account the e to the minus s factor, we shift 3t plus t squared by 1 and multiply by u of t minus 1. This gives us minus 3 times t minus 1 plus t minus 1 squared times u of t minus 1. Now in the third term, we see 1 over s squared, which is the transform of t, multiplied by e to the minus 2s. So we shift t by 2 and multiply by u of t minus 2 to get the inverse transform. That's t minus 2 times u of t minus 2. Now we just need to simplify, and then let's think about what the function's graph looks like. F of t equals t squared times u of t minus t squared plus t minus 2 times u of t minus 1 plus t minus 2 times u of t minus 2. Now, of course, this is 0 for all negative t. When t is between 0 and 1, only the first term is non-zero. So, for t greater than or equal to 0 and less than 1, f of t is equal to t squared. When t is between 1 and 2, the third term is 0, and the first and second terms are t squared minus t squared plus t minus 2, which simplifies to 2 minus t. And when t is greater than or equal to 2, all three of the unit step functions here equal 1, and so f of t equals t squared minus t squared plus t minus 2 plus t minus 2, which adds up to 0. Now, having this piecewise form makes it easy to see that the graph of f is the one shown here. One more example. Let's solve the initial value problem y double prime plus y equals f of t with initial conditions y of 0 equal to y prime of 0 equal to 0, where f of t is the function that equals the absolute value of sine t when t is between 0 and 2 pi and 0 otherwise. Here's the graph of little f of t. The first thing we need to do is express f of t in terms of shifted unit step functions. Taking note of the fact that f of t equals sine t between 0 and pi, and equals minus sine t between pi and 2 pi, and equals 0 everywhere else, we first write down a term that equals sine t between 0 and pi and 0 everywhere else. That's sine t times u of t minus pi. Then we add to that a term that equals minus sine t between pi and 2 pi and 0 everywhere else. That's minus sine t times u of t minus pi minus u of t minus 2 pi. Now multiplying out each term and simplifying gives us sine t times u of t minus 2 times sine t times u of t minus pi, which we'll go ahead and write as plus 2 times sine of t minus pi times u of t minus pi, since sine of t minus pi is equal to minus sine t. And we have a third term equal to sine t times u of t minus 2 pi, which is the same as sine of t minus 2 pi times u of t minus 2 pi. Next, we need the Laplace transform of f of t. The transform of the first term is just the transform of sine t, which is 1 over s squared plus 1. Using our shift theorem, the transform of the second term will be 2 times the transform of sine t, which is 1 over s squared plus 1, multiplied by e to the minus pi s. And the transform of the third term is the same 1 over s squared plus 1, this time multiplied by e to the minus 2 pi s. Now let's take the transform of each side of the differential equation. Since our initial conditions are 0, the left side will be simply s squared times capital Y of s plus capital Y of s, and the right-hand side is our transform capital F of s. Now the left side is equal to s squared plus 1 times capital Y of s, so dividing by s squared plus 1 gives us capital Y of s equal to 1 over s squared plus 1 quantity squared times 1 plus 2 e to the minus pi s plus e to the minus 2 pi s. Now we just need to find the inverse transform of capital Y of s. To do that, we first need to identify the inverse transform of 1 over the square of s squared plus 1. Consulting our table reveals that that's 1/2 the transform of sine t minus t times cosine t. So the first term in our inverse transform will be 1/2 of sine t minus t cosine t all times u of t. The second term will be the inverse transform of 1 over the square of s squared plus 1 times 2 e to the minus pi s. The e to the minus pi s factor tells us to shift the inverse transform of 1 over the square of s squared plus 1 by pi and multiply by u of t minus pi. And the e to the minus 2 pi s factor tells us to shift 1/2 of sine t minus t cosine t by 2 pi and multiply by u of t minus 2 pi. Now let's simplify all this a bit. We have a 1/2 factor common to everything. Inside the parentheses, the first term is sine t minus t cosine t times u of t. The middle term is equal to 2 times minus sine t plus t minus pi times cosine t. That's because sine of t minus pi is minus sine t, and cosine of t minus pi is minus cosine t. And the third term is equal to sine t minus 2 pi times cosine t times u of t minus 2 pi. Now let's convert this to piecewise form. For t between 0 and pi, y of t is equal to 1/2 of sine t minus t cosine t. For t between pi and 2 pi, we have sine t minus t cosine t plus 2 times minus sine t plus t minus pi cosine t, which all adds up to minus sine t plus t cosine t minus 2 pi cosine t. Now when t is greater than or equal to 2 pi, all three of our shifted unit step functions equal 1, and it's not difficult to see that everything inside of the big parentheses adds up to 0. Now here's the graph of that solution. It is the response to our original input function f of t. The initial value problem that we solved governs the motion of an undamped spring mass system with natural frequency 1 over 2 pi with forcing function f of t. Here's an animation in which the top end of the spring moves according to the function f of t. That motion is timed perfectly so that the mass actually stops at time 2 pi. Linear algebraic equations, part 1. Here are three typical systems of linear equations. This one consists of two equations and the two unknowns x and y. This one consists of three equations and three unknowns x, y, and z. And this one consists of only two equations and four variables x1 through x4. In this last system, because there are no non-zero constant terms, we say that the system is homogeneous. This is very much like our usage of the term homogeneous when talking about a differential equation. A system of linear equations is said to be consistent if it has a solution, and inconsistent if it has no solution. Note that a homogeneous system is automatically consistent since it will have the trivial solution, that is, a solution in which all variables equal 0. With any system of linear equations, we associate an augmented matrix that contains the coefficients and the non-homogeneous terms of the system. For a system of m equations and n unknowns, the augmented matrix will be m by n plus 1. That is, it will have m rows and n plus 1 columns. For instance, the augmented matrix for this system of two equations and two unknowns consists of the coefficients of the first equation, which are 1 and 3 in the first row, along with the right-hand side of that equation, 0, as the last entry in that row. And in the second row, we have the coefficients of the second equation, 1 minus 1, along with the right-hand side of that equation, which is 3. Notice that we draw a vertical line to separate the coefficients from the non-homogeneous terms in the last column. Also be sure to notice that each row of the matrix corresponds to an equation in the system, and left of the vertical bar, each column corresponds to one of the variables. Here's a system of three equations and three unknowns, and its augmented matrix. Notice that it's constructed in essentially the same way. Each row contains the coefficients of one of the equations along with the right-hand side. And here's a system of two equations and four unknowns, along with its augmented matrix. The m by n matrix left of the vertical bar is the coefficient matrix of the system. So the augmented matrix is the coefficient matrix augmented with an additional column containing the right-hand sides of the equations. A system's augmented matrix serves as a proxy for the system in the sense that manipulations of the equations for the purpose of solving the system may be accomplished by analogous manipulations of the rows of the augmented matrix. Some systems are easy to solve by a method called back substitution. Here are two examples. First, let's look at the equations x plus y minus z equals 3, y plus 3z equals 10, and z equals 2. And here's the augmented matrix for the system. The third equation tells us already that in any solution, the value of z has to be 2. We can solve the second equation for y in terms of z. Y equals 10 minus 3z, and since we already know that z must be 2, y is equal to 10 minus 6, or 4. We can solve the first equation for x in terms of y and z. X equals 3 minus y plus z, and since we know that y is 4 and z is 2, x is equal to 3 minus 4 plus 2, which is 1. Here's a similar example involving a system of three equations and four unknowns. We'll start with the last equation, x3 minus x4 equals 1, and solve that for x3. We get x3 equals 1 plus x4. Now solving the second equation for x2 gives us x2 equals 4 minus x4.
Then solving the first equation for x1 gives us x1 equals x2 minus 2x3, and replacing x2 with 4 minus x4 and x3 with 1 plus x4 ends up giving us 2 plus 3 times x4. So we now have all of the first three variables expressed in terms of the fourth variable x4. There's no more information in the system that we can use to determine a value for x4. In fact, x4 can be any real number, and as long as x1 is 2 plus 3x4, x2 is 4 minus x4, and x3 is 1 plus x4, the system will be satisfied. So in fact, this system has infinitely many solutions. The common structure of these two systems that allowed this method called back substitution to be used is evident in each of the augmented matrices. Any matrix has what we refer to as a main diagonal, consisting of the first entry in the first row, the second entry in the second row, and so forth. Notice that in each of these augmented matrices, there are only zeros below that main diagonal. That means that the coefficient of the first variable in the second equation is 0. The coefficient of the first and second variables in the third equation are both 0, and so forth. That's what allows us to use back substitution, to start with the last equation and work our way back up to the first equation, solving as we go. Definition. A matrix is in echelon form if 1. All rows containing only zeros are at the bottom of the matrix, 2. The first non-zero entry in each row is to the right of the first non-zero entry in all the rows above it, and 3. The first non-zero entry in each row is a 1. This last requirement is optional. Some textbooks use it, others don't. Here are some matrices in echelon form. This 3 by 4 matrix has no row full of zeros, and so property 1 is automatically satisfied. Each row has a leading 1 that's to the right of the leading 1 in each row above it, so properties 2 and 3 are true. Notice that as a result, all of the entries in the matrix below that main diagonal are zeros. This 2 by 4 matrix is in echelon form. Here, the leading non-zero entry in the second row is not on the diagonal. It is, however, to the right of the leading non-zero entry in the first row, which means that property 2 is satisfied. Here's a 3 by 5 matrix in echelon form. Here we have an entire row of zeros. It's at the bottom of the matrix, so property 1 is satisfied, and properties 2 and 3 are true as well. Notice in all three of these examples the downward trending zigzag line below and to the left of which every entry in the matrix is 0. And finally, we point out that a consistent system whose augmented matrix is in echelon form is one that can be solved by back substitution. Now here's our plan for solving linear systems of equations. We'll use elementary operations to reduce the system to one whose augmented matrix is in echelon form. That's a process called Gaussian elimination. Then we'll solve the reduced system by back substitution. So what are these elementary operations? Here's a list of the elementary operations on equations. These are basically the things that we can do to a system of equations to transform the system into another system that has the same set of solutions. We're allowed to multiply an equation by a non-zero constant. We may add a multiple of one equation to another equation, and we may interchange two equations. The corresponding elementary row operations, which we perform on the augmented matrix of a system, are the following. We may multiply a row by a non-zero constant. We may add a multiple of one row to another row, and we may interchange two rows. Notice the correspondence here. We can manipulate the rows of our augmented matrix in exactly the same ways that we're allowed to manipulate the equations in the system. Now let's look at an example. Let's solve this system of three equations and three unknowns. Here's the augmented matrix of the system. What we're going to do here in this first example is work with the equations
and update the augmented matrix as we go along. The first thing we like to do here is to eliminate the x variable from the second and third equations. So we'll leave the first equation alone. We'll subtract the first equation from the second equation, which gives us y minus 5z equals negative 3, and the new second row of the augmented matrix becomes 0, 1, minus 5, minus 3. Notice that we could have gotten that row by subtracting the first row of the matrix from the second. Now, to eliminate the x term from the third equation, we'll subtract 2 times equation 1 from equation 3. That gives us minus 3y minus 5z equals minus 11, and the new third row of the augmented matrix is 0, minus 3, minus 5, minus 11. Now notice that eliminating the first variable from the second and third equations results in zeros below the diagonal entry in the first column. Next, we want to eliminate the y term from the third equation. We'll leave the first and second equations alone, and then add 3 times equation 2 to equation 3. That gives us minus 20z equals minus 20. And the new third row in the augmented matrix is 0, 0, minus 20, minus 20. Now at this stage, we have zeroed out every entry in the augmented matrix below the diagonal in the first 2 columns. Now let's tidy things up a bit by dividing the third equation by minus 20. That makes the third row in the matrix 0, 0, 1, 1. We can now solve the system by back substitution. The third equation says that z is 1. The second equation says that y is minus 3 plus 5z, and since z is 1, y is minus 3 plus 5 equals 2. The first equation says that x is 6 minus 3z, and since z is 1, that's 6 minus 3 equals 3. Now let's do another similar example. Again, it's a system of 3 equations and 3 unknowns, and here's the augmented matrix. This time we're going to work with the rows of the matrix rather than the equations themselves. Our first goal is to get zeros below the diagonal entry in the first column, which is tantamount to eliminating x1 from the second and third equations. So we leave the first row alone. Subtracting the first row from the second row gives us a new second row, 0, 3, minus 4, and 1. Next, we replace the third row with the third row minus the first row, which makes the third row 0, 2, minus 2, 2. Next, let's go ahead and divide the second row by 3 so that we'll have a 1 on the diagonal in the second row. Now we want to have a 0 below the diagonal in the second column. We can do that by subtracting 2 times the second row from the third row. So we leave the first and second rows alone and replace the third row with the third row minus 2 times the second row. Now finally, let's multiply the third row by 3 halves to get a 1 on the diagonal in that row. So now we have an augmented matrix in echelon form, and the equations to which it corresponds are x1 minus x2 plus 3x3 equals 4, x2 minus 4/3 x3 equals 1/3, and x3 equals 2. Now using back substitution, we have x3 equals 2, x2 equals 1/3 of 1 plus 4x3, and since x3 is 2, that's 1/3 of 1 plus 8, or 3. Then x1, which is 4 plus x2 minus 3x3, is equal to 4 plus 3 minus 6, which equals 1. Now, it's always a good idea to go back and check the solution with the original equations, since it's very easy to make arithmetic mistakes when doing so much arithmetic. Here, that's fairly easy to do, and our solution does in fact check out. Here's another example. It's another system of 3 equations and 3 unknowns. And here's the augmented matrix for the system. We begin with the goal of zeroing out the entries below the diagonal in the first column. We'll leave the first row alone. We'll replace the second row with the second row minus the first row. That gives us 0, 3, minus 4, minus 2 as a new second row. Then we'll replace the third row with the third row minus 3 times the first row. That gives us 0, 3, minus 4, minus 5. Now, following the previous examples, We'd like to zero out the entry below the diagonal in the second column, so we'll leave the first and second rows alone and subtract row 2 from row 3. That gives us a new row 3 of 0, 0, 0, minus 3. We have a matrix in echelon form now, and it corresponds to the following system of equations. x1 minus x2 plus 3x3 equals 2, 3x2 minus 4x3 equals minus 2, and 0 times x3 equals minus 3. Actually, there's a 0 coefficient for the other two variables in that equation as well. We just put the 0x3 there for a placeholder. Now, clearly, no values of x1, x2, and x3 are going to make 0 equal minus 3. So there's no solution for this system. Now, why did this happen? What makes this system different from the previous two in terms of the echelon form that we arrived at for our augmented matrix? Well, clearly the problem was that our echelon form contained a row with all zeros to the left of the vertical bar and a non-zero entry in the last column. A convenient way to describe this is to say that the coefficient matrix, that is, the part of the matrix to the left of the vertical bar, has an echelon form with an entire row of zeros, while the full augmented matrix does not. Definition. A matrix is in reduced echelon form if 1. It is in echelon form, 2. The first non-zero entry in each row is a 1, which is redundant if that is included in your definition of echelon form, and 3. The first non-zero entry in each row is the only non-zero entry in its column. Here are a few examples. This matrix is clearly in echelon form. The first non-zero entry in each row is in fact 1. It is in reduced echelon form because of the zeros above the leading ones in the second and third rows. This 2x4 matrix is in echelon form. Each row has a leading 1, and above the leading 1 in the second row we have a 0 entry, and so the matrix is in reduced echelon form. Here's a third matrix in reduced echelon form. Note that in each example, every row that isn't full of zeros has a leading 1 that is the only non-zero entry in its column. We'll see in our examples that we can use elementary row operations to obtain a reduced echelon form, and that once we have a reduced echelon form, property 3 eliminates the need for back substitution. Example. Let's solve this system of 3 equations and 3 unknowns by obtaining a reduced echelon form for its augmented matrix, which we see here. Our first goal is to get zeros in the first column below that leading 1 in the first row. We'll leave the first row alone. We'll replace the second row with itself minus row 1. That gives us 0, minus 1, 0 in that row. Then we'll subtract from row 3 times row 1. That gives us 0, 2, minus 5, 1 as our new third row. Now let's zero out the entry in the third row and second column. And at the same time, let's multiply the second row by minus 1 in order to get a leading positive 1 in that row. Our new third row is now 0, 0, minus 7, 1. Now let's zero out the entry above the leading 1 in the second row. To do that, we'll replace row 1 with row 1 plus row 2. Our new first row is 1, 0, 3, 0. We do nothing to row 2, and we'll go ahead and get our leading 1 in the third row by multiplying by minus 1/7. Now we need to zero out the entries in the third column above the leading 1 in the third row. So we'll subtract 3 times row 3 from row 1, giving us 1, 0, 0, 3/7, and subtract row 3 from row 2, giving us 0, 1, 0, 1/7 in the second row, and we leave row 3 alone. Our matrix is now in reduced echelon form, and it corresponds to 3 very simple equations. x1 equals 3/7, x2 equals 1/7, and x3 equals minus 1/7. So there's nothing more to do. We have our solution. Notice that in this case, where we ended up with a unique solution to our system of equations, the solution was contained in the last column of the reduced augmented matrix. In fact, you could say that the solution is the last column. One more example. Let's solve this system of 3 equations and 4 unknowns. Here's our augmented matrix. As usual, we'd like to have zeros below the first entry in the first column, but since that first entry is a 0, the only way we can accomplish that is to exchange rows. So let's move row 1 down to row 2, and row 2 up to row 1. And we can make the first entry in the third row a 0 by replacing the third row with row 3 minus the old row 2. Now we already have a leading 1 in the second row, and what we want to do now is to zero out all the entries other than that leading 1 in the second column. So we'll replace row 1 with row 1 minus row 2, and replace row 3 with row 3 plus 2 row 2. We now have our reduced echelon form. This time we have arrived at an entire row of zeros in the reduced augmented matrix. Consequently, our system of equations is equivalent to 1 with only 2 equations. x1 plus 2x3 equals 1, and x2 minus x3 plus x4 equals 0. In order to describe the solutions of this system, let's solve the first equation for x1, that gives us 1 minus 2x3, and solve the second equation for x2. x2 is equal to x3 minus x4. These equations give x1 and x2 in terms of x3 and x4, and there's nothing to determine values for x3 and x4, so they may equal any 2 real numbers. Having described our solution this way, we would refer to x3 and x4 as free variables, or parameters. And since there are 2 free variables needed to describe the solution set, we'd say that the solution set is 2-dimensional. Since there are 4 variables here, that 2-dimensional solution set lives in 4-dimensional space, but if it lived in 3-dimensional space, we could visualize it as a plane. Linear algebraic equations, part 2. We have seen that basically 3 outcomes can occur when we solve a system of linear equations. First, the system may have no solution. For instance, here's the augmented matrix for a system of 3 equations and 3 unknowns. Gaussian elimination produces this echelon form, which tells us that this is an equivalent system of equations. The third equation here tells us that the system has no solution. You may recall that we previously talked about this situation in terms of the coefficient matrix having an echelon form with fewer non-zero rows than any echelon form of the augmented matrix. A second possible outcome is that the system may have infinitely many solutions. To illustrate this, let's take our previous augmented matrix and system of equations and simply change the right-hand side of the third equation from 1 to 4. Gaussian elimination on this augmented matrix produces an echelon form with an entire row of zeros. Consequently, our original system is equivalent to one involving just 2 equations. So the system has infinitely many solutions that can be expressed in terms of 1 free variable. The third and last possible outcome is that the system may have a unique solution. To illustrate this, let's go back to our original system and change the coefficient of the third variable in the third equation from 5 to 4. Gaussian elimination then produces this echelon form, which corresponds to a system of equations we can easily solve by back substitution to obtain a unique solution. Some general observations. Suppose that we have a system of m equations and n unknowns, and let U denote any echelon form of the augmented system matrix. 1. The system is consistent if and only if the last column of U does not contain the first non-zero entry in any row. This is just another way of saying that any zero row in an echelon form of the coefficient matrix is part of a zero row in an echelon form of the augmented matrix. For instance, here we have an augmented matrix in echelon form, and the first non-zero entry in the third row is in the last column. This matrix corresponds to a system which has no solution, in other words, an inconsistent system. This is an echelon form of an augmented matrix corresponding to a consistent system. In fact, it's a system that has infinitely many solutions. Here's an echelon form of the augmented matrix for a consistent system of 5 equations and 3 unknowns. In fact, it's a system that has a unique solution. 2. If the system is consistent, then the number of non-zero rows in U plus the number of free variables equals n, the number of unknowns. For instance, here we have an augmented matrix in echelon form. It corresponds to a system of equations with 2 unknowns. It has 1 non-zero row, and we could express the solution of the system using 1 free variable. So we see that the number of non-zero rows plus the number of free variables is equal to the number of unknowns. Here we have an augmented matrix in echelon form that corresponds to a system with 4 unknowns. We have 2 non-zero rows, and we can express the solution using 2 free variables. And this is an echelon form of the augmented matrix for a system of equations with 3 unknowns. There are 3 non-zero rows, and the system has a unique solution, so the number of free variables is 0. Now, because of this identity, and the fact that we have infinitely many solutions whenever there's 1 or more free variables, we can state that if the system is consistent, then it has a unique solution if the number of non-zero rows in U is equal to n, the number of unknowns, and infinitely many solutions if the number of non-zero rows in U is less than n. Another observation that follows from the previous one is that if m is less than n, that is, if the number of equations is less than the number of unknowns, and the system is consistent, then it has infinitely many solutions. Such a system, one in which the number of equations is less than the number of unknowns, is called an underdetermined system. All that's going on here is that if the number of rows in the augmented matrix is less than the number of unknowns, then it's impossible for the number of non-zero rows in the matrix to equal the number of unknowns. For instance, here we have an echelon form of the augmented matrix for a system of 2 equations and 3 unknowns. There are 2 non-zero rows, and the system is consistent, and so we'll need to use 1 free variable when we describe the solutions of the system. This matrix corresponds to a consistent system of 3 equations and 4 unknowns. It has the maximum number of 3 non-zero rows, and the solutions would be described using 1 free variable. And finally here, we have an echelon form for the augmented matrix of a system of 2 equations and 4 unknowns. There's only 1 non-zero row, meaning that the solutions would be described using 3 free variables. 5. If m equals n, that is, if the number of equations is equal to the number of unknowns, then the system has a unique solution if and only if each diagonal entry in U is non-zero. Note that the alternative to having a unique solution consists of 2 possibilities. 1, that there's no solution, and 2, that there's infinitely many solutions. Here we have an augmented matrix in echelon form corresponding to a system of 3 equations and 3 unknowns. There are no zeros on its diagonal, which makes it impossible for the system to be inconsistent or to have any 0 rows. Consequently, the system must have a unique solution. Here we have a matrix corresponding to a system of 2 equations and 2 unknowns. Notice that it's inconsistent, something that's made possible by the fact that we have a 0 on the diagonal in the second row. And finally here we have a matrix corresponding to a system of 3 equations and 3 unknowns. The system is consistent, and since there's an entire row of zeros, we would describe the solutions using 1 free variable, and so there'd be infinitely many solutions, something that would not happen without having 0 on the diagonal in that third row. We're now going to talk a bit about homogeneous systems. We'll try to illustrate our points with a couple of examples. Let's first consider this homogeneous system. Here's the augmented matrix for the system. The first thing we want to point out is that the system automatically has one solution, the one with x equals 0, y equals 0, and z equals 0, which we refer to as the trivial solution. So the main issue here is whether or not the system has any non-trivial solutions. Also, since the last column of the augmented matrix contains only zeros, it will continue to contain only zeros throughout our row reduction process. So, we need only row reduce the coefficient matrix. So let's go ahead and do that and see what our reduced echelon form looks like. To zero out the entries in the first column below the diagonal, we'll leave row 1 alone, subtract row 1 from row 2, and subtract 2 times row 1 from row 3. Then, to zero out the off-diagonal entries in the second column, we'll add 1/3 of row 2 to row 1, and replace the third row with 3 times the third row minus 5 times the second row. It's clear now that we're not going to obtain a row of zeros, and that by adding an appropriate multiple of row 3 to row 1 and row 2, we can zero out the off-diagonal entries in the third column. Now finally, by scaling row 2, we obtain our reduced echelon form. Notice how simple it is. It has ones on the diagonal and zeros everywhere else. So we started with our coefficient matrix, representing a homogeneous linear system, and a few steps of Gaussian elimination produced our reduced echelon form, which makes it easy to see that the only solution to the system is x equals 0, y equals 0, and z equals 0. In other words, the trivial solution is unique. Let's now think about what would have happened if we had started with a non-homogeneous system with the same coefficient matrix. So suppose that instead of having 0 on the right-hand side of each equation, we had instead arbitrary numbers p, q, and r. Then we would have built our augmented system matrix and done exactly the same steps of Gaussian elimination, which would have given us a reduced echelon form with the same first 3 columns and a fourth column containing numbers p prime, q prime, and r prime that depend on the values of p, q, and r. The solution of the system would then be x equals p prime, y equals q prime, and z equals r prime. And so the system has a unique solution regardless of the values of p, q, and r. What this example demonstrates is that if a homogeneous system has only the trivial solution, then any consistent non-homogeneous system with the same coefficient matrix has a unique solution. If, as in this example, we have the same number of equations as unknowns, then the system will automatically be consistent as well. Now let's consider a homogeneous system with a different coefficient matrix. We'll omit the details, but this coefficient matrix reduces to a reduced echelon form with a row of zeros. And so the system of equations reduces to one in which there are only 2 equations, but we go ahead and write 0 times z equals 0 to stand for the third equation. So we see that the system has infinitely many solutions in which z equals any real number, y equals 2 times z, and x equals minus 3z. Now let's think about what would have happened if instead of having 0 on the right-hand side of each equation, we had arbitrary numbers p, q, and r. We would have formed our augmented system matrix, and the same steps of Gaussian elimination would have produced its reduced echelon form, in which the first 3 columns are the same, and the fourth column contains numbers p prime, q prime, and r prime that depend on the values of p, q, and r. There are 2 possibilities for what happens now. If the number r prime is not 0, then the system will have no solution. On the other hand, if r prime is 0, we can take z to be any real number, and then y equal to 2z plus q prime, and x equal to minus 3z plus p prime, giving us infinitely many solutions to the non-homogeneous problem. Notice the similarity to the solutions of the homogeneous problem. We've simply added p prime to x and q prime to y. Now, what this example illustrates is the fact that if a homogeneous system has a non-trivial solution, which in fact means that it has infinitely many solutions,
then any non-homogeneous system with the same coefficient matrix will have either no solution or infinitely many solutions. Now, combining this with our previous observation, we have a theorem that says that a non-homogeneous system, irrespective of the non-homogeneous terms, has a unique solution if and only if the corresponding homogeneous system has only the trivial solution. We're now going to introduce an important term from linear algebra, the rank of a matrix. The rank of a matrix is defined to be the number of non-zero rows in any echelon form of the matrix, which of course is the same as the number of rows minus the number of zero rows in an echelon form. Let A be the m by n coefficient matrix of a system of m linear equations in n unknowns, and let A plus be the system's augmented matrix. We have seen that 1. The system is consistent if and only if the rank of A is equal to the rank of A plus. This is just a concise way of saying that any zero row in an echelon form of A corresponds to a zero row in an echelon form of A plus, or that the last column of any echelon form of A plus does not contain the first non-zero entry in any row. 2. The system has a unique solution if and only if the rank of A and the rank of A plus both equal n, the number of unknowns, which is also the number of columns in the coefficient matrix. And 3. For any consistent system, the rank of A plus the number of free variables needed to describe the system's solutions is equal to the number of unknowns. The number of free variables used to describe a solution set is the dimension of that solution set. It is a property of the coefficient matrix A since it's always the same as it is for the solution set of the homogeneous system. That set is called the null space of A. So property 3 says that the rank of A plus the dimension of the null space of A equals the number of columns in A. This is a major theorem in linear algebra. Vectors and matrices. Vectors. In the context of linear algebra, a vector, or column vector, in Rn is an n by 1 array of numbers. We say that the vector is in Rn because it may be thought of as a point or a vector in n-dimensional space, but for our purposes here, it mainly just tells us how many entries are in the vector. As you see here, we will use lowercase, boldface, and non-italic letters to denote vectors, and the corresponding non-bold italic letter with subscripts to denote the entries of a vector. The term scalar refers to a real or complex number. A vector x may be multiplied by a scalar c as follows. So the ith entry in c times x is simply c times xi. Addition of two vectors in Rn is defined entry-wise. In other words, we add the first entries, the second entries, and so on, making the ith entry in x plus y xi plus yi. Given vectors x1, x2 through xk in Rn, and scalars c1, c2 through ck, the vector c1x1 plus c2x2 up to ck is called a linear combination of the vectors x1 through xk. For instance, here's a linear combination of the vectors 2, 1, 1 minus 1, and 0, 2 in R2. 2 times 2, 1 plus 3 times 1 minus 1 minus 0, 2. The first term in the sum is the vector 4, 2. The second term is the vector 3 minus 3. And of course the third term is the vector minus 0 minus 2. And so the end result is the vector 7, negative 3. Given a vector A in Rn, the row vector with entries A1, A2, and so forth up to An is called the transpose of A, and vice versa. In other words, the transpose of a column vector is a row vector, and the transpose of a row vector is a column vector.
The product of the row vector A transpose with a vector x is defined as A transpose x equals A1 times x1 plus A2 times x2 and so forth up to AN xn. This is the familiar dot product from calculus. So recall that the vectors A and x are orthogonal, that is perpendicular, if A transpose x is equal to 0. Also, the norm, or length, of a vector x is denoted by double vertical bars around x and equals the square root of x transpose x, which, when written in terms of the entries of x, becomes the square root of the sum of the squares of the entries in x. Matrices. An M by N matrix A is a two-dimensional array of numbers with M rows and N columns. As indicated here, the corresponding lowercase letter with a double subscript is used to denote the entries of the matrix. Notice that the first subscript of each entry indicates its row, and the second subscript of each entry indicates its column. In other words, Aij lives in row I and column J. Also, note that an M by 1 matrix is a vector, and a 1 by N matrix is a row vector. In fact, we can think of any matrix as being composed of an ordered collection of vectors comprising its columns and an ordered collection of row vectors comprising its rows. Matrix vector products. Given an M by N matrix A and a vector x in Rn, the product Ax is the vector in Rm whose ith entry is the product of the ith row of A and x. So to compute A times x, we first multiply the first row of A times x, then the second row of A times x, and so forth until finally the last row of A times x. Note that this can only be done if the number of columns in A is the same as the number of entries in X, and notice also that the number of entries in the result is equal to the number of rows in the matrix A. On the other hand, AX is a linear combination of the columns of A, in which the ith column of A is multiplied by xi. So we could compute the same product by multiplying x1 times the first column of A and adding x2 times the second column of A, and so on up to xn times the nth column of A. Example. Consider the 2 by 3 matrix A whose entries are 1, 2, 3 in the first row and -1, 1, 2 in the second row. For any vector x in R3, we can form the product Ax and compute it by taking the first row of A times the vector x, which gives us x1 plus 2x2 plus 3x3, and then multiplying the second row of A times x, which gives us minus x1 plus x2 plus 2x3. On the other hand, Ax is a linear combination of the columns of A. We could compute the product by taking x1 times the first column of A and adding x2 times the second column of A, and then adding x3 times the third column of A. The first term here is the vector x1 minus x1. The second term is the vector 2x2, x2, and the third term is the vector 3x3, 2x3. Example. Consider the 2 by 2 matrix A equal to 0, minus 1, 1, 0. For any vector x in R2, Ax is the vector whose first entry is 0 times x1 minus 1 times x2, and whose second entry is 1 times x1 plus 0 times x2. Now let's look at this transformation from x to Ax geometrically in the plane. Let's associate the vector x with the point whose coordinates are x1 and x2. Next, let's find x1 on the vertical axis and find minus x2 on the horizontal axis. That lets us find the point associated with AX and to draw the vector AX. Now let's notice that the length or the norm of AX is the same as the length of X, since each one is the square root of x1 squared plus x2 squared. That tells us that the points associated with X and AX both live on the same circle centered at the origin. In fact, the vector AX is the vector X rotated counterclockwise about the origin through an angle of pi over 2. So we have a simple and interesting interpretation of the action of multiplying a vector by A. In fact, this A is a special case of a whole family of rotation matrices. The 2x2 matrix that rotates vectors counterclockwise about the origin through an angle theta has entries cosine theta minus sine theta and sine theta cosine theta. Note that we obtain our matrix A by setting theta equal to pi over 2. Systems of linear equations. Suppose we have a system of linear equations such as the one here. Let's form a vector in R3 using the left-hand side of each equation. Our system of equations will be true if and only if that vector is equal to the vector 1, 0, 1. So in this way, our system of three equations may be thought of as a single vector equation. Also, the vector on the left-hand side is the matrix vector product of this coefficient matrix and the vector x in R4. So now if we name the coefficient matrix A, the vector of unknowns x, and the right-hand side vector b, we see that our system of equations can be expressed very simply as ax equals b. So now any system of linear equations may be thought of as an equation of the form ax equals b, where A is a given matrix, b is a given vector, and x is a vector of unknowns. And we've learned previously that we would solve this equation by row-reducing the augmented matrix obtained by appending B as a last column to the matrix A. What we already know about the equation AX equals B. Let A be m by n, which demands that the vector x be in Rn and b in Rm. We say that AX equals B is underdetermined if m is less than n, since that means that there are fewer equations than unknowns. And we say that AX equals B is overdetermined if m is greater than n, since in that case we have more equations than unknowns. In the underdetermined case, that is when m is less than n, we know that the homogeneous equation AX equals the 0 vector has infinitely many solutions that can be described using n minus rank of A free variables. Now recall that rank of A is the number of non-zero rows in any echelon form of A. So n minus rank of A represents the number of 0 rows in any echelon form of A. Also, if the equation AX equals B is consistent, then it has infinitely many solutions. In other words, any such equation is either inconsistent or has infinitely many solutions. Now in the overdetermined case, when m is greater than n, we know that the homogeneous equation AX equals 0 has only the trivial solution if and only if the rank of A is equal to n. In other words, in any echelon form of A, the number of non-zero rows is equal to the number of columns. We also know that any equation AX equals B may be inconsistent, regardless of the rank of A. This is because, since we have more rows than columns, there's always the potential of obtaining a reduced echelon form for the augmented matrix in which the first non-zero entry in some row is in the last column. Finally, if AX equals B is consistent, it may be reduced to a system with m less than or equal to n. This is simply because any echelon form of A will have at most n non-zero rows. All of this means that in the overdetermined case, the primary issue is what to do when the system is actually inconsistent, something that we're not going to go any further into. Now, the case that we're most interested in is the case that's neither overdetermined nor underdetermined, and this is called the square case, in which m equals n. A matrix with the same number of rows and columns is called a square matrix.
So a square matrix is n by n for some n, and is the coefficient matrix for a system of n linear equations in n unknowns, which is the case in which we expect or at least hope to find a unique solution to the system of equations. We'll state what we've previously learned about this case in the form of a big theorem, and this is version 1 of the theorem. We will be adding more parts to it as we go further. Let A be an n by n matrix. Then the following statements are equivalent. In other words, they're either all true or all false. 1. The rank of A is equal to n. That is, no echelon form of A has a row of zeros. 2. The homogeneous equation AX equals 0 has only the trivial solution. And 3. The equation AX equals B has a unique solution for any vector B in Rn. Linear dependence or independence of vectors. A collection of vectors x1 through xk in Rn is linearly dependent if there are scalars c1 through ck, not all zero, such that c1x1 plus c2x2 and so forth up to ckxk is equal to the zero vector. If the only such scalars are all zeros, then the collection of vectors is said to be linearly independent. In other words, a collection of vectors is linearly dependent if there's a non-trivial linear combination of them that equals the zero vector. Otherwise, they're linearly independent. Now let's observe that any collection of vectors that includes the zero vector is linearly dependent. That's because if we take all scalars to be zero except for the one multiplying the zero vector, then we would have a non-trivial linear combination that equals the zero vector. Also, a collection of two vectors is linearly dependent if and only if one of them is a scalar multiple of the other one. Geometrically, they point in the same or opposite direction. A collection of k vectors is linearly dependent if and only if one of them can be expressed as a linear combination of the others. Example. Let's determine whether the following vectors in R3 are linearly dependent or independent. x1 equals 1, 1, 1, x2 equals 2, minus 1, 3, and x3 equals 1, minus 5, 3. We want to know whether the equation c1x1 plus c2x2 plus c3x3 equals the zero vector holds for some c1, c2, and c3 other than c1 equals c2 equals c3 equals 0. Now, remembering that a matrix vector product can be thought of as a linear combination of the columns of the matrix, we notice that the left-hand side of this equation is a matrix vector product. So we can rewrite the equation as the matrix with x1, x2, x3 as its columns times a vector of unknowns c1, c2, c3 equal to the zero vector. Now, to solve this system, we row reduce the coefficient matrix as follows. First, we subtract row 1 from row 2 and subtract row 1 from row 3. Next, we'll multiply row 2 by minus 1/3 and add 1/3 of row 2 to row 3. And that gives us a row of zeros. Since we have produced an echelon form of the matrix that contains a row of zeros, we know that the system has infinitely many non-zero solutions, one of which we can write down by first setting C3 equal to 1, and then noticing that the second equation would tell us that C2 is minus 2, and then the first equation would tell us that C1 equals minus C3 minus 2C2, which would equal positive 3. Therefore, the vectors x1, x2, and x3 are linearly dependent. In fact, using the values of C1, C2, and C3 above, we can say that 3 times x1 minus 2 times x2 plus x3 is equal to the zero vector. And so in particular, we could express x3 as a linear combination of x1 and x2 by writing minus 3x1 plus 2x2. The equation c1x1 plus c2x2 and so forth up to ckxk equal to the zero vector, which is the equation in the definition of linear dependence, is equivalent to
AC equals 0, where A is the matrix whose columns are x1 through xk, and C is the vector of scalars c1 through ck. So the vectors x1 through xk are a linearly independent set if and only if the equation AC equals 0 has only the trivial solution, which is a property of the matrix A that we can state in terms of its rank. We'll state the result as a theorem. A collection of vectors x1 through xk in Rn is linearly independent if and only if the matrix whose columns are x1 through xk has rank k. That is, it has an echelon form with k non-zero rows. Now let's notice that it's impossible for this matrix to have rank k if k is greater than the number of rows in the matrix, which is n. So we have a corollary that says if k is greater than n, then any collection of k vectors in Rn is linearly dependent. So for instance, we can't have 3 linearly independent vectors in R2, or 4 linearly independent vectors in R3, and so forth. In other words, the number of vectors in any linearly independent set cannot exceed the dimension of the space in which they live. Let's finish here by adding that previous result to our big theorem. This is version 2. Let A be an n by n matrix. Then the following statements are equivalent. 1. Rank of A equals n. 2. AX equals 0 has only the trivial solution. 3. AX equals B has a unique solution for any vector B in Rn. And now the new part 4, the columns of A are linearly independent. Matrix algebra. Our purpose here is to define algebraic operations on matrices. First, multiplication by scalars and addition of matrices are defined in the natural way. For instance, to multiply this matrix by the scalar 3, we simply multiply each entry in the matrix by 3. We can also factor out a scalar that's a common factor of every entry, something that's often done when a matrix contains fractions. Two matrices having the same number of rows and columns may be added entry-wise. You can also think of this in terms of adding the column vectors that comprise the columns of the matrices. Now, with scalar multiplication and addition defined, we can compute linear combinations of matrices provided that they have the same dimensions, that is, the same number of rows and the same number of columns. The product AB of two matrices A and B is defined so that its product with a vector x is the same as multiplication of x first by B and then by A. So it's really more of a composition than a product. Now the first thing we want to notice here is that this only makes sense if the dimensions of A and B are compatible. For instance, if B is this 2 by 3 matrix and x is the column vector 2, 1, minus 1, which lives in R3, then B times x turns out to be the vector 3, 8, which is in R2, and it's in R2 precisely because B had 2 rows. Therefore, A times BX, which would be A times 3, 8, makes sense if and only if A has 2 columns. This is an illustration of the important fact that A times B makes sense if and only if the number of columns in A equals the number of rows in B. So now we can be a little more specific and say that if A is an M by K matrix and B is a K by N matrix, then A times B is the M by N matrix for which AB times any vector x in Rn is equal to A times the vector Bx. This defines the product AB, but it doesn't tell us how to compute it, at least not directly. So how do we compute the product AB? Well, let's let B1, B2 through Bn denote the columns of the matrix B. Then the matrix vector product Bx can be written as a linear combination of those columns, x1 b1 plus x2 b2 and so forth up to xn bn. So now we have A times a linear combination of vectors. Matrix vector multiplication is in fact distributive, and a matrix times a scalar multiple of a vector is the same as the scalar times the matrix vector product. So we can rewrite this as x1 times ab1 plus x2 times ab2 and so forth up to xn times abn. Now this linear combination of vectors is the vector x multiplied by a matrix, the matrix whose columns are ab1, ab2 and so forth up to abn. So ab1 through abn are the columns of the matrix AB. Now the ith entry in a typical column ABJ is going to be the ith row of A times BJ. In other words, the ijth entry of AB is the product of the ith row of A with the jth column of B. The bottom line is this: to compute AB, simply multiply each column of B by the matrix A. Example: compute AB, where A is the 2 by 3 matrix with rows 1, 2, 1 and 2, 0, 1, and B is the 3 by 2 matrix with columns 1, 2, minus 1 and minus 1, 3, 2. Since A is 2 by 3 and B is 3 by 2, the number of columns in A is the same as the number of rows in B, so we know that A times B makes sense, and in fact A times B will end up being a 2 by 2 matrix. So we want to multiply each of the columns of B by the matrix A. The first column in the product will be the product of A with the first column of B, and the second column of the product will be A times the second column of B. Now the first entry in the first column will be the first row of A times the first column of B, and the second entry in the first column will be the second row of A times the first column in B. The first entry in the second column of the product will be the first row of A times the second column in B, and the second entry in the second column will be the second row of A times the second column of B. So the first entry in the first column will be 1 plus 4 minus 1 equals 4. The second entry in the first column will be 2 plus 0 minus 1 equals 1. The first entry in the second column will be minus 1 plus 6 plus 2, which equals 7. And the second entry in the second column will be minus 2 plus 0 plus 2 equals 0. So we have the matrix AB. Multiplication of any vector in R2 by this 2 by 2 matrix is a shortcut for first multiplying by B and then multiplying the result by A. Now we should point out that generally there's no point in showing so much detail in the computations. In fact, once you get used to the idea, you should be able to just write down the result. Example: compute AB and BA if A is the matrix 1, 2, 0, 1 and B is the matrix 1, minus 1, minus 1, 1. Let's start with AB. The first entry in the product will be the first row of A times the first column of B, which gives us 1 minus 2, or minus 1. The second entry in the first column of the product will be the second row of A times the first column of B, which is 0 minus 1, or minus 1. Now the first entry in the second column will be the first row of A times the second row of B, which is minus 1 plus 2 equals 1. And the second entry in the second column will be the second row of A times the second column of B. That's 0 plus 1 equals 1. So we have the matrix AB. Now let's compute BA. The first row of B times the first column of A is 1 minus 0 equals 1. The second row of B times the first column of A is minus 1 plus 0, or minus 1. The first row of B times the second column of A is 2 minus 1 equals 1, and the second row of B times the second column of A equals minus 2 plus 1 equals minus 1. This is the product BA. So notice that the matrix AB and the matrix BA are not the same.
So we see that matrix multiplication is not commutative. In fact, we can expect in general that the dimensions of A and B allow both products to be formed, but even when they can, we can't expect the products to be equal. Otherwise, however, matrix multiplication has the algebraic properties we might expect. Some of those are A times the product BC is the same as the product AB times C. This is an associative property, and it tells us that it makes sense to simply write ABC with no parentheses. Another associative type property is that a scalar C times a matrix product AB is the same thing as C times A times B, as well as A times CB. We also have left and right distributive properties over addition. A times the sum B plus C is the same as the product AB plus the product AC. So matrix multiplication distributes over addition from the left. It also distributes over addition from the right, meaning that a sum AB times C is equal to the product AC plus the product BC. Square matrices and inverses. A matrix is square if it has the same number of rows and columns. Thus, a square matrix A is n by n for some n. For instance, these are 2 by 2 and 3 by 3 square matrices, respectively. The n by n identity matrix, denoted capital I, has ones on its diagonal and zeros elsewhere. Here's the 3 by 3 identity matrix. You'll sometimes see the size of the matrix indicated by a subscript. So this would be I sub 3. The matrix I has the following properties. For any vector x in Rn, I times x equals x, and the row vector x transpose times I is equal to x transpose. So multiplication of a vector by I from the left leaves that vector unchanged, and multiplication of a row vector by I from the right leaves that row vector unchanged. Notice how that works in the n equals 3 case. To multiply a vector x1, x2, x3 by the 3 by 3 identity matrix, we first take the first row of the identity matrix times x, which gives us 1 times x1 plus 0 times x2 plus 0 times x3. So that's x1. The second row of I times x gives us 0 times x1 plus 1 times x2 plus 0 times x3, or x2. And the third row of I times x gives us 0 times x1 and x2 plus 1 times x3. So we end up with the same vector x. Now, to multiply the row vector x transpose on the right by the identity, we take the first and only row in x transpose times the first column of I, giving us x1 times 1 plus x2 times 0 plus x3 times 0, which is x1. And then we multiply x transpose times the second column of I, which gives us x2. And then x transpose times the third column of I gives us x3. And so the result is x transpose. Now let A be any square matrix. From the identity I times x equals x for vectors x, it follows that the columns of I times A are the columns of A. Since to form the product I times A, we simply multiply each column of A by I. And from the identity x transpose I equals x transpose, it follows that the rows of A times I are the rows of A. Therefore, I times A and A times I are both equal to A for all n by n matrices A. This is why I is called the identity matrix. It's the multiplicative identity for matrix multiplication, just as the number 1 is the multiplicative identity for multiplication of scalars. Matrix inverses. An n by n matrix A is invertible if there is an n by n matrix M with the property that A times M equals M times A equals the identity matrix. The matrix M, if it exists, is the inverse of A and is denoted by A with a superscript -1. So assuming that A is invertible, the preceding equation could be written as A times A inverse equals A inverse times A equals the identity matrix. Invertible matrices are sometimes called non-singular, while non-invertible matrices are said to be singular. For an invertible matrix A, the equation AX equals B and the equation X equals A inverse B are equivalent. This is because if we take the equation AX equals B and multiply each side of the equation on the left by A inverse, the left-hand side of the equation becomes A inverse times X, and since A inverse times A is the identity matrix, the left-hand side is simply X. Also, if we start with X equals A inverse B, we can multiply both sides of the equation on the left by A and work our way back to AX equals B. Example. Let A be the 3 by 3 matrix whose rows are 3, 2, 1, 2, 2, 1, and 1, 1, 1. Verify that A inverse is the matrix whose rows are 1, -1, 0, -1, 2, -1, and 0, -1, 2. To do this, we'll compute both matrix products involving the two matrices to see if we get the identity matrix each time. Let's first compute A times its potential inverse matrix. First row times first column gives us 3 minus 2 plus 0, which is 1. Second row times first column gives us 2 minus 2 plus 0, which is 0. And third row times first column gives us 1 minus 1 plus 0, which is 0 also. Then first row times second column gives us minus 3 plus 4 minus 1, which equals 0. Second row times second column gives us minus 2 plus 4 minus 1, which is 1. Third row times second column is minus 1 plus 2 minus 1, which is 0. First row times third column is 0 minus 2 plus 2 equals 0. Second row times third column is 0 minus 2 plus 2, which is 0. And third row times third column is 0 minus 1 plus 2 equals 1. And so we see that we do get the 3 by 3 identity matrix. Next, we compute the potential inverse of A times A, and the calculation proceeds more or less as before. This product is also equal to the identity matrix, and therefore the two matrices are in fact inverses. Example. Let A be the 2 by 2 matrix with rows 1, 1 and 1, 2. Find A inverse if it exists. Let's look for the inverse of A in the form of M equal to a matrix with rows PQ and RS by first requiring that A times M equal I. This equation is equivalent to two linear systems. A times the first column of M equal to the first column of the identity matrix, and A times the second column of M equal to the second column of the identity matrix. Now let's solve the first of these by row reducing its augmented matrix. To zero out the entry below the diagonal in the first column, we'll subtract row 1 from row 2. That gives us a new second row, 0, 1, minus 1. Next, we want to zero out the entry above the diagonal in the second column, so we subtract row 2 from row 1, which makes the new row 1, 1, 0, 2. So we see that the solution of this system is P equal to 2 and R equal to minus 1. Now let's reduce the augmented matrix of the second system. We'll zero out the 1 below the diagonal in the first column by subtracting row 1 from row 2, making the new row 2, 0, 1, 1. And then zero out the entry above the diagonal in the second column by subtracting row 2 from row 1, and that gives us a new row 1 of 1, 0, minus 1. So the solution of this system is Q equal to minus 1 and S equal to 1. Therefore, if A has an inverse, it must be the matrix M with first column PR equal to 2 minus 1 and second column QS equal to minus 1, 1. Now we know that A times M equals I, so we just need to check that M times A equals I as well. This is fairly easy to do mentally, and in fact we do find out that M times A is the identity matrix. Therefore A is invertible, with A inverse equal to the matrix with rows 2 minus 1 and minus 1, 1. In the preceding example, we could have done the two row reductions simultaneously by row reducing the 2 by 4 matrix obtained by first appending to the matrix A the column 1, 0, and also appending the column 0, 1. In fact, you may have noticed that we did exactly the same row reduction steps to solve each of the two systems. We subtracted row 1 from row 2, and then we subtracted the new row 2 from row 1. Now notice what we've done here. We began with an augmented matrix consisting of the matrix A on the left and the identity matrix on the right. We performed Gaussian elimination until the identity matrix was on the left and a new matrix is on the right, and that new matrix is precisely the inverse of A. This is our method for computing A inverse. Start with an augmented matrix whose first n columns are the matrix A and whose last n columns are the identity matrix. Then row reduce until the first n columns are the identity matrix and the last n columns contain the inverse of A. If this process fails, then A is not invertible. And in fact, it will fail if A is not invertible. Example. Let A be this 3 by 3 matrix. Let's find A inverse if it exists. We first build the 3 by 6 matrix consisting of A on the left and the identity matrix on the right. Now we want to zero out the entries below the diagonal in the first column. So we'll subtract 2 times row 1 from row 2 and subtract row 1 from row 3. Next, we want to zero out the entries above and below the diagonal in the second column. So we'll add row 2 to row 1 and subtract row 2 from row 3. Now we just need to zero out the first entry in the third column. We do that by subtracting row 3 from row 1. So now we have the identity matrix on the left, which means that the right half of this augmented matrix contains the inverse of A. So here we have A inverse, and it's a simple calculation to verify that this is in fact the inverse of A. Here's another example. Let A be this 3 by 3 matrix, and let's find A inverse if it exists. We'll form the 3 by 6 matrix consisting of A on the left and the identity matrix on the right. We'll zero out the entries below the diagonal in the first column by subtracting 2 times row 1 from row 2 and by subtracting 1 times row 1 from row 3. Next, we need to zero out the third entry in the second column, so we'll subtract 2 times row 2 from row 3. Now we need to zero out the first entry in the third column, but we can't do that because we have a 0 on the diagonal in the third row. Thus the process has failed, and we conclude that A is not invertible. Now let's wrap this up by updating our big theorem. This will be version 3. Let A be an n by n matrix. The following statements are equivalent. 1. The rank of A equals n. That is, no echelon form of A has a row of zeros. Now, since we've talked about the identity matrix, we'll insert a new statement 2. The reduced echelon form of A is the identity matrix. 3. The homogeneous equation AX equals 0 has only the trivial solution. 4. The equation AX equals B has a unique solution for any vector B in Rn. 5. The columns of A are linearly independent. And 6. A is invertible. If any one of these statements is true, then they're all true,
And if any one of them is false, then they're all false.
Determinants. Let's begin here with an example. Find a formula for the inverse of a 2 by 2 matrix, capital A, with entries A, B, C, and D. In particular, we want to pay attention to what sort of assumptions need to be made in order for the matrix to even be invertible. We begin by augmenting A with the identity matrix. We'll first go ahead and scale the first row by multiplying it by 1 over A. In doing that, we're assuming that A isn't 0. If A were 0, we would switch rows, and then we would have to assume that C was not 0. In any event, we have to assume that either A or C is not 0, and we may as well just assume that it's A. To zero out the entry below the diagonal in the first column, we'll replace the second row with A times row 2 minus C times row 1. Now let's go ahead and scale row 2 by dividing by AD minus BC. There we must assume that AD minus BC is not 0. Now to zero out the off-diagonal entry in the first row, we'll subtract B over A times row 2 from row 1. Some simplification is required here, but after combining terms over a common denominator, we see that all the terms in the third and fourth columns have the denominator AD minus BC. So we can now write down our formula for the inverse. The common scalar factor 1 over AD minus BC may be brought out front of the matrix with entries D minus B minus CA. And this makes sense if and only if AD minus BC is not 0. That is, in fact, the condition for the invertibility of A. And it turns out that we arrive at the same formula even if A is 0 and we interchange rows at the beginning. This is actually a very useful and easy formula to remember. We can write down the inverse of the 2 by 2 matrix by switching the diagonal entries, negating the off-diagonal entries, and then dividing by the determinant of the matrix. Determinants. The determinant of a 2 by 2 matrix A equal to ABCD is the number AD minus BC, the product of the diagonal entries minus the product of the off-diagonal entries. There are two common notations used for the determinant. One is basically absolute value notation. Vertical bars about a matrix indicate its determinant. Also, the abbreviation DET stands for the function that takes a matrix and produces its determinant. We've just seen in the previous example that in the 2 by 2 case, A is invertible if and only if the determinant of A is not 0. In other words, A is singular if its determinant is 0, and non-singular if its determinant is not 0. The determinant of an n by n matrix A will be defined in such a way that this statement will be true in general. Before we talk about the determinant of a 3 by 3 matrix, let's notice that using subscript notation, the 2 by 2 determinant is A11 times A22 minus A12 times A21. The 3 by 3 determinant. The determinant of the 3 by 3 matrix, whose ijth entry is Aij, is given by the following formula. This is a very complicated formula to try to remember, so we need a better, more intuitive way of thinking about it. Let's first notice that the first two terms have a common factor of A11. The other factor, A22 times A33 minus A23 times A32, is actually the 2 by 2 determinant of the matrix A22, A23, A32, A33. Similarly, the third and fourth terms have a common factor of A12. If we factor out minus A12, then the other factor, A23, A31 minus A21, A33, is the determinant of the 2 by 2 matrix with entries A21, A23, A31, A33. And the last two terms have A13 as a common factor, and the other factor is the determinant of A21, A22, A31, A32. So we see that the formula for the 3 by 3 determinant can be expressed in terms of 2 by 2 determinants. Now let's think about this version of the formula, not in terms of the original formula, but in terms of the matrix itself. The first term is the product of the 1, 1 entry of the matrix and the determinant of the 2 by 2 matrix that consists of the entries that are left after deleting the first row and the first column. Similarly, aside from the minus sign, the second term is the product of the 1, 2 entry of the matrix and the determinant of the 2 by 2 matrix obtained by deleting the first row and the second column. And the third term is the product of the 1, 3 entry and the determinant of the 2 by 2 matrix that remains after we delete the first row and the third column. This form of the formula is called an expansion on the first row. It's a sum of terms with alternating sign, each one being the product of an entry from the first row and the 2 by 2 determinant obtained by deleting the row and column of that entry. Now let's go back to the original formula and group terms a little bit differently. Let's take the middle two terms first, and just as before, we'll write that difference as minus A12 times the determinant of A21, A23, A31, A33. Now let's take the first and last terms, which have A22 as a common factor, with the other factor being the determinant of A11, A13, A31, A33. And the second and fifth terms can be written as minus A32 times the determinant of A11, A13, A21, A23. Notice that the factors in front of each of those determinants all come from the second column of the matrix. In fact, the first term is minus A12 times the determinant of the matrix that's left after we delete the first row and the second column. And the second term is A22 times the determinant of the 2 by 2 matrix that's left after we delete the second row and the second column. And finally, the third term is minus A32 times the determinant of the 2 by 2 matrix that's left after we delete the third row and the second column. The formula for the 3 by 3 determinant written this way is an expansion on the second column. And in fact, there are 4 other similar such expansions corresponding to each of the remaining rows and columns, and all of them give the same result. There's an alternating sign pattern in any such expansion. We'll say more about this momentarily, but that sign pattern begins with a plus if the row or column on which the expansion is being done is an odd-numbered row or column. And it begins with a minus sign if the row or column on which the expansion is done is an even-numbered row or column. Example. Let's compute the determinant of the matrix A, whose rows are 4, 2, 1, 2, 2, 1, and 1, 1, 1. We'll first do an expansion on the first row. Since that's an odd-numbered row, the sign pattern begins with a plus. So the expansion is 4 times the determinant of 2, 1, 1, 1, minus 2 times the determinant of 2, 1, 1, 1, plus 1 times the determinant of 2, 2, 1, 1. This is equal to 4 times 2 minus 1, minus 2 times 2 minus 1, plus 1 times 2 minus 2, which equals 4 minus 2 plus 0, or 2. Now, just for the sake of illustration, let's do a different expansion, the expansion on the third row. Again, that's an odd-numbered row, so we begin with a plus sign. 1 times the determinant of 2, 1, 2, 1, minus 1 times the determinant of 4, 1, 2, 1, plus 1 times the determinant of 4, 2, 2, 2. So we have 1 times 2 minus 2, minus 1 times 4 minus 2, plus 1 times 8 minus 4. All this equals 0 minus 2 plus 4 equals 2. So we get the same determinant that we got from the expansion on the first row. The n by n determinant. Suppose that A is n by n, and let M sub ij denote the n minus 1 by n minus 1 matrix obtained by deleting the ith row and the jth column of A. Then, For any I between 1 and n, the determinant of A will equal the sum as j goes from 1 to n of minus 1 to the I plus j power times aij times the determinant of mij. Note that the subscript I is the same in every term of the sum, and it represents the row from which aij is taken. So this is an expansion on the ith row. The factor minus 1 to the I plus j in each term takes care of the sign pattern. That's a plus 1 if I plus j is even, and a minus 1 if I plus j is odd. The first term in the expansion corresponds to j equal to 1, so the sign in front of the first term will be minus 1 to the I plus 1, and I plus 1 is even when I is odd, and odd when I is even. That's why the sign pattern begins with a plus when I is odd, and a minus when I is even. Also, for any j, that is, for any column, the determinant of A is equal to the sum from I equals 1 to n of minus 1 to the I plus j times aij times the determinant of mij. This is the expansion on the jth column. The determinant of the matrix mij is called the ijth minor of A, and these kind of expansions are sometimes called expansions by minors. The expansion on any one particular row or column serves as a definition of the determinant of A. It's a definition in terms of determinants of matrices with one less row and column, which are in turn defined in terms of determinants of matrices with one less row and column, and so on. So no matter how big the matrix A is, we can eventually work our way down to something involving only determinants of 2 by 2 matrices. Example: compute the determinant of this 4 by 4 matrix. As is often the case, we can make our calculation easier by choosing the row or column that has the greatest number of zeros. So let's compute our expansion on the second column. The first term will be 0. But let's notice that the first entry in that column is in row 1 and column 2, and so I plus j is 3, meaning that our sign pattern needs to begin with a minus sign. The next term will be plus 2 times the determinant of the 3 by 3 matrix that remains after we delete the second row and the second column. The next term will be minus 1 times the 3 by 3 determinant that remains after we delete the third row and the second column. And finally, the fourth term will be 0. So now we need to compute two 3 by 3 determinants. Let's compute the first one by expanding on the second row, since it contains a 0. That's an even numbered row, so our sign pattern begins with a minus. The first term will be minus 1 times the determinant of 1, 1, 1 minus 1. The second term is plus 1 times the determinant of minus 1, 1, 1 minus 1. And the third term is 0. Let's compute the second 3 by 3 determinant by expanding on the first row. That will be minus 1 times the determinant of 1 minus 2, 1 minus 1, minus 1 times the determinant of 2 minus 2, 1 minus 1, plus 1 times the determinant of 2, 1, 1, 1. Now in the first set of parentheses, the first of those 2 by 2 determinants will be minus 1 equals minus 2, and the second one will equal plus 1 minus 1 equals 0. So inside those parentheses, we have minus 2 plus 0 minus 0. Now inside the second set of parentheses, the first 2 by 2 determinant is minus 1 plus 2 equals 1. The second 2 by 2 determinant is minus 2 minus minus 2, which is 0. And the third 2 by 2 determinant is 2 minus 1 equals 1. So inside those parentheses, we have minus 1 minus 0 plus 1. So the determinant of A ends up being 2 times 2 minus 0, which equals 4. Cramer's rule. Cramer's rule is an interesting application of determinants. What it does is allow us to express the solution of any linear system of n equations and n unknowns fairly simply in terms of certain determinants. Let's begin with a generic 2x2 system. Ax plus by equals r, and cx plus dy equals s. As a vector equation, this becomes the matrix ABCD times the vector xy equals the vector rs. So xy will equal the inverse of the matrix ABCD times the vector rs, assuming, of course, that the matrix is invertible. Now, remembering our little algorithm for writing down the inverse of a 2x2 matrix, we write 1 over the determinant AD minus BC times the matrix we get by switching the diagonals and negating the off diagonals. That's D minus B minus C A. Now, this matrix D minus B minus CA times RS will have first entry equal to D times R minus B times S, and second entry minus C times R plus A times S. So the x component of the solution is dr minus bs divided by AD minus BC, and the y component of the solution is AS minus CR, also divided by AD minus BC. Now finally, we get Cramer's rule for a 2x2 system by simply observing that these formulas can be expressed in terms of 2x2 determinants. In the formula for x, the denominator, of course, is the determinant of the coefficient matrix ABCD, and the numerator is the determinant of the matrix with columns RS and BD. The thing to notice about that determinant is that it's the determinant of the coefficient matrix with the first column replaced with the right-hand side vector of our equation, RS. Now, in the formula for y, the denominator is the same, and the numerator is the determinant of the coefficient matrix with the second column replaced by the right-hand side vector RS. So this is Cramer's rule for 2x2 systems. The remarkable thing is that essentially the same thing is true for systems of n equations in n unknowns for any n. Now here's the general form of Cramer's rule. Let A be an n by n matrix and B a vector in Rn, and consider the equation Ax equals B. If the determinant of A is not 0, then the ith component of the solution vector x is xi equal to the determinant of a matrix A tilde sub I divided by the determinant of A, where the matrix A tilde sub I is obtained by replacing the ith column of A with the vector B. Example. Use Cramer's rule to solve this linear system. We'll begin by computing the determinant of the coefficient matrix A. Expanding on the first row gives us 2 times the determinant of 3 minus 1 minus 1, 2, minus 1 times the determinant of minus 1 minus 1, 0, 2, minus 0. That's 2 times 6 minus 1 plus minus 2 minus 0, which ends up equaling 8. Next, we'll compute the determinant of the coefficient matrix with the first column replaced by the right-hand side vector B. Let's expand on the first column since it contains 2 zeros. The only non-zero term we get will be minus 1 times the determinant of minus 1, 0, minus 1, 2. So we get minus negative 2 minus 0, or positive 2. This tells us that x, the first component of the solution, is 2 divided by 8, or 1/4. Next, we'll compute the determinant of the coefficient matrix with the second column replaced by B. Expanding on the second column gives us minus 0 plus 1 times the determinant of 2, 0, 0, 2 minus 0, which equals 4. So y equals 4 divided by 8, or 1/2. Finally, we'll compute the determinant of the coefficient matrix with the third column replaced by B. We'll expand on the third column. The only non-zero term we get is minus 1 times the determinant of 2 minus 1, 0 minus 1, which equals minus negative 2 minus 0, or 2. And so z is 2 divided by 8, or 1/4. Altogether, our solution is the vector 1/4, 1/2, 1/4. Properties of the determinant. Let A be an n by n matrix. 1. If A has a row or column of zeros, then the determinant of A is equal to 0. This should be easy to see, since if we have a row or column of zeros, then if we expand on that row or column, every term in the expansion will be 0. 2. If A is upper or lower triangular, then the determinant of A equals the product of its diagonal entries. Let's see how this works in a little example. Suppose we have this matrix here. It's upper triangular, and its diagonal entries are 2, 3, 4, and 5. The expansion of the determinant on the first column yields only one non-zero term, and that's 2 times the determinant of the 3 by 3 matrix that's left when we delete the first row and first column. Now let's expand that 3 by 3 determinant on its first column. That will give us 3 times the 2 by 2 determinant of 4, 7, 0, 5. And that 2 by 2 determinant is equal to 4 times 5 minus 0. So the determinant of our original matrix is 2 times 3 times 4 times 5, the product of its diagonal entries. 3. When a multiple of one row of A is added to another row, the resulting matrix has the same determinant. This property is somewhat complicated to justify, and we'll not go into it here. Just be sure to notice that adding a multiple of one row to another row is a typical Gaussian elimination step. 4. If any row of A is a linear combination of its other rows, then the determinant of A is 0. This property follows from properties 3 and 1, because if A has a row that's a linear combination of other rows, then one can turn that row into a row of zeros by adding multiples of other rows to it. 5. When two rows of A are exchanged, the determinant of the resulting matrix is the negative of the determinant of A. So exchanging rows negates the determinant. The proof of this is again a little more complicated than we want to go into here, but it is very easy to see for a 2 by 2 matrix. Property 6 follows from properties 3 and 5. If E is an echelon form of A obtained without scaling rows, then the determinant of E is equal to minus 1 to the kth power times the determinant of A, where k is the number of row exchanges done. This is because each step of Gaussian elimination used to obtain E from A either doesn't change the determinant, or if the step is a row exchange, it negates it. It turns out that this property gives us a good way to compute determinants, which we'll see in the next example. Example. Compute this 3 by 3 determinant by row reduction. We want to obtain an echelon form of the matrix, which will necessarily be upper triangular, without scaling rows. We'll first zero out the entries below the diagonal in the first column by subtracting 2/3 of row 1 from row 2, and then adding row 1 to row 3. Neither of those steps changes the determinant, since each one involves adding a multiple of one row to another. Now let's zero out the entry below the diagonal in the second column. We'll do that by adding 6 times row 2 to row 3. That step also leaves the determinant unchanged. We now have the determinant of an echelon form of the original matrix that we obtained without scaling rows and also without exchanging rows. Its determinant is the product of its diagonal entries, which gives us 3 times minus 1/3 times 10, which is minus 10. Another example. Compute this 3 by 3 determinant by row reduction. To zero out the entries below the diagonal in the first column, we'll subtract row 1 from row 2 and subtract 3 times row 1 from row 3. Those transformations leave the determinant unchanged. Now, because we have a 0 on the diagonal in the second column, we have to interchange row 2 and row 3. That's a step that negates the determinant. Our matrix is now an echelon form, and the negative of its determinant is minus 1 times minus 7 times minus 1, which gives us negative 7. It's now time to update our big theorem again. This is version 4. Let A be an n by n matrix. The following statements are equivalent. 1. The rank of A is equal to n. 2. The reduced echelon form of A is the identity matrix. 3. The homogeneous equation AX equals 0 has only the trivial solution. 4. AX equals B has a unique solution for any vector B in Rn. 5. The columns of A are linearly independent. 6. A is invertible. And finally, our new entry, 7. The determinant of A is not 0. Probably the simplest way to connect number 7 with statements 1 through 6 is through statement 1. If no echelon form of A has a row of zeros, then no echelon form has a 0 on its diagonal, and so the determinant will not be 0. And likewise, a non-zero determinant implies that no echelon form of A has a 0 on its diagonal, and so A must have rank n. Now we want to emphasize the equivalence of two of these statements in particular, that the columns of A are linearly independent if and only if the determinant of A is not 0. This gives us a way of determining whether a collection of n vectors in Rn is linearly independent. Specifically, vectors x1 through xn in Rn are linearly independent if and only if the determinant of capital X is not 0, where capital X is the matrix whose columns are x1, x2, and so forth up to xn. Example. Determine whether the following vectors are linearly dependent or independent. We just need to form the matrix with those columns and compute its determinant. We may as well just expand on the first row. That will give us 3 times the determinant of 7, 3, minus 1, 3, minus 2 times the determinant of minus 2, 3, 4, 3, plus 4 times the determinant of minus 2, 7, 4, minus 1. That first term is 3 times 21 plus 3. The second term is minus 2 times minus 6 minus 12. And the third term is 4 times 2 minus 28. So our determinant is 72 plus 36 minus 104, which equals 4. So this determinant is not 0. Therefore, the vectors comprising its columns are linearly independent. Matrix eigenvalue problems. Let A be a square matrix. A scalar lambda is called an eigenvalue of A if there is a non-zero vector V such that A times V equals lambda times V. Such a vector V is called an eigenvector of A corresponding to the eigenvalue lambda. And the pair lambda V is called an eigenpair of A. So an eigenpair consists of an eigenvalue along with a corresponding eigenvector. For instance, noticing that the matrix 1, 2, 4, minus 1 times the vector 1, 1 is equal to the vector 3, 3, which is the same as 3 times the vector 1, 1, we see that 3, the vector 1, 1 is an eigenpair of the matrix 1, 2, 4, minus 1. So an eigenvector of a matrix A is a non-zero vector upon which the action of multiplying by A is the same as simple scalar multiplication, and in fact any non-zero multiple of that eigenvector has the same property. The eigenvalue problem for A is that of finding a complete collection of eigenpairs in which all eigenvectors are linearly independent. By a complete collection, we mean one for which the inclusion of any further eigenpairs would result in linear dependence among the eigenvectors. The characteristic polynomial. Suppose that lambda, v is an eigenpair of A. Since the defining equation AV equals lambda v is equivalent to AV minus lambda v equal to the 0 vector,
which is equivalent in turn to the matrix A minus lambda I times V equal to the 0 vector. The matrix A minus lambda I is singular, that is, not invertible, so its determinant must be 0. The left side here, the determinant of A minus lambda I, is called the characteristic polynomial of the matrix A. Its zeros are the eigenvalues of A. Example. Find the eigenvalues of the 2 by 2 matrix A equal to 1, 2, 4, minus 1. Let's first build the matrix A minus lambda I. Lambda I has lambda on its diagonal and zeros everywhere else. So subtracting it from A simply amounts to subtracting lambda from each diagonal entry of A. Next, we'll write down the determinant of that matrix. It's 1 minus lambda times minus 1 minus lambda minus 2 times 4. Multiplying out the first term and simplifying turns this into lambda squared minus 9, which factors into lambda plus 3 times lambda minus 3. This is our characteristic polynomial. It equals 0 when lambda is either plus or minus 3. So these are the eigenvalues of A. Another example. Find the eigenvalues of A equal to the matrix 1 minus 1, 1, 1. To write down the determinant of A minus lambda I, we'll simply subtract lambda from the diagonal entries of A, making those diagonal entries 1 minus lambda and 1 minus lambda. This determinant is 1 minus lambda squared plus 1, which equals 0 when 1 minus lambda squared equals negative 1, which means that 1 minus lambda equals plus or minus I, the square root of negative 1. So our eigenvalues are lambda equal to 1 plus and minus I. This demonstrates that a matrix with real entries can have complex eigenvalues. Example. Find the eigenvalues of this 3 by 3 matrix. We begin by forming the determinant of A minus lambda I by subtracting lambda from the diagonal entries of the matrix. We'll do an expansion on the first row. That gives us minus 3 minus lambda times the determinant of minus 3 minus lambda 2, 1, minus 3 minus lambda, minus 1 times the determinant of 2, 2, 0, minus 3 minus lambda. The determinant in the first term is the square of minus 3 minus lambda minus 2, which is the same as the square of 3 plus lambda minus 2. The determinant in the second term is 2 times minus 3 minus lambda minus 0. So we have a common factor of minus 3 plus lambda, with the other factor being the square of 3 plus lambda minus 2 minus 2. The second factor here is lambda squared plus 6 lambda plus 5, which factors into lambda plus 1 times lambda plus 5. So our characteristic polynomial in factored form is equal to minus lambda plus 3 times lambda plus 1 times lambda plus 5, which tells us that the eigenvalues of the matrix are negative 1, negative 3, and negative 5. Finding eigenvectors. Our goal when solving an eigenvalue problem for an n by n matrix A is to find as many linearly independent eigenvectors as possible. Usually there will be n of them, which always happens when A has n distinct eigenvalues. However, it sometimes happens that there are not n linearly independent eigenvectors. For each eigenvalue lambda, the corresponding eigenvectors are the non-zero solutions of the homogeneous equation A minus lambda I times x equals the 0 vector. So finding eigenvectors will involve row reduction of the matrix A minus lambda I. The number of linearly independent eigenvectors corresponding to a given eigenvalue lambda will equal the number of free variables in the system, which equals the number of 0 rows in any echelon form of A minus lambda I. Example.
Find a complete set of eigenpairs for the 2 by 2 matrix with rows 0, 1, and 2, 1. We first need to find our eigenvalues. To write down the characteristic polynomial, we subtract lambda from each diagonal entry of A and compute the determinant. That gives us minus lambda times 1 minus lambda minus 2, which equals lambda squared minus lambda minus 2. That factors into lambda plus 1 times lambda minus 2, and so our eigenvalues are minus 1 and 2. Now let's find an eigenvector corresponding to the eigenvalue minus 1. A minus lambda I, then, is A plus I, which is the matrix 1, 1, 2, 2. Subtracting 2 times the first row from the second row makes the second row 0, 0. Therefore, the equation A plus I times V equal to the 0 vector, which any eigenvector corresponding to minus 1 must satisfy, is equivalent to the single equation V1 plus V2 equals 0. Now we just want to write down the simplest non-zero solution that we can. If we set V1 equal to 1, then V2 must be minus 1. So one eigenvector is the vector 1 minus 1. And in fact, all other eigenvectors are non-zero multiples of that one. Now let's find an eigenvector corresponding to the eigenvalue 2. The matrix we're interested in here is A minus 2 times the identity, whose rows are minus 2, 1, and 2, minus 1. Let's multiply the first row by minus 1 and add the first row to the second row, resulting in 0, 0. So now we can see that the equation A minus 2 times the identity times V equal to the 0 vector, which is satisfied by any eigenvector corresponding to lambda equal to 2, is equivalent to the scalar equation 2v1 minus v2 equals 0. If we take v1 equal to 1, then v2 will equal 2, so we have the eigenvector 1, 2. Now finally, let's list our eigenpairs. We have the eigenvalue minus 1 with corresponding eigenvector 1 minus 1, and the eigenvalue 2 with corresponding eigenvector 1, 2. Example. Find eigenvectors of this 3 by 3 matrix given that its eigenvalues are minus 1, minus 3, and minus 5. This is the matrix from 2 examples ago. For lambda equal to minus 1, A minus lambda I is equal to A plus I, which is A with 1 added to each diagonal entry. We'll row reduce this matrix by first adding the first row to the second row, making the second row be 0, minus 1, 2, and then adding this new second row to the third row, which makes the third row 0, 0, 0. And so, as will always happen, A minus lambda I has at least one 0 row. From this echelon form of A plus I, we can see that the equation A plus lambda I times V equals 0 is equivalent to the two scalar equations V1 minus V3 equals 0 and V2 minus 2V3 equals 0. Now we just want to write down a simple non-zero solution of these equations. One way to do that is to set V3 equal to 1. Then the first equation tells us that V1 is 1, and the second equation tells us that V2 is 2. So one solution of our system is V equal to the vector 1, 2, 1. This is an eigenvector corresponding to lambda equals minus 1. And in fact, every eigenvector is a scalar multiple of that one. Now let's find an eigenvector corresponding to lambda equals minus 3. A minus lambda I is A plus 3i, so we add 3 to each diagonal entry of the matrix. We'll interchange the first and second rows and subtract the first row from the third row. And we may as well go ahead and multiply the first row by 1/2. Now this echelon form tells us that the equation A plus 3i times V equal to the 0 vector is equivalent to the two scalar equations V1 plus V3 equals 0 and V2 equals 0. Taking V3 equal to 1, the first equation tells us that V1 equals minus 1, and of course the second equation says V2 is 0. So we have an eigenvector V with entries minus 1, 0, 1. Now, lambda equals minus 5 gives us A minus lambda I equal to A plus 5i. which we write down by adding 5 to the diagonal entries of A. Let's multiply the second row by 1/2 and move that row up to the first row, and at the same time let's subtract the old row 1 from the old row 2, making the new second row 0, 1, 2. Now let's subtract the second row from the first row and the second row from the third row. That gives us our row of zeros and puts the matrix in reduced echelon form. So we can now see that the equation a plus 5i times v equals 0 is equivalent to the two scalar equations v1 minus v3 equals 0 and v2 plus 2v3 equals 0. Again, we'll simply set v3 equal to 1 and then observe that the first equation gives us v1 equal to 1 and the second equation gives us v2 equal to minus 2. So we have an eigenvector v equal to 1 minus 2, 1. So to summarize our result, the matrix A has the following eigenpairs. The eigenvalue minus 1 with eigenvector 1, 2, 1, the eigenvalue minus 3 with eigenvector minus 1, 0, 1, and the eigenvalue minus 5 with the eigenvector 1, minus 2, 1. Now a couple of comments about complex vectors and conjugates. First of all, a complex vector is merely a vector whose entries are complex numbers. Any complex vector z can be expressed as x plus iy, where x and y are real vectors called the real and imaginary parts of z. For instance, the vector with entries 2 minus i, 3, and 5i can be written as a real vector 2, 3, 0 plus I times another real vector minus 1, 0, 5. We can also talk about the conjugate of a complex vector in much the same way as the conjugate of a complex number. The conjugate of a vector z equal to x plus iy, where x and y are real vectors, is z bar equal to x minus iy. For instance, the vector z with entries 1 and 2 plus 3i is equal to the real vector 1, 2 plus I times the real vector 0, 3. So its conjugate is the vector 1, 2 minus I times the vector 0, 3, which equals the vector with entries 1 and 2 minus 3i. Now really all that's going on here is that we write down the conjugate of a vector by simply taking the conjugate of every entry in the vector. But thinking of a complex vector in terms of its real and imaginary vector parts will turn out to be important to us later on. Complex eigenvectors. If lambda equal to alpha plus beta I with beta non-zero is an eigenvalue of a real matrix A, then any corresponding eigenvector will have non-zero imaginary part as well. So we can assume that any eigenvector v can be written as r plus iq, where r and q are real vectors and q is not the zero vector. In other words, if A has real entries and has a complex eigenvalue, then it's impossible for a corresponding eigenvector to be real. Also, conjugate pairs of eigenvalues give rise to conjugate pairs of eigenvectors. That is, if v equal to r plus iq is an eigenvector corresponding to lambda equal to alpha plus beta I with beta not zero, then v equal to r minus iq is an eigenvector corresponding to lambda equal to alpha minus beta I. For instance, if we know that one eigenpair of A consists of the eigenvalue 3 plus 2i and the eigenvector 1 plus 7i minus 2, then another eigenpair consists of the eigenvalue 3 minus 2i and the eigenvector 1 minus 7i minus 2. So, even though the complex arithmetic required to find a complex eigenvector is a bit more complicated than the real case, we actually get two linearly independent eigenvectors for the price of one. Example. Find a complete set of eigenpairs for the 2x2 matrix A with rows minus 3, 1 and minus 2, minus 1. We first need to find our eigenvalues, so we subtract lambda from the diagonal entries of A and take the determinant of the resulting matrix. That gives us the quadratic polynomial minus 3 minus lambda times minus 1 minus lambda plus 2. A little simplification then gives us lambda squared plus 4 lambda plus 5. And using the quadratic formula, we find out that the zeros of this characteristic polynomial are the complex numbers minus 2 plus and minus I. These are the eigenvalues of A. Now let's find an eigenvector corresponding to lambda equal to minus 2 plus I. The matrix A minus lambda times the identity matrix equals A plus 2 minus I times the identity matrix. The entries in the first row of this matrix are minus 1 minus I and 1, and the entries in the second row are minus 2 and 1 minus I. Row reduction on a matrix with complex entries can seem rather strange. A good first step to take here is to scale the first row to make its first entry real. That can be done by multiplying by the conjugate of that first entry. So we'll multiply the first row by minus 1 plus I. Minus 1 plus I times minus 1 minus I equals the square of minus 1 minus the square of I, which is 1 plus 1, or 2. Now, having scaled the first row this way, it's easy to see that we can zero out the entry below the diagonal in the first column by adding the new row 1 to row 2. So our second row is now full of zeros, as we should have expected. This echelon form of the matrix tells us that the equation A plus 2 minus I times the identity matrix times V equals the zero vector is equivalent to a single equation 2v1 plus minus 1 plus I times v2 equals 0. We can write down a simple solution of that equation by taking v2 equal to 2 and then v1 equal to 1 minus I. So we have one eigenpair. It consists of the eigenvalue minus 2 plus I and corresponding eigenvector 1 minus I, 2. We can simply write down another eigenpair by taking complex conjugates in this one. We have the eigenvalue minus 2 minus I and corresponding eigenvector 1 plus I, 2. Example. Find a complete set of eigenpairs for this 3x3 matrix. First, we'll find its eigenvalues. We subtract lambda from each of the diagonal entries and compute the determinant. Let's expand on the second column. The first term is minus 0. The second term is minus lambda times the determinant of the 2x2 matrix, whose first row is minus 1 minus lambda minus 1, and whose second row is minus 1 minus 1 minus lambda. The third term will be minus 4 times the determinant of the 2x2 matrix, with minus 1 minus lambda and minus 1 in the first row, and 1 minus 1 in the second row. That first determinant is the square of minus 1 minus lambda minus 1, which is the same as the square of 1 plus lambda minus 1. And the determinant in the last term equals 1 plus lambda plus 1. Now let's go ahead and factor out a minus sign, and then multiply out everything and collect like terms. The result is minus lambda cubed plus 2 lambda squared plus 4 lambda plus 8. Now notice that the first two terms in the parentheses factor as lambda squared times lambda plus 2, while the third and fourth terms factor into 4 times lambda plus 2. So lambda plus 2 is a factor of the entire expression, with the other factor being lambda squared plus 4. We can now write down our eigenvalues. The zeros of the characteristic polynomial are minus 2 and plus and minus 2i. Now let's find an eigenvector corresponding to lambda equals minus 2. The matrix A minus lambda I is A plus 2i, and we'll zero out the entries below the diagonal in the first column by subtracting the first row from the second and by adding the first row to the third row. Now, subtracting 2 times the second row from the third row gives us a row of zeros, and we'll go ahead and multiply the second row by 1/2. This reduced echelon form of the matrix makes it clear that the equation A plus 2i times v equal to the zero vector is equivalent to the two scalar equations v1 minus v3 equals 0 and v2 equals 0. These equations are satisfied by the vector 1, 0, 1. Now let's find an eigenvector corresponding to lambda equal to 2i. We subtract 2i from each diagonal entry of A, and in order to make the first entry in the first column real, we'll multiply the first row by its conjugate minus 1 plus 2i. Now we'll zero out the entries below the diagonal in the first column by multiplying the second row by 5 and subtracting row 1, and multiplying the third row by 5 and adding row 1. Now let's make the diagonal entry in the second column real by multiplying the second row by 1/2 I, and let's zero out the entry below the diagonal in the second column by subtracting 2i times row 2 from row 3. That reveals a zero row. So now we can see that the equation a minus 2i times the identity times v equal to the 0 vector is equivalent to the scalar equations 5v1 plus 1 minus 2i times v3 equals 0, and 5v2 minus 1 plus 3i times v3 equals 0. Now we can write down a simple solution by first taking v3 equal to 5, which makes v2 equal 1 plus 3i, and v1 equal minus 1 plus 2i. Now let's write this eigenvector in terms of its real and imaginary parts. Its real part is the vector minus 1, 1, 5, and its imaginary part is the vector 2, 3, 0. That will allow us to express this eigenvector along with its conjugate in a very simple way. Now finally we can write down all of our eigenpairs. We have the eigenvalue negative 2 with corresponding eigenvector 1, 0, 1, and the conjugate pair of eigenvalues plus and minus 2i along with a conjugate pair of eigenvectors minus 1, 1, 5 plus and minus I times 2, 3, 0. Repeated eigenvalues. Let lambda be an eigenvalue of a square matrix A. The multiplicity of lambda is defined to be its multiplicity as a root of the characteristic polynomial. For instance, if A is a 3 by 3 matrix with characteristic polynomial equal to the square of lambda plus 3 times 2 minus lambda, then the eigenvalues minus 3 and 2 have multiplicity 2 and 1 respectively. An eigenvalue with multiplicity 1 is called simple. An eigenvalue with multiplicity greater than 1 is called repeated. And all of our examples so far have involved only matrices with simple eigenvalues. An eigenvalue with multiplicity m will typically have m linearly independent corresponding eigenvectors. However, all we can guarantee in general is that there will be at most m linearly independent corresponding eigenvectors. An eigenvalue with multiplicity m, for which there are not m linearly independent eigenvectors, is said to be deficient. Example. Find a complete set of eigenpairs for this 3 by 3 matrix. We begin, as usual, by finding the eigenvalues of the matrix. Subtracting lambda from each diagonal entry and then computing the determinant leads eventually to the polynomial minus lambda cubed plus 2 lambda squared minus lambda. We'll factor out minus lambda, leaving the quadratic lambda squared minus 2 lambda plus 1, which is the square of lambda minus 1. So our eigenvalues are 0 and 1, and we'll list 1 twice to indicate that it is a repeated eigenvalue with multiplicity 2. Now let's find an eigenvector corresponding to the eigenvalue 0. A minus lambda I is just A. Switching the first and second rows, and adding the second row to the third row zeroes out the entries below the diagonal in the first column. Then subtracting the second row from the third makes the third row a row full of zeros. So the equation satisfied by any eigenvector is equivalent to the two scalar equations v1 minus v3 equals 0 and v2 plus v3 equals 0. So let's set v3 equal to 1, then v2 equals minus 1, and v1 equals 1. Now let's look at lambda equal to 1. We'll form A minus I by subtracting 1 from each diagonal entry in A, and now by simply adding row 1 to row 2, adding row 2 to row 3, and multiplying row 1 by minus 1, we arrive at the reduced echelon form of the matrix and see that it has 2 rows of zeros. The equation satisfied by any eigenvector is therefore equivalent to a single scalar equation v1 minus v2 minus v3 equals 0. The simplest way to write down two linearly independent eigenvectors is by first taking V3 equal to 1 and V2 equal to 0, making V1 equal 1, and then taking V3 equals 0 and V2 equal to 1, which again makes V1 equal to 1. So we have two linearly independent eigenvectors corresponding to an eigenvalue with multiplicity 2. Now finally, our eigenpairs are the eigenvalue 0 along with eigenvector 1, minus 1, 1, the eigenvalue 1 with corresponding eigenvector 1, 0, 1, and the eigenvalue 1 again with eigenvector 1, 1, 0. One more example. Find a complete set of eigenpairs for this 3 by 3 matrix. It turns out that the characteristic polynomial for this matrix is exactly the same polynomial as in the previous example, minus lambda times the square of lambda minus 1. And so again our eigenvalues are 0, 1, and 1, with 1 listed twice to indicate that it has multiplicity 2. Now let's find an eigenvector corresponding to lambda equal to 0. A minus lambda I is just A, and let's row reduce by multiplying the first row by a half, by adding 1/2 of the first row to the second row, and by subtracting the first row from the third row. Now, subtracting the second row from the third row fills the third row with zeros. So the entries in any eigenvector will satisfy V1 minus V3 equals 0 and V2 plus V3 equals 0. And by setting V3 equal to 1, we get the eigenvector 1 minus 1, 1. Now let's see what happens with the eigenvalue lambda equal to 1. We subtract 1 from each diagonal entry of A. We add row 1 to row 2, which produces a row of zeros that we want to move down to the bottom of the matrix. And we subtract 2 times row 1 from row 3, multiply the result by a half, and write it in the second row. This is our reduced echelon form, and this time our eigenvalue with multiplicity 2 has given us only one row of zeros. Any corresponding eigenvector will have entries that satisfy V1 minus 2V3 equals 0 and V2 plus 2V3 equal to 0. Taking V3 equal to 1 gives us V2 equal to minus 2 and V1 equal to 2. So even though our eigenvalue had multiplicity 2, the system of equations satisfied by corresponding eigenvectors reduced to one in which there was only one free variable. Consequently, we could not write down two linearly independent eigenvectors. So let's go ahead and list our eigenpairs. The eigenvalue 0 with corresponding eigenvector 1, minus 1, 1, and the eigenvalue 1 with eigenvector 2, minus 2, 1, and we note that the eigenvalue 1 is deficient.
Linear differential systems. Let's begin here by looking at an example of a two-tank mixing problem. Let's say that we have two tanks, as indicated here, each containing 100 liters of water. A salt solution flows into the first tank at a rate of 1 liter per minute, with concentration 1 gram per liter. At the same time, the solution in the second tank flows out at the same rate, 1 liter per minute. Let's also assume that the solution in the first tank flows into the second tank at a rate of 3 liters per minute, and that the fluid in the second tank flows back into the first tank through a separate pipe at a rate of 2 liters per minute. So notice that for both tanks, the total volume flow rate in is equal to the total volume flow rate out, and therefore the volume of 100 liters will remain constant in both tanks. Now the unknowns of interest are the amounts of salt in the two tanks. So let's let Y1 of t denote the amount of salt in the first tank with units of grams, and let Y2 of t denote the amount of salt in the second tank. Now we'd like to write down differential equations for those two unknowns. We'll basically describe the rate of change in each amount in the form of rate in minus rate out. Now, having salt solution with concentration 1 gram per liter flowing into the first tank at a rate of 1 liter per minute contributes the term 1 liter per minute times 1 gram per liter to the rate in the Y1 equation. Note that the units for that term end up being simply grams per minute, as they should be, since Y1 has units of grams. Another term contributing to the rate in for Y1 comes from the 2 liter per minute flow from the second tank back into the first. So we write 2 liters per minute times the salt concentration in the second tank, which is Y2, the amount, divided by the volume, 100 liters. Now that same term contributes to the rate out in the Y2 equation. And again, we notice that those terms have the correct units of grams per minute. The 3 liter per minute flow from the first tank into the second contributes to the rate out for the Y1 equation, the term being minus 3 liters per minute times the concentration in the first tank, which is Y1 grams divided by 100 liters. And that same product contributes to the rate in the Y2 equation. Now finally, we have one more term to add to the rate out for Y2, and that will be 1 liter per minute times the concentration in the second tank, which again is Y2 grams divided by 100 liters. So these are our differential equations for Y1 and Y2, which after we simplify and omit the units, become Y1 prime equals 1 minus 0.03 Y1 plus 0.02 Y2, and Y2 prime equals 0.03 Y1 minus 0.03 Y2. So we have a pair of differential equations for the two unknowns Y1 and Y2, and the right-hand side of each equation involves both of those unknowns, so the system is said to be coupled. This is a typical example of the type of problem we like to learn how to solve. Now it turns out that a problem of this sort can be rewritten in a sense as a single equation for a vector unknown. To do that, we begin by building a vector out of the left-hand side of each equation, and then move the differentiation outside of that vector, resulting in the derivative of a vector-valued quantity. Now the terms involving y1 and y2 on the right-hand side of each equation can be written as a matrix vector product. In this case, the matrix can be expressed as 1 over 100 times minus 3, 2, 3, minus 3. And finally, we account for the constant term 1 in the first equation by adding on the constant vector 1, 0. Now, if we denote the vector y1, y2 by y, then on the left side we have y prime. On the right side we have a matrix times y. So let's call that matrix A, and let's call the vector 1, 0 F. Now the equation has the form y prime equals AY plus F. Another context in which these types of problems arise is that of a single higher-order equation. Here's an example of a linear third-order differential equation. The idea here is that we can consider the unknown x along with each of its derivatives up to, but not including the third derivative, as separate unknowns in the problem. So let's let y1 equal x, then y2 equal x prime, and y3 equal x double prime. Then y1 prime is the same as x prime, which is y2, and y2 prime is the same as x double prime, which is y3, and y3 prime is the same as x triple prime, and the differential equation says that x triple prime is equal to cosine t minus 2x prime minus x, all of which is the same as minus 2y2 minus y1 plus cosine t. This system of three first-order differential equations is equivalent to the original third-order equation. Now let's write the system in vector form. We have a vector containing the derivatives of y1, y2, and y3 on the left-hand side, and on the right-hand side we'll have a matrix times the vector y1, y2, y3. The first row of that matrix is 0, 1, 0. The second row is 0, 0, 1. And the third row is minus 1, minus 2, 0. And to account for the cosine t term in the third equation, we add on a vector 0, 0 cosine t. This equation has essentially the same basic form as in the previous example. We have the derivative of a vector quantity y equal to a matrix A times y plus an additional term f. Here, that f depends upon t. T-dependent coefficients. The coefficients in a linear differential system may be continuous functions of t, causing the resulting matrix to have entries that depend on t. For example, here's a pair of equations for x and y that are both linear but certain coefficients do depend upon t. Let's write this as a single differential equation for the vector quantity xy. The terms minus 3x plus y cosine t in the x equation tell us that the first row of our matrix will contain the coefficients minus 3 and cosine t. Likewise, the terms x minus y over t tell us that the entries in the second row of our matrix will be 1 and minus 1 over t. And we need to add the vector containing sine 2t and e to the minus t to account for the terms that don't involve x or y. Now the matrix here may be thought of as a matrix-valued function, capital A of t, and if we denote the vector xy by u, we can write our differential equation as u prime equals a of t times u plus f of t. Now let's note that the minus 1 over t entry in a of t causes a of t to be discontinuous at 0. So altogether, the entries of a of t are continuous on either of the open intervals 0 to infinity or minus infinity to 0. So we could take either of those intervals to be the domain of solutions. The general initial value problem. Each of the previous examples, as well as an abundance of other examples, involve a differential equation of the form y prime minus a matrix A of t times y equals f of t. A collection of initial values for the components of y can be written as a single vector equation, y of t naught equals a given vector y naught. We assume that the entries of the matrix A of t and the vector f of t are continuous on an interval I that contains t naught. The following terminology is in effect. If the matrix A is independent of t, the system is called autonomous. If the vector f of t equals the zero vector for all t, the system is called homogeneous. Also, we'll go ahead and state an existence and uniqueness theorem. If a of t and f of t are continuous on an interval I, then for any t naught in I and any initial vector y naught, there exists a unique solution on I. As a result of linearity, homogeneous systems, that is, equations y prime minus ay equals 0, have the following properties. Given a solution y, any constant multiple c times y is also a solution. And if y1, y2 through yk are solutions, then so is any linear combination of them. That is, c1y1 plus c2y2 and so on up to cky will be a solution for any constant c1 through ck. Also, we should note here that even though we've not explicitly indicated it, the matrix A in the differential equation may depend upon t. Also, because of linearity, non-homogeneous systems, y prime minus ay equals f, have the following properties. The difference between any two solutions satisfies the corresponding homogeneous reduced equation, which is y prime minus ay equals 0. And, given any particular solution z, every solution has the form y plus z, where y is a solution of the corresponding reduced equation. Note that all of these properties correspond to properties that we're familiar with in the context of a single linear equation. Example. Let A of t be the matrix containing 2 over t, 1 over t, 1 over t, 2 over t, which we can rewrite as 1 over t times the matrix 2, 1, 1, 2, and let f of t be the vector minus t, 0. And consider the system y prime minus a of t times y equals f of t for t in the interval 0 to infinity. Verify that a. z of t equal to the vector 0 t squared is a particular solution, and b. y1 of t equal to the vector t minus t, and y2 of t equal to the vector t cubed satisfy the reduced equation. And because of a and b, we'll conclude that for any scalars c1 and c2, the function y of t equal to c1 times t minus t plus c2 times t cubed plus the vector 0t squared, which is equal to the vector with entries c1t plus c2t cubed
and minus c1t plus c2t cubed plus t squared is a solution of the differential equation on the interval 0 to infinity. Now for reference, let's write our differential equation and highlight it. For part A, we want to show that the function z of t equal to the vector 0t squared is a solution. So we compute z prime minus a times z, which explicitly is the expression shown here. Z prime is the vector 0, 2t, and the matrix product here is minus 1 over t times the vector t squared, 2t squared. So we have the vector 0, 2t minus the vector t, 2t, which gives us the vector minus t, 0. This is the vector on the right-hand side of our differential equation, and so we conclude that z of t is indeed a particular solution. Moreover, the calculation is valid so long as t isn't 0, and in particular for all t in the open interval from 0 to infinity. Now, to address part B, we want to show that y1 of t equal to the vector t minus t satisfies the reduced homogeneous equation. So we compute y1 prime minus a times y1 as follows. y1 prime is simply the vector 1 minus 1, and minus ay1 is minus 1 over t times the vector with entries 2t plus minus t and t plus 2 times minus t, which simplifies to minus 1 over t times the vector t minus t. The second term here is equal to minus the vector 1 minus 1, and so the entire expression simplifies to the 0 vector. Next, we do the same thing for y2 of t equal to the vector t cubed, t cubed. We compute y2 prime minus a times y2. y2 prime is equal to the vector 3t squared, 3t squared, and minus ay2 is equal to minus 1 over t times the vector with entries 2t cubed plus t cubed and t cubed plus 2t cubed. And all of this simplifies easily to give us the 0 vector. So y1 and y2 are solutions of the homogeneous reduced equation on any interval that does not contain 0, and in particular on the open interval from 0 to infinity. And again, from all of this, we can conclude that any linear combination of y1 and y2 plus the vector 0t squared is a solution of the non-homogeneous differential equation on the open interval 0 to infinity. Linear independence. A collection of vector functions x1 through xk defined on an interval I is linearly dependent on I if there are scalars c1 through ck, not all 0, such that c1 times x1 plus c2 times x2 and so forth up to ck is equal to the 0 vector for all t in I. For instance, consider these three vector functions. It turns out that 3 times the first one plus 1/3 of the second one minus the third one equals the 0 vector for all t. Consequently, these three vector functions are linearly dependent on any interval I. If a collection of vector functions is not linearly dependent on I, it is said to be linearly independent on I. That is, the collection is linearly independent on I if the only scalars c1 through ck, for which c1 times x1 plus c2 times x2, and so forth up to ck times xk, is equal to the 0 vector for all t in I, are all 0. For instance, consider these three vector functions. Let's determine how we can form a linear combination of these to get the 0 vector. Since the first entry in the second and third vectors is 0 for all t, and the first entry in the first vector is never 0, the coefficient of the first vector must be 0. Now, since the second entry in the second vector is 0 for all t, and the second entry in the third vector is never 0, the coefficient of the third vector must be 0. And finally, the only way that the third entry on the left-hand side of the equation can be 0 is if the coefficient of the second vector is 0. Therefore, we conclude that these three vector functions are linearly independent on any interval. The Wronskian.
Let x1, x2 through xn be n vector functions on an interval I with values in Rn, meaning that they each have n entries, and let capital X of t equal the matrix whose columns are x1, x2 through xn. The determinant of x of t is called the Wronskian of x1 through xn. Example: let x1 be the vector 1 sine t 2t minus 1, let x2 be the vector 0 sine t and 2t, and let x3 be the vector 3 2 sine t and 4t minus 3. Let's note that x1, x2, and x3 are linearly dependent on the entire number line because 3 times x1 minus x2 minus x3 is equal to the 0 vector for all t. So for each fixed t, the numerical vectors x1 of t, x2 of t, x3 of t are linearly dependent as ordinary vectors. Thus, for each t, we should have the determinant of x of t equal to 0. Now let's verify that that is indeed the case. We'll compute our determinant by doing a row expansion on the first row. That gives us 1 times the determinant of the lower right 2 by 2 submatrix, which is sine t times 4 minus 3 minus 4t sine t. The next term is minus 0, and the next term is 3 times the determinant of the lower left 2 by 2 submatrix, which is sine t times 2t minus 2t minus 1 times sine t. The first term here simplifies to minus 3 sine t, and the last term simplifies to 3 sine t, and so our Wronskian is in fact 0 for all t. What we've just seen is true in general, and we state the result as a theorem. Let x1 through xn be n vector functions on an interval I with values in Rn. If that collection of vectors is linearly dependent on I, then their Wronskian is 0 for all t in I. Now we need to be careful with this theorem because it turns out that its converse is not true without an additional assumption. For example, let x1 be the vector function t 2t and x2 the vector function cosine t 2 cosine t. These are clearly linearly independent because neither is a constant multiple of the other. But their Wronskian, the determinant of the 2 by 2 matrix with x1 as first column and x2 as its second column, is equal to 2t cosine t minus 2t cosine t, which equals 0 for all t. Therefore, the converse of the theorem is not true. Linearly independent vector functions can have an identically 0 Wronskian. Here's the crucial theorem concerning the Wronskian in the context of solutions of a homogeneous linear differential system. Let A be an n by n matrix whose entries are continuous on an interval I, and suppose that x1 through xn are solutions of x prime equals ax on the interval I. Then the collection of vectors x1 through xn is linearly independent on I if and only if their Wronskian is not 0 for all t in I. Example: we've seen that y1 of t equal to the vector t minus t and y2 of t equal to the vector t cubed are solutions of the differential equation y prime minus ay equals 0 on the open interval from 0 to infinity, where the matrix A is 1 over t times the 2 by 2 matrix with entries 2, 1, 1, 2. According to our theorem, they are linearly independent on the open interval 0 to infinity because their Wronskian, which is t times t cubed plus t times t cubed, or 2 times t to the fourth, is never 0 for t in the open interval 0 to infinity. Note that the Wronskian is 0 at t equal to 0, but we have to exclude t equals 0 anyway because the matrix in the differential equation is undefined there. Another example. Let x1 be the vector sine t 2 sine t and x2 the vector 1 e to the t. Let's compute their Wronskian and see what we can conclude from it. Their Wronskian is e to the t times sine t minus 2 sine t times 1, which we can factor into e to the t minus 2 times sine t. Now notice that this is equal to 0 when e to the t equals 2, which happens when t is the natural log of 2, and also when t is any multiple of pi. So we can conclude from our theorem that these two functions cannot be solutions of x prime minus a of t times x equals 0 on any interval I that contains the natural log of 2 or a multiple of pi. Now keep in mind that the entries of the matrix A of t are assumed to be continuous on I. So what's happening here is that if x1 and x2 were solutions of some equation x prime minus a of t times x equals 0, then the entries of that matrix would have to have discontinuities at log 2 and each multiple of pi. Now it turns out that x1 and x2 are solutions of such an equation, where the matrix is the one shown here, on any interval on which the entries of that matrix are continuous. And we can notice that continuity of the entries of the matrix A fails precisely at the natural log of 2 because of the 1 over e to the t minus 2 factor in front, and at multiples of pi because of the cotangent function that appears in the matrix. Now just a quick note on how this matrix A of t was found. The matrix capital X of t, whose determinant is the Wronskian here, will satisfy the differential equation, simply because each of its columns do. In other words, x prime of t must equal the matrix A of t times capital X of t. So if we formally compute the inverse of capital X of t and multiply each side of this equation on the right by that, we arrive at A of t equal to capital X prime of t times the inverse of capital X of t. That's where this matrix A of t came from. We'll now state a theorem that essentially describes the structure of the general solution of a homogeneous linear differential system. Let A be an n by n matrix whose entries are continuous on an interval I. Then the following are true about the homogeneous equation x prime equals ax. First, something that we've stated before, for any number t naught in I and any vector x naught in Rn, there exists a unique solution satisfying the initial condition x of t naught equals x naught. By applying that fact with n linearly independent initial vectors x naught, we arrive at 2. There exists a linearly independent collection of n solutions on I. And 3. Given any n linearly independent solutions x1 through xn on I, every solution on I may be expressed as a linear combination of them. This tells us that the general solution of the equation may be constructed by finding n linearly independent solutions and forming a general linear combination of them. Example. Let A of t be the matrix with entries 2 over t, 1 over t, 1 over t, and 2 over t, and let f of t be the vector function with entries minus t and 0. And consider the system y prime minus a of t times y equals f of t for t in the open interval from 0 to infinity. We previously showed that a, the function z of t equal to 0t squared, is a particular solution, and b, that y1 of t equal to t minus t and y2 of t equal to t cubed satisfy the reduced equation and are linearly independent on the open interval from 0 to infinity. We can now conclude that every solution of the homogeneous reduced equation has the form c1y1 plus c2y2, and therefore every solution of the non-homogeneous differential equation has the form y of t equal to c1 times y1 plus c2 times y2 plus z of t, which we can write as a single vector with entries c1t plus c2t cubed and minus c1t plus c2t cubed plus t squared.
Homogeneous systems and the fundamental matrix. Let's begin by recalling the theorem with which we left off last time. Let A be an n by n matrix whose entries are continuous on an interval I. Then the following are true about the homogeneous equation x prime equals ax. 1. For any number t naught in I and any vector x naught in Rn, there exists a unique solution satisfying the initial condition x of t naught equals x naught. 2. There exists a linearly independent collection of n solutions on I. And 3. Given any n linearly independent solutions x1 through xn on I, every solution on I may be expressed as a linear combination of them, x of t equal to c1 times x1 plus c2 times x2, and so on up to cn times xn. Also recall that solutions x1 through xn are linearly independent on I if and only if the determinant of the matrix X of t, which we call the Wronskian, is not 0 for all t in I, where X of t is the matrix whose columns are x1 through xn. The linear combination x of t equal to c1 x1 plus c2 x2 and so on up to cn xn may be written as a matrix vector product. It's equal to the product of the matrix with columns x1 of t, x2 of t, and so on up to xn of t, and the vector with entries c1 through cn. That's the matrix X of t times a constant vector c. If the solutions x1 through xn are linearly independent on I, then the matrix X of t is called a fundamental matrix for the equation x prime equals ax. Or we could say that it's the fundamental matrix associated with the matrix A. Now, recalling that x1 through xn are linearly independent on I if and only if their Wronskian is never 0 on I, and noting that if the columns of a matrix satisfy the differential equation x prime equals ax, then the matrix itself satisfies the same differential equation, we can now say that X of t is a fundamental matrix of the equation x prime equals ax if x prime of t equals a times x of t, and if the determinant of x of t is not 0 for all t in I. And to go along with that fact, given any fundamental matrix X of t of the equation x prime equals ax, every solution of that differential equation on I has the form x of t equals X of t times a constant vector c. Example. Let A be the matrix 1/3 times the 2 by 2 matrix with entries -4, 2, 1, and -5. Show that X of t equal to the matrix with entries 2 e to the minus t, e to the minus 2t, e to the minus t, and minus e to the minus 2t is a fundamental matrix for x prime equals ax on the interval from minus infinity to infinity, and write the general solution of the system. First, we want to verify that the matrix X of t satisfies the differential equation. So we'll compute X prime minus a times X and hopefully show that that is the 0 matrix. So we want to do the computations indicated here. We compute the derivative of X by differentiating each entry in the matrix. That gives us minus 2 e to the minus t, minus 2 e to the minus 2t, minus e to the minus t, and 2 e to the minus 2t. The matrix product in the second term will be minus 1/3 times the matrix whose 1, entry is minus 8 e to the minus t plus 2 e to the minus t, or minus 6 e to the minus t, and whose 1, 2 entry is minus 4 e to the minus 2t minus 2 e to the minus 2t, which is minus 6 e to the minus 2t, and whose 2, 1 entry is 2 e to the minus t minus 5 e to the minus t, which is minus 3 e to the minus t, and whose 2, 2 entry is e to the minus 2t plus 5 e to the minus 2t, which is 6 e to the minus 2t. Now, when we multiply each entry of that matrix by 1/3, it's clear that we're looking at the difference between two matrices that are the same, and so we get the 2 by 2 0 matrix. Next, we want to show that the determinant of X of t is never 0. That determinant turns out to be minus 2 times e to the minus 3t minus e to the minus 3t, which is minus 3 e to the minus 3t, a function that's never 0. Therefore, the columns of X of t are linearly independent solutions of x prime equals ax on the interval from minus infinity to infinity. That is, capital X of t is a fundamental matrix for our differential equation. So the general solution is given by x of t equals capital X of t times c, which is capital X of t times the vector of scalar constants c1 and c2, which equals c1 times the vector 2 e to the minus t plus c2 times the vector e to the minus 2t minus e to the minus 2t. Initial values. Suppose that we have a fundamental matrix, capital X of t, for the equation x prime equals ax, and we want to solve an initial value problem, x prime equals ax, with the initial condition x of t naught equals x naught, where t naught is in I and x naught is a vector in Rn. We know that the solution has the form x of t equals capital X of t times some constant vector c. Since the determinant of capital X of t naught is not 0, capital X of t naught is invertible. So the equation capital X of t naught times c equals x naught, which is what we'd like to solve for the constant vector c in order to satisfy our initial condition, is equivalent to c equal to the inverse of capital X at t naught times x naught. Therefore, the solution is equal to capital X of t times the inverse of capital X at t naught times x naught. The matrix here, capital X of t times the inverse of capital X at t naught, is a special fundamental matrix for initial value problems at t naught, and we'll denote this special matrix by capital phi sub t naught of t. This is the unique fundamental matrix whose value at t naught is the identity matrix. In other words, when we evaluate capital phi sub t naught of t at t naught, we get capital X of t naught times the inverse of capital X of t naught, which will be the identity matrix. Now let's summarize all this as a method for solving our initial value problem. First, we need to find n linearly independent solutions, x1 through xn, of the differential equation. Next, we construct the fundamental matrix capital X of t, whose columns are the solutions x1 through xn. Next, we compute the special fundamental matrix capital phi sub t naught of t equal to capital X of t times the inverse of capital X at t naught. And then finally, we compute the solution x of t equal to capital phi sub t naught at t times the initial vector x naught. Now, there are alternatives to steps 3 and 4 that let us avoid computing the inverse of capital X of t naught. In step 3, we may as well simply solve the equation capital X of t naught times c equals x naught for the constant vector c. That, in essence, gives us the result of multiplying x naught by the inverse of capital X at t naught. Then step 4 is simply to compute the solution as capital X of t times c. Example. In a previous example, we verified that y1 of t equal to the vector t minus t and y2 of t equal to the vector t cubed are linearly independent solutions of y prime equals ay on the open interval from 0 to infinity, where A is the matrix 1 over t times the 2 by 2 with entries 2, 1, 1, 2. Let's find the solution that satisfies the initial condition y of 1 equals the vector 2, 1. Now first let's note that capital Y of t equal to the matrix whose columns are the solutions y1 and y2 is a fundamental matrix. Now let's compute the fundamental matrix capital phi sub 1 of t, which is capital Y of t times the inverse of capital Y at 1. Capital Y at 1 is the matrix with entries 1, 1, minus 1, and 1, and we'll write down its inverse using our simple method for the inverse of a 2 by 2 matrix. The determinant of the matrix is 2, and so we have 1/2 times the same matrix with the diagonal entries switched and the off-diagonal entries negated. And this matrix product turns out to be 1/2 times the matrix with entries t plus t cubed minus t, t cubed minus t again, and t plus t cubed again. And notice that if we evaluate this matrix at t equal to 1, we do in fact get the identity matrix. Now, the solution of our initial value problem is y of t equal to capital Phi sub 1 of t times the initial vector y naught, which is a straightforward computation, resulting in 1/2 times the vector with entries 3t cubed plus t and 3t cubed minus t. Now let's do the same thing, but without inverting a matrix. We want to solve capital Y of 1 times c equals y of 1 for c, and then compute y of t equal to capital Y of t times that vector c. Now here's what capital Y of 1 times c equals y of 1 looks like. So we form our augmented matrix and compute its reduced echelon form. That tells us that c is the vector 1/2, 3/2. Then we compute the solution by multiplying that vector c by our fundamental matrix capital Y of t, and the result, of course, is the same as before. Autonomous systems. In the case where A is independent of t and t naught is equal to 0, the special fundamental matrix capital Phi sub 0 of t is called the matrix exponential and is denoted by e to the at. That is, given any fundamental matrix capital X of t for x prime equals ax, we define e to the at to be capital X of t times the inverse of capital X at 0. Using this notation, which is really all it is at this point, x of t will satisfy x prime equals ax with x of 0 equals x naught if and only if x of t is equal to e to the at times x naught, which looks similar to the solution in the single equation case. A function x satisfies the single differential equation x prime equals ax, where a is a number, and has initial value x of 0 equal to x naught, if and only if x of t is equal to x naught times e to the at. Example. Given that A has constant entries and that a fundamental matrix for x prime equals ax is given by capital X equal to the 2 by 2 matrix whose first column contains 2 e to the minus t and e to the minus t, and second column contains e to the minus 2t and minus e to the minus 2t. A. Compute e to the at, and B. Solve x prime equals ax with initial vector x of 0 equal to the vector 1, 2. Since we already have a fundamental matrix, computing e to the at is just a matter of multiplying that fundamental matrix on the right by the inverse of its value at 0. Its value at 0 is the matrix with entries 2, 1, 1, minus 1, whose inverse is equal to 1 over its determinant, which is negative 3, times the matrix with the diagonals reversed and the off-diagonals negated. Now, just for convenience, let's pull positive 1/3 out front and multiply the second matrix here by negative 1 before finally computing the matrix product. So here we have e to the at, and notice that in fact its value at t equal to 0 is the identity matrix. Now the solution satisfying x of 0 equal to the vector 1, 2 is x of t equal to e to the at times x of 0, which equals e to the at times the vector 1, 2, and this simple calculation leads us to 1/3 times the vector with entries 6 e to the minus t minus 3 e to the minus 2t and 3 e to the minus t plus 3 e to the minus 2t. And finally, by multiplying through by the 1/3 factor in front, we arrive at the vector with entries 2 e to the minus t minus e to the minus 2t and e to the minus t plus e to the minus 2t. Finding a fundamental matrix in the autonomous case. Here we're dealing with the equation x prime equals ax, where a has constant entries. Recall that to build a fundamental matrix, we need n linearly independent solutions of the equation. We'll look for solutions in the form of x of t equal to e to the lambda t times a constant vector v. Now, for x of t equal to e to the lambda t times v, x prime will simply equal lambda times e to the lambda t times v. So the equation x prime equals ax is true if and only if lambda e to the lambda t times v equals a times e to the lambda t times v. Here we can divide out e to the lambda t and arrive at the equivalent equation av equals lambda v. Therefore, x of t equal to e to the lambda t times v is a solution of x prime equals ax if and only if lambda comma v is an eigenpair of a. That is, lambda is an eigenvalue of a with corresponding eigenvector v. Now, a collection of solutions of this type corresponding to linearly independent eigenvectors will be a linearly independent set of solutions. So we have the following theorem. If A is n by n and has eigenpairs lambda 1 v1 through lambda n vn, in which the eigenvalues are real and the eigenvectors are linearly independent, then a fundamental matrix for x prime equals ax is given by capital X of t equal to the matrix with columns e to the lambda 1 t v1 through e to the lambda n t vn. So each column is an eigenvector of a multiplied by e to the lambda t, where lambda is the corresponding eigenvalue. Example. Suppose that A is a 2 by 2 matrix with eigenpairs -2 with the vector 1 minus 1 and -3 with the vector 2, 1. A, compute e to the at, and B, find the solution of x prime equals ax with x of 0 equal to the vector 0, 1. From the given eigenpairs, two linearly independent solutions of x prime equals ax are e to the minus 2t times the vector 1 minus 1 and e to the minus 3t times the vector 2, 1. So a fundamental matrix is capital X of t equal to the matrix whose columns are those two solutions. Now we can compute e to the at by multiplying that fundamental matrix on the right by the inverse of its value at 0. That inverse is 1 over the determinant of the matrix times the matrix with its diagonal entries reversed and its off-diagonal entries negated. Now factoring the 1/3 out front and carrying out the matrix multiplication, we arrive at the matrix shown here. Now we can compute the solution of the initial value problem in part B by simply multiplying the initial vector by this e to the at. Since the initial vector is 0, 1, that multiplication simply picks out the second column of e to the at. That's the vector with entries minus 2 e to the minus 2t plus 2 e to the minus 3t and 2 e to the minus 2t plus e to the minus 3t. So we now know how to solve any autonomous homogeneous system in which the matrix has real eigenvalues and n linearly independent eigenvectors. Next time, we'll learn how to handle the case of complex eigenvalues, as well as the case where the matrix does not have n linearly independent eigenvectors. Complex and deficient eigenvalues. Let's begin with a quick review of what we've just learned. Capital X of t is a fundamental matrix of the equation x prime equals ax on an interval I if capital X prime of t is equal to a times capital X of t, and if the determinant of capital X of t is non-zero for all t in I. Recall that capital X prime equals a times capital X just means that each column of capital X of t satisfies the differential equation. And, given any fundamental matrix capital X of t of the equation x prime equals ax, every solution has the form x of t equals capital X of t times a constant vector c. That's just a compact way of expressing an arbitrary linear combination of the columns of capital X of t. We also have the following theorem. If A is n by n and has eigenpairs lambda 1 v1 through lambda n vn, in which the eigenvalues are real and the eigenvectors are linearly independent, then a fundamental matrix for x prime equals ax is given by capital X of t equal to the matrix with columns e to the lambda 1t v1 through e to the lambda nt times vn.
We're next going to learn how to build a fundamental matrix in the case where A has complex eigenvalues. Complex eigenvalues. If A has a complex conjugate pair of eigenvalues, alpha plus and minus beta I, with corresponding eigenvectors r plus and minus I times q, then x prime equals ax has a pair of complex solutions, e to the alpha plus beta I times t times the vector r plus iq, and e to the alpha minus beta I times t times the vector r minus iq. This is just as in the real case, except these solutions are not acceptable to us because they have complex values. We can rewrite them using Euler's identity. We replace e to the alpha plus and minus beta I times t with e to the alpha t times cosine beta t plus and minus I times sine beta t. Next, by expanding the complex products in each of these solutions, we arrive at the form shown here, in which we can identify the real and imaginary parts of each solution. Now note that if we add these two solutions, we obtain a real solution. Also, if we subtract the second from the first, we end up with a purely imaginary solution, which after dividing by or multiplying by I becomes real. So, by adding and subtracting and scaling these, or simply by extracting their real and imaginary parts, we get two linearly independent real solutions, e to the alpha t times cosine beta t times r minus sine beta t times q, and e to the alpha t times sine beta t times r plus cosine beta t times q. So these are our formulas for solutions corresponding to a complex conjugate pair of eigenvalues. Example. Let A be the 2 by 2 matrix with entries 1, 6, minus 3, and minus 5. A. Find a fundamental matrix for x prime equals ax, and B. Compute e to the at. We first need to find the eigenvalues of A. The characteristic polynomial is the determinant of the 2 by 2 matrix 1 minus lambda, 6, minus 3, minus 5 minus lambda, which is 1 minus lambda times minus 5 minus lambda plus 18. That's lambda squared plus 4 lambda plus 13, which after completing the square becomes the square of lambda plus 2 plus 9. Now that expression equals 0 if lambda plus 2 squared is negative 9, which implies that lambda plus 2 equals plus or minus 3i. So our eigenvalues are lambda equal to minus 2 plus and minus 3i. Now let's find an eigenvector corresponding to minus 2 plus 3i. The matrix A minus lambda I is the 2 by 2 matrix with entries 3 minus 3i, 6, minus 3, and minus 3 minus 3i. Now we'll row reduce the matrix. Let's first divide both rows by 3. Then let's multiply the first row by 1 plus I, which will make the 1, 1 entry 2, and let's also multiply the second row by negative 2, so that the 1, 2 entry will also be a 2. Now, subtracting the first row from the second makes the second row 0, 0, and we divide the first row by 2, making the first row 1, 1 plus I. So, the vector v is an eigenvector if its entries satisfy v1 plus 1 plus I times v2 equals 0. That will be true if we take v2 equal to minus 1 and v1 equal to 1 plus I. So we have the complex eigenpair consisting of minus 2 plus 3i with eigenvector 1 plus I minus 1. That's all we need to write down two real solutions of the differential equation. Here are the formulas from the previous page. In this case, we have alpha equal to negative 2 and beta equal to 3, which we'll go ahead and put in the formulas. Now, the vectors r and q are the real and imaginary parts of our eigenvector. So let's write the eigenvector as the real part 1 minus 1 plus I times the imaginary part 1, 0. So we substitute this r and q into each of our formulas. The first solution becomes e to the minus 2t times the vector whose first entry is cosine 3t minus sine 3t, and second entry is minus cosine 3t. Now the second solution becomes e to the minus 2t times the vector whose first entry is sine 3t plus cosine 3t, and whose second entry is minus sine 3t. Now let's build a fundamental matrix with these two solutions as its columns. Now let's compute e to the at. All we need to do is multiply our fundamental matrix on the right by the inverse of its value at 0. Its value at 0 is the matrix with entries 1, 1, minus 1, 0, whose determinant is 1, so we just switch the diagonal entries and negate the off-diagonal entries to obtain the inverse. And finally, we'll compute this matrix product, and then observe that this is indeed the identity matrix when t is equal to 0. Another example. Let A be the 3 by 3 matrix with eigenvalues minus 2, minus 3, plus and minus 4i, and the corresponding eigenvectors shown here. Let's find a fundamental matrix for x prime equals ax. First, the real eigenpair, consisting of minus 2 and the vector 1, minus 2, 1, tells us that e to the minus 2t times that eigenvector is a solution of the differential equation. Now let's write the complex eigenvectors corresponding to minus 3 plus and minus 4i in terms of their real and imaginary parts. The real part of each of them is the vector 1, minus 1, 0, and their imaginary parts are the vectors plus and minus 0, 2, minus 1. Note here that we have to be careful to keep our plus and minuses straight so that they're consistent between the eigenvalues and the eigenvectors. Now, here again are the formulas for real solutions corresponding to these complex eigenpairs. Our alpha is minus 3 and our beta is 4. So here are our solutions in terms of the vectors r and q. Now let's turn the page, and into the first solution substitute r equal to the vector 1, minus 1, 0, and q, the vector 0, 2, minus 1, and rewrite the result as e to the minus 3t times the vector with entries cosine 4t, minus cosine 4t minus 2 sine 4t, and sine 4t. Using the same vectors r and q in the second formula, ends up giving us e to the minus 3t times the vector with entries sine 4t, minus sine 4t plus 2 cosine 4t, and minus cosine 4t. So we now have three linearly independent solutions of our differential equation, and those three vectors become the columns of our fundamental matrix, capital X of t. Now finally, one relatively minor point. We can simplify this somewhat by factoring out e to the minus 3t. Note that that changes the e to the minus 2t factor of the first column to e to the t. Deficient eigenvalues. We now know how to construct a fundamental matrix corresponding to any n by n matrix A that has n linearly independent eigenvectors. However, that's not always the case, and when it's not, at least one of the eigenvalues of A is said to be deficient. More precisely, let lambda be an eigenvalue of A with multiplicity m as a root of the characteristic polynomial, and let v1 through vk be a complete set of corresponding linearly independent eigenvectors. If k is less than m, we say that lambda is a deficient eigenvalue with deficiency k minus m. For instance, if lambda is a double root of the characteristic polynomial and yet does not have two linearly independent eigenvectors, then that eigenvalue is deficient with deficiency 1. If A has a deficient eigenvalue, there are not enough eigenpairs to construct a fundamental matrix for x prime equals ax. Example. Let A be the 2 by 2 matrix with entries 4, 1, minus 1, 2. Then the characteristic polynomial of A is equal to 4 minus lambda times 2 minus lambda plus 1. That's equal to lambda squared minus 6 lambda plus 9, which equals the square of lambda minus 3. So A has only one eigenvalue with multiplicity 2. Now let's find eigenvectors. The matrix A minus 3i has entries 1, 1, minus 1, minus 1,
which clearly row reduces to the matrix 1, 1, 0, 0. So V is an eigenvector corresponding to lambda equals 3 if its entries satisfy V1 plus V2 equals 0. So we can take V1 equal to 1 and V2 equal to minus 1. And we can observe that every other eigenvector is simply a constant multiple of this one. So while lambda equals 3 is a double root of the characteristic polynomial, no two eigenvectors can be linearly independent, and so the eigenvalue is deficient. And note that we only get one solution of our differential equation by the ordinary means that we've learned so far. Now, suppose that lambda v is an eigenpair in which lambda is deficient. We know that e to the lambda t times v is a solution of x prime equals ax. Let's look for another solution in the form of x of t equal to e to the lambda t times v plus w, where w is a vector that we'd like to determine. Note that this has the form of our known solution, e to the lambda t times v, multiplied by t plus some unknown vector w times e to the lambda t. Or one can think of it as e to the lambda t times an antiderivative of the vector v. Anyway, we'd like to choose w so that this satisfies our differential equation. So let's compute x prime minus ax. Using the product rule, x prime is lambda times e to the lambda t times tv plus w plus e to the lambda t times the derivative of tv plus w, which is just v. And minus ax is minus e to the lambda t times av plus aw. Now let's factor out e to the lambda t and multiply lambda through tv plus w. Then we have plus v from the middle term and minus tav, which equals minus lambda tv because v is an eigenvector corresponding to lambda, and then minus aw. Now lambda tv minus lambda tv adds up to 0, and so this expression becomes e to the lambda t times lambda w plus v minus aw, which we want to equal the 0 vector. That will only happen if the vector in the parentheses equals 0, and that equation can be written as a minus lambda I times w equals v. So, assuming lambda is deficient, the function e to the lambda t times tv plus w is a solution of x prime equals ax if w is any solution of the algebraic equation a minus lambda I times w equals v. Such a vector w is called a generalized eigenvector of a corresponding to lambda. Example. Let A be the 2 by 2 matrix, 4, 1, minus 1, 2. We've previously found that 3, the vector 1 minus 1 is its only eigenpair, at least in the sense that in any other eigenpair, the eigenvector would just be a constant multiple of this one. So we need to solve the system A minus lambda I times W equals V for W, where lambda equals 3 and V is the vector 1 minus 1. The matrix A minus 3I here becomes 1, 1, minus 1, minus 1. So let's form the augmented matrix for this system, and note that clearly it row reduces to the matrix whose first row contains 1, 1, 1, and second row 0, 0, 0. This tells us that the entries of W must satisfy W1 plus W2 equals 1, and the simplest choice we can make here is the vector W equal to 1, 0. Note that 0, 1 would also work, or any linear combination of those two, but it turns out that we get everything we need from one simple choice. Now we build the function e to the lambda t times tv plus w. That's e to the 3t times the vector 1 minus 1 plus the vector 1, 0. And all of that turns into e to the 3t times the vector with entries t plus 1 and minus t. So now we can build our fundamental matrix. Capital X of t equal to e to the 3t times the matrix whose first column is our eigenvector, 1 minus 1, and whose second column is t times v plus w, which is the vector with entries t plus 1 and minus t. And while we're at it, we may as well compute e to the at, that's our fundamental matrix capital X of t, times the inverse of that matrix evaluated at 0. The determinant of that matrix is 1, and so its inverse is obtained by simply switching the diagonals and negating the off diagonals. And carrying out the matrix multiplication here finally gives us e to the 3t times the 2 by 2 matrix with entries t plus 1, t minus t, and 1 minus t. Handling deficient eigenvalues in general. Here we're going to lay out in table form the computations that lead to a sufficient number of solutions of x prime equals ax for the construction of a fundamental matrix in the case where the matrix A has one or more deficient eigenvalues. For lambda with deficiency d, compute v0, v1, and so forth up to v sub d and resulting solutions of the differential equation as follows. First solve a minus lambda I times v0 equal to the 0 vector. That simply gives us an ordinary eigenvector corresponding to lambda. And of course, the resulting solution of the differential equation is simply e to the lambda t times v0. Then solve a minus lambda I times v1 equals v0 for v1. That's the vector w from the previous example. And the resulting solution of the differential equation is e to the lambda t times v0 plus v1. Then, if the deficiency of the eigenvalue is greater than 1, solve a minus lambda I times v2 equals v1 for the vector v2. And the resulting solution of the differential equation is e to the lambda t times 1/2 t squared v0 plus t times v1 plus v2. Now, if the deficiency of the eigenvalue is greater than 2, we continue this process until finally we solve a minus lambda I times the vector v sub d, where d is the deficiency, equal to v sub d minus 1, and write the resulting solution of the differential equation as e to the lambda t times 1 over d factorial times t to the d power times v0 plus lower order terms down to t times v sub d minus 1 plus v sub d. So notice that each term in the parentheses has a numerical coefficient equal to 1 over the factorial of the power of t in that term. Now, one more example. Let A be the 3 by 3 matrix shown here, whose characteristic polynomial turns out to be minus the cube of lambda plus 2. So we have a single eigenvalue, negative 2, with multiplicity 3. So let's begin here by finding eigenvectors. We form the matrix A minus lambda I, that is, A minus negative 2i, and then row reduce. Let's first multiply the third row by minus 1 and bring that up to the first row, and move the first and second rows down to become the second and third rows. Now let's add 3 times the first row to the second, and subtract 2 times the first row from the third row. Now adding the second row to the third row, dividing the second row by minus 8, and subtracting 3 times that new second row from the first, gives us our reduced echelon form. So any eigenvector v has entries that satisfy the equations v1 minus v3 equals 0 and v2 equals 0. So we can take v3 equal to 1, making v1 equal 1, and of course v2 equals 0. So we have the vector with entries 1, 0, and 1, and every other solution of that system is a constant multiple of this one. So no linearly independent collection of eigenvectors can contain more than one vector. So negative 2 is an eigenvalue with deficiency 2, and therefore we need to find 2 generalized eigenvectors. Now the next step is to solve the system A plus 2i times v1 equal to v0. This is the augmented matrix for that system, and exactly the same row reduction steps as before leads to its reduced echelon form. Here the third variable is free, but we may as well set that equal to 0, making the first 2 entries in the solution minus 1/4 and plus 1/4. Now that generalized eigenvector, v1, leads to the solution e to the minus 2t times t times the original eigenvector v0 plus v1. Now t times v0 contributes t times 1 in the first entry and t times 1 in the third entry, and we get minus 1/4 in the first entry and plus 1/4 in the second entry from v1. Now any scalar multiple of this solution will also be a solution, so we may as well multiply it by 4 and write e to the minus 2t times the vector with entries 4t minus 1, 1, and 4t. Now we need to be careful here. We're not allowed to scale the generalized eigenvector here, but we are allowed to scale the resulting solution, which basically amounts to scaling both the eigenvector and the generalized eigenvector by the same factor. Now let's write down what we have so far. Lambda equals minus 2 has deficiency 2. V0 equal to 1, 0, 1 is an eigenvector, and the resulting solution is x equal to e to the minus 2t times 1, 0, 1. Our first generalized eigenvector, v1, is 1/4 times the vector minus 1, 1, 0, and the resulting solution is e to the minus 2t times the vector with entries 4t minus 1, 1, and 4t. Now we need to find one more generalized eigenvector. For that, we need to solve the system a plus 2i times v2 equals v1. Here's the augmented matrix. And again, the same row reduction steps lead us to the reduced echelon form. And again, the third variable here is free, and we may as well take the third entry in the solution to be 0. That gives us v2 equal to 1 over 32 times the vector 3, 1, 0. And the resulting solution of the differential equation is e to the minus 2t times 1/2 t squared times v0 plus t times v1 plus v2, which is e to the minus 2t times 1/2 t squared times the vector 1, 0, 1 plus t times 1/4 times the vector minus 1, 1, 0 plus 1 over 32 times the vector 3, 1, 0. Now if we factor out 1 over 32 and simplify, that becomes 1 over 32 times e to the minus 2t times the vector with entries 16t squared minus 8t plus 3, 8t plus 1, and 16t squared. And we may as well multiply that solution by 32. So finally we have three linearly independent solutions of our differential equation, with which we can build the fundamental matrix that you see here.